Section 29 of A Textbook of Assaying for the Use of Those Connected with Mines, by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recorded by Peter Yearsley. Chapter 12. Tin, Tungsten, Titanium. Part 1. Tin. Tin occurs in nature as cassiterite, containing from 90 to 95% of oxide of tin, which mineral is the source from which the whole of the tin of commerce is derived. Tin also occurs as sulphide combined with sulphides of copper and iron in the mineral stannine, or bell metal ore. It is a constituent of certain rare minerals, such as tantalite. The methods of assaying tin in actual use are remarkable when compared with those of other metals. The more strictly chemical methods are rendered troublesome by the oxide being insoluble in acids, resembling in this respect the gangue with which it is associated. Moreover, it is not readily decomposed by fusion with alkalis. The oxide has first to be reduced to metal before the tin can be dissolved. The reduction may be performed by fusing with potassic cyanide, by heating to moderate redness in a current of hydrogen or coal gas, or by heating to a higher temperature with carbon. The reduced metal is only slowly dissolved by hydrochloric acid, and although it is readily soluble in aqua regia, the solution cannot be evaporated or freed from the excess of acids by boiling without loss of tin because of the volatility of stannic chloride. There has long been a difficulty in getting a quick, wet method. The process of assaying tin ores adopted in the mines of Cornwall is a mechanical one known as vanning, the object of which is to find the percentage of black tin, which, it is well to remember, is not pure cassiterite, much less pure oxide of tin. Tin ore, as taken from the lode, contains from 2 to 5% of cassiterite, and is mainly made up of quartz, feldspar, chlorite, schorl, and other stony minerals, together with more or less mispickel, iron and copper pyrites, oxide of iron, and wolfram. The cassiterite has a specific gravity, 6.4 to 7.1, considerably higher than that of the vein stuff, 2.5 to 3.0, and is concentrated by a series of washings till it is free from the lighter material. Those minerals which have a specific gravity approaching that of the cassiterite ore are not completely removed. The mispickel and copper and iron pyrites are converted into oxides by roasting, and are in great part removed by a subsequent washing. The concentrated product is known as black tin, and in this condition is sold to the smelter. The chief foreign matters in the black tin are silica, oxides of iron and copper, and wolfram, with traces of manganese and niobic acid, and in certain stream ores there may be as much as 6 or 7% of titaniferous iron. The black tin from the mines contains from 5 to 12% of water, and is sold and assayed wet. A series of typical samples of black tin ranged as follows: source of material, good mine ore, percentage of metal in dry ore, 72.0, specific gravity, 6.39. Source of material, inferior mine ore, percentage of metal in dry ore, 71.5, specific gravity, 6.64. Source of material, titaniferous stream ore, percentage of metal in dry ore, 67.0, specific gravity, 6.39. Source of material, mine ore with wolfram, percentage of metal in dry ore 64.5, specific gravity 6.67. Source of material, ore from stream works, percentage of metal in dry ore 58.5, specific gravity 5.99. It will be seen from these figures that black tin is a very variable substance, and that the specific gravity is largely influenced by the impurities. Hence it is only an indication of the percentage of metal when the same kind of ore is dealt with. As already pointed out, the object of vanning is to determine the proportion of black tin in the lode stuff. The relation between the actual content in oxide of tin and the produce got by vanning has been tested on several occasions, with results which show a fair degree of approximation. The following are some published results of assays of the same batch of ore. The vanning results were obtained by a Cornish vanner of recognised ability, and the wet assays by 2 London firms of the highest standing. Vanning results: average 91 pounds of black tin. Wet assay results: A 83.7 pounds of stannic oxide, B 79.7 pounds of stannic oxide. The vanner reported his black tin as containing 70% of tin. This will bring his result, if calculated as stannic oxide, to 80.9 pounds to the ton, which agrees with the others. According to our experience, the van assay agrees fairly well with the wet one, if the black tin is assumed to contain 92.5% of stannic oxide, SnO2. Vanners are as a rule skillful men and show remarkable dexterity in separating the black tin with the help of their apparatus, which consists simply of a shovel and a kiva of water. An account of the process is given below. But different vanners, all good men, will get different results working on material new to them. The black tin weighed by the vanner is supposed to correspond in quality with the black tin returned from the floors of the mine for which he is assaying, but this differs materially in different mines with the nature of the gangue. The process leaves too much to the judgment of the vanner. It is more than probable that in practice the returns from the dressing floors check the assayer, instead of, as should properly be the case, the assayer checking the returns. It is only when this last is done that any control is had over the system of dressing. A correct assay of this ore is a matter of some importance because of the high price of the metal. The method of assaying the black tin is a dry one, and consists of mixing it with culm and submitting it in a black lead crucible to the highest temperature of a wind furnace. The sample is taken wet as it arrives at the smelting house and is assayed direct. The product of the assay is examined, and a deduction of a considerable percentage is very properly made for impurities, since the assay really determines the percentage not merely of tin, but of the bodies present which are reducible at a white heat. The judgment as to how much is to be deducted is assisted partly by an examination of the metal got from the assay, and partly by the experience acquired in smelting similar ores. The produce, which is that of the impure tin, is stated in parts in 20. Thus, a produce of 14 is equivalent to 70%, or to 14 hundredweight per ton. Mechanical separation, vanning. This process, which has already been referred to, is carried out as follows. After sampling the ore in the ordinary way, a quantity, varying with its richness, is weighed out. Special weights are generally used. The standard weight, marked 200, weighs about an ounce. With poor ores, this quantity is taken for an assay, but with richer ores 100 or even 50 is sufficient. The unit of weight has no special name, but the parts in 200 are spoken of as the produce. Thus, if 200 of ore were taken and 9.5 of black tin were separated, the produce would be 9.5. Obviously, half the produce will give the percentage. The weighed portion of the ore is placed on the vanning shovel. The vanner stands in front of a tub of water, note, keeve, endnote, and allows 30 or 40 cc's of water to flow onto the ore. He then raises the shovel a little above the surface of the water and, holding it nearly horizontal, briskly rotates the water by imparting to the shovel a slight circular motion, passing into an elliptical one front to back. This causes the finer mud to be suspended in the liquid, which is then run off, leaving the body of the ore in the centre of the shovel. This is repeated until the water, after standing a moment, is fairly clear. About half as much water as before is brought on. Then, with a motion which is similar to the previous one but with a jerk added in one direction, the heavier minerals are thrown up and the stony matter brought back. The jerk is produced just as the wave of water is returning. The descending wave of water draws with it the bulkier and lighter particles of the ore, whilst the heavier matter lying on the bottom is scarcely affected by it. The jerky motion, however, carries it to the front of the shovel. The lighter stuff is washed off and the residue dried by holding the shovel over the furnace. It now corresponds more or less to the stuff which on the mine is sent to the calciner. It is swept from the shovel into a scoop and transferred to a hot crucible, in which it is calcined until free from sulphur. Some vanners calcine their samples before commencing to van. The calcined ore is shaken out of the crucible onto the shovel, rubbed up with a hammer, and washed, as at first, to get rid of the finer and lighter waste. The separating motions are again gone through, and the head of the best of the black tin is thrown well up on one side of the shovel, in the form of a crescent, so as to leave room on the shovel to work with the tailings. The quantity of water used is kept low to prevent this crop tin from being washed back again. The tailings are then crushed to free the tin from adherent oxide of iron, and again washed to throw up the remaining tin ore. As this tin is finely divided, it is more difficult to bring it up, so that a vigorous and rapid motion is required. The tailings are now washed off, and the whole of the black tin is brought into the centre of the shovel. It requires 2 or 3 washings more to free it from the waste it contains. Very small quantities of water are used. The purity of the black tin can be seen by its appearance on the shovel. The cleaned ore is dried as before, freed from particles of iron with the aid of a magnet, and weighed. The weighings are carried to 1/8 of the unit used. The following example illustrates the method of calculation adopted on the mine. A parcel of 1 ton 200 weight 3/4 of tin ore with a produce of 45, equal to 22.5%, contains 500 weight 0/4 12 pounds of black tin. This result is obtained as follows. Reader's note. The method of calculation has been omitted. End reader's note. Similarly, a parcel of 20 tons 10 hundredweight with a produce of 9.5 contains 19 hundredweight 1/4 25 pounds of black tin. For the following information, as well as for much of that already given about vanning, we are indebted to Captain Reynolds of Cook's Kitchen Mine. To have a complete set of tools for all vanning purposes, it will be necessary to get the following: a vanning shovel 14 inches long and 13 inches wide, weighing not over 2 3/4 pounds. It is made of hammered sheet iron of the shape shown in figure 57. Reader's note. From above, the shovel has a straight handle about 2.5 times the length of the blade, which is slightly longer than square, with the front edge rounded off into almost a semicircle. From the side, the blade of the shovel is scooped into a very shallow dish, and the handle is angled upwards at about 30 degrees with a slight convex curve. End reader's note. It must have a light wooden handle, preferably of deal, 3 feet long. A bruising hammer, weighing 2.5 pounds with a handle 1 foot long. A pair of tongs, furnace, 2.5 feet long, made of 1/2 inch round iron. And a set of ordinary clay crucibles for calcining. There ought to be 2 sets of scales and weights. The first should be confined to weighing the powdered tin stuff, and the second ought to be a much higher class one for weighing the black tin obtained. The furnace for roasting the sample should be 10 inches square and 12 inches deep, with the fire bars at the bottom 3/4 of an inch apart. The water box for vanning in should be at least 4 feet long, 2 feet 6 inches wide, and 8 inches deep. Dry methods. For the following description of the process adopted in Cornwall, we are indebted to Mr. A. K. Barnett, F.G.S., of Chyandur. Cornish method. Tin ore assay. The ore to be smelted or assayed should be concentrated to, say, not less than 50% of metallic tin. Though to obtain satisfactory results it should be brought nearer 70%, as with ore containing less than 40 to 50% of metal, there will be a considerable loss both in the assaying and in the smelting. If the ore to be operated on does not contain this quantity of metal, then the sample, if coarse, must be reduced to a fine state, the gangue being removed by vanning, and the ore saved for the fire assay. The method adopted for the determination of tin in the ore is as follows. About 2½ ounces Troy, note 1,200 grains or about 80 grams, end note, of the ore to be assayed is weighed out and mixed on a flat copper pan, shaped with a long lip, with 1/5 of its weight, 240 grains or 15.5 grams, of powdered culm, anthracite. The mixture of ore and culm is either transferred to a black lead crucible before the latter is put into the furnace, or, as some prefer, it is carefully swept into a crucible which has been embedded in the fire. Some assayers cover their pots with a flat cover placed loosely on, while others leave the mixture in the open pot. The furnace, which has been previously fired to a strong heat, is then covered, and the sample is subjected to a sharp fire for a period of from 12 to 20 minutes. No definite time can be stated, as besides the strength of the fire, the quality and condition of the ore and the impurities associated with it greatly affects the time required for the complete reduction of the ore. As soon as the mixture in the crucible has settled down to a uniform white heat, and any very slight ebullition which may have taken place has subsided, the crucible is gently shaken, removed from the fire, note the culm ash or slag which covers the metal being carefully drawn aside with an iron scraper, end note, and the metal is poured quickly into an iron ingot mould, which is usually placed on a copper pan to save the culm slag and the adherent metal which comes out with it. The crucible is then carefully scraped, and the scrapings, together with the contents of the mould and pan, are transferred to a mortar. There the ingot of tin is freed from slag and then taken to the scales. The rest, after being finely powdered, is passed through a sieve. The flattened particles of tin which remain on the sieve are weighed with the ingot, the lump as it is called, while the siftings are vanned on a shovel, and, the slag being washed off, the fine tin is collected, dried, and weighed with the rest. The whole gives the produce or percentage of metal in the ore. The results of the assays are expressed in hundredweights of metal in the ton of ore. The percentage is rarely given, and never used in Cornwall. Thus, 13½ produce would mean that the assay yielded results at the rate of 13½ hundredweights of metal for 1 ton of the ore. Some assayers use a little powdered fluorspar to assist the fusion of refractory slags. A small quantity of borax will also occasionally be of service for ores containing silica in excess of any iron that may be present. The borax renders the slag more fusible and assists the formation of a larger lump with less fine tin in the slag than would be obtained by the use of culm alone. The quantity and the percentage of pure tin in the metal will vary considerably according to the impurities that are associated with the ore to be assayed. The crude lump is then remelted in a small iron ladle at as low a temperature as possible, and the fused metal is poured into a shallow trench about 4 inches long by 3/4 of an inch wide, cut in a block of white marble. The metal will be silvery white if the temperature employed be correct. If too hot, the surface will show a yellow, red, or blue colour, according to the heat employed. In such case, the metal should be remelted at a lower temperature. If the metal on cooling remains perfectly clear and bright, then it may be assumed that the tin is of good quality and commercially pure. A crystallized or frosted appearance of the metal indicates the presence of some alloy, say of iron, copper, zinc, lead, antimony, etc. The assayer who has had much practice can readily distinguish the metal or metals that are associated with the ore by noting the appearance of the tin on cooling, and can fairly judge the quantity of impurity present by the amount of the crystallization or stain. Whilst the foregoing method of assaying cannot lay claim to scientific accuracy, it is by no means so imperfect as some writers would have us believe, who state that a loss of 5 to 10% arises in the operation. It is certainly the most ready and expeditious mode of determining the commercial value of a parcel of tin ore, which, after all, is the main object of all assaying operations. The difficulty which beginners find in obtaining satisfactory results, and any loss of metal which those not accustomed to the process may incur, will invariably occur in the vanning of the powdered slag for the fine tin, the rest of the operations being easy of execution and requiring only the ordinary care necessary for all metallurgical work. There is no doubt that if low percentage ores containing silica are assayed in this manner, low results are obtained, as it is impossible to reduce the whole of the tin in the presence of free silica. With this class of ores, care should be taken to remove some of the silica by preliminary vanning, or some flux should be added which will combine with the silica and so prevent its entering into combination with the tin. Low quality tin ores containing iron, copper, lead, zinc, antimony, etc., combined with arsenic, sulphur or oxygen, will give very much higher results than the actual percentage of tin in the sample. The other metals, being readily reduced in the presence of tin, alloy with it, and give a hard lump difficult to fuse in the iron ladle. Where the quantity of foreign metals is large, the metal can only be melted to a stiff, pasty mass, so that in determining the value of a ton of tin ore, or even reporting on the percentage of tin it contains, not only must the weight of the assay be the basis for calculation, but the quality and character of the metal obtained must also be considered. Thus, 2 ores of tin might be assayed, both yielding a similar produce, say 13.5, note 67.5%, end note, and yet one might contain 5% less tin than the other. If it be required to obtain the pure metal from tin ores containing the ores of other metals associated with them, the latter must be removed by digesting in strong hydrochloric acid and washing. The assay may then be conducted in the usual way, and a fairly pure lump will be obtained. If wolfram be present in any appreciable quantity in the ore, it considerably reduces the proportion of lump, and at the same time it increases the fine tin, or prillion as it is termed, in the assay. This may be got rid of by boiling in aqua regia and dissolving out the tungstic acid, which has been liberated by means of ammonia. It will be seen that this method of assaying tin has its advantages and its drawbacks. It is quickly performed. With ores of good quality it gives results not to be excelled by any other process, and it gives the smelter the actual alloy and quality of metal he may expect to get in the smelting of the ore, which no other mode of assaying will do. Against which may be set the skill required to obtain accurate results with the vanning shovel, the loss of metal in poor ores containing an excess of silica, and the high results from ores containing a large quantity of metallic impurities. Cyanide method. Weigh up 20 grams of the ore and dry it on a scoop over the Bunsen flame. When dry, weigh and calculate the percentage of water from the loss in weight. Transfer the dried ore to an evaporating dish and cover with 30 cc of hydrochloric acid. Boil for 10 or 12 minutes, and then add 5 cc of nitric acid and boil again. Dilute with water and filter. Transfer the filter and its contents to an E. Battersea crucible and calcine it for a few minutes. Cool and weigh the residue. The loss equals the oxides soluble in acid. Transfer the residue to the crucible and mix it with its own weight of cyanide of potassium. Add a similar amount of cyanide as a cover. Place in the furnace, and when the charge has attained the temperature of the furnace, note in from 3 to 6 minutes, end note, remove it at once. Tap the pot vigorously several times, and then pour its contents quietly into a mould. Dissolve the slag in water, clean, dry, and weigh the button of tin. Wet methods. Detection. Tin ore is detected by its insolubility in acids, high specific gravity, and characteristic appearance in water. The powder is separated from the lighter gangue by washing. It is fused in a Berlin crucible with 5 times its weight of potassic cyanide at a moderately high temperature in a muffle or over the blowpipe. The slag is washed off with water, and the metallic buttons or residue treated with hydrochloric acid, not aqua regia. for some time. One portion of the solution strikes a purple colour with chloride of gold. Another portion gives a white or grey precipitate, or cloudiness, with mercuric chloride. These reactions are characteristic of tin as stannous chloride. Metallic tin, treated with nitric acid, becomes converted into a white insoluble powder, metastannic acid. Aqua regia dissolves tin readily, forming stannic chloride, and in this solution the metal is detected by precipitation with sulphuretted hydrogen, which gives a yellow precipitate. Tin in solution as stannic or stannous chloride is precipitated as metal by means of zinc. The fact that tin forms two well-defined series of compounds is taken advantage of in assaying, just as in the case of iron, by determining how much of an oxidizing agent is required to convert it from the stannous into the stannic state. For example, on the addition of a solution of permanganate of potash to a solution of stannous chloride, the oxidation goes on rapidly and the finishing point is sharp and distinct. But acid solutions of stannous chloride quickly take up oxygen from that dissolved in the water used and from the air. Unfortunately, there is no obvious sign that such oxidation has taken place, except that, fatal to the assay, a smaller volume of the permanganate is required. Great care is required with such solutions, both before and during titration. The addition of an excess of ferric chloride to the stannous solution, as soon as the whole of the tin has been dissolved, will lessen this liability to oxidation. Separation. If the tin is present in an alloy, the substance is boiled in an evaporating dish with dilute nitric acid until the whole of the material is attacked. Evaporate nearly to dryness, dilute, boil for a few minutes, and filter off the white insoluble residue. Under certain circumstances, this residue will be nearly free from other metals, in which case it is ignited and weighed. If not known to be pure, it must be ignited, reduced in a current of hydrogen, and treated as subsequently described. When the tin is present as insoluble oxide in an ore, the substance is finely powdered, and from 1 to 5 grams of it, according to its richness, boiled with 30 c.c. of hydrochloric acid in an evaporating dish, till the oxide of iron is seen to be dissolved. Then add 1 c.c. of nitric acid, or more if much pyrites, etc. is present, and continue the boiling till these are decomposed. Dilute and filter off, washing first with dilute acid and afterwards with a little dilute ammonia. Dry, ignite, and place in a combustion tube, together with the filter ash, and heat to redness for about 30 minutes in a current of dried hydrogen. The oxide of tin is placed in a porcelain boat, figure 58, which is then introduced into a piece of combustion tube. Reader's note: figure 58 shows a long, shallow porcelain trough with a circular handling loop at one end. End reader's note. The latter, wrapped in a piece of wire gauze, is supported on a couple of iron rings and heated by 1 or 2 Bunsen burners in a furnace fitted up with loose fire brick tiles, as shown in figure 59. Reader's note: figure 59 shows a base of fire bricks with fire tiles leaning against each other along its top surface to make a triangular passage. Within that passage, the length of combustion tube is resting on 2 supports made of iron wire. There are 2 Bunsen burners under the centre of the combustion tube. End reader's note. When the reduction is complete, the tube is allowed to cool. The boat is removed and the tin dissolved. Add a rod of zinc to the freely acid hot solution, and in a few minutes decant through a filter and wash with water, after having removed the zinc. Wash the precipitated metal back into the beaker and dissolve in 10 c.c. of dilute nitric acid. Evaporate off the excess of acid, dilute, boil and filter. Wash, dry, ignite strongly in a porcelain crucible and weigh. In the absence of antimony, the above separation works very well, but if this metal is present in quantity, the metals precipitated on the zinc must be covered with hydrochloric acid and treated with a few drops of nitric. It is then warmed with iron wire until no more of the latter dissolves. The antimony is precipitated as metal, and the tin remains in solution as stannous chloride. The antimony is filtered off and may be washed with alcohol and weighed, whilst the tin in the filtrate is precipitated with zinc and treated as already described. The end of section 29. Section 30 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 12. Tin, Tungsten, Titanium. Part 2. Tin. Gravimetric method. If the tin is not already in the metallic state, it is reduced to this condition by the method given. Note: precipitation by zinc. End note. Treat the finely divided metal, washed free from chlorides, in a 4-inch evaporating dish with 10 cc of dilute nitric acid. Cover with a clock glass and apply a gentle heat until the precipitate appears, of a white colour, and the metal is completely attacked. Evaporate nearly to dryness on a water bath, then add 50 cc of water, heat to boiling, and filter. Wash with hot water, dry, transfer to a weighed porcelain crucible, add the filter ash, ignite strongly, and weigh. The precipitate after ignition is stannic oxide, SnO2. It is a yellowish-white powder, darker whilst hot, insoluble in acids, and contains 78.67% of tin. Cold dilute nitric acid dissolves tin to a clear solution, which becomes a white enamel-like jelly on heating. This, filtered off, washed and dried, forms an opal-like substance, which is converted on ignition into stannic oxide with evolution of nitrous fumes. Stannic oxide, when ignited with chlorides, is more or less completely converted into stannic chloride, which volatilizes. The presence of chlorides during the evaporation with nitric acid causes a similar loss. Determination of tin in an alloy, bronze. Take 2 grams and attack with 20 cc of dilute nitric acid in a covered beaker with the aid of heat. Boil till the bulk is reduced by 1/2. Dilute with 50 cc of water, allow to settle for a few minutes, and filter. Wash well first with water acidulated with a little nitric acid, and afterwards with water. Dry, ignite, and weigh as stannic oxide. Determination of tin in tin ore. Treat 5 grams of the dried and finely powdered ore with 30 cc of hydrochloric acid in a 4-inch evaporating dish. After the soluble oxides have been dissolved, add 1 or 2 cc of nitric acid. Boil off nitrous fumes, dilute and filter. Dry the filter, transfer the cleaned ore to a piece of combustion tube 10 or 12 inches long and narrowed at one end. Pass a current of hydrogen through the tube and heat to redness for 30 minutes. Cool whilst the gas is still passing. Dissolve in 20 cc of dilute hydrochloric acid and keep the solution tinted with permanganate of potassium. When the colour of the permanganate becomes permanent, dilute to a bulk of 50 cc with water, filter and wash. Heat. Add a rod of zinc weighing about 3 grams. Allow to stand for a few minutes. Decant through a filter and wash, removing the remaining zinc and returning the tin to the beaker. Treat with 5 cc of dilute nitric acid, boil for some time, take up with water, filter, wash, dry, ignite, and weigh as stannic oxide. Volumetric method. Titration with solution of permanganate of potassium. This titration may be made either directly on the solution of stannous chloride, prepared by dissolving the precipitated metal in hydrochloric acid, or indirectly on a solution of ferrous chloride, produced by the reducing action of the precipitated metal on ferric chloride. The standard solution of permanganate of potassium is made by dissolving 5.356 grams of the salt in water and diluting to 1 litre. 100 cc are equivalent to 1.00 gram of tin. The precipitated tin is transferred to a flask and dissolved in 10 cc hydrochloric acid with the aid of heat and in an atmosphere of carbonic acid. The acid and metal are placed in the flask, which is then filled with the gas and stopped with a cork provided with a rubber valve. When solution is complete, the flask is again filled with carbonic acid. 50 cc of water, freed from air and saturated with carbonic acid, are then added. This water is made by adding a gram of bicarbonate of soda and 2 cc of hydrochloric acid to 100 cc of water. The effervescence sweeps out the dissolved oxygen. The permanganate of potassium solution is then run in from a stopcock burette in the usual way until a faint pink tinge is obtained. The following experiments show the effect of variations in the conditions of the assay. A solution of stannous chloride equivalent in strength to the permanganate was made by dissolving 19.06 grams of the crystallized salt, note SnCl2.2H2O, end note, in 50 cc of water and 10 cc of hydrochloric acid, and diluting to 1 litre with water freed from dissolved oxygen. 100 cc contain 1 gram of tin. In the first experiments, tap water was used and no precautions were taken for excluding air. Except when otherwise stated, 20 cc of the stannous chloride were used in each experiment, with 10 cc of hydrochloric acid, and were diluted to 100 cc with water before titration. Effect of varying hydrochloric acid. Acid added 1.0 cc. Permanganate required 18.8 cc. Acid added 10.0 cc. Permanganate required 18.9 cc. Acid added 20.0 cc. Permanganate required 18.8 cc. Acid added 50.0 cc. Permanganate required 18.8 cc. The only effect of the increase in quantity of acid was to give the brown of perchloride of manganese instead of the pink of permanganic acid to mark the finishing point. Effect of varying temperature. Temperature 15 degrees centigrade. Permanganate required 18.8 cc. Temperature 50 degrees centigrade. Permanganate required 18.7 cc. Temperature 70 degrees centigrade. Permanganate required 18.6 cc. Temperature 100 degrees centigrade. Permanganate required 18.4 cc. Rate of atmospheric oxidation. Solutions ready for titration were exposed to air at the ordinary temperature for varying lengths of time and then titrated. Time exposed 0 minutes. Permanganate required 18.8 cc. Time exposed 5 minutes. Permanganate required 18.8 cc. Time exposed 10 minutes. Permanganate required 18.8 cc. Time exposed 20 minutes. Permanganate required 18.8 cc. Time exposed 60 minutes. Permanganate required 18.6 cc. It is best to titrate at once, although the loss by oxidation is only small after 1 hour's exposure. Effect of varying tin. Stannous chloride added 1.0 cc. Permanganate required 0.7 cc. Stannous chloride added 10.0 cc. Permanganate required 8.8 cc. Stannous chloride added 20.0 cc. Permanganate required 18.0 cc. Stannous chloride added 50.0 cc. Permanganate required 47.4 cc. Stannous chloride added 100.0 cc. Permanganate required 95.4 cc. Effect of varying bulk. Bulk 50.0 cc. Permanganate required 19.0 cc. Bulk 100.0 cc. Permanganate required 18.3 cc. Bulk 200.0 cc. Permanganate required 17.4 cc. Bulk 500.0 cc. Permanganate required 15.1 cc. The two last series show an interference, which is due to the oxygen dissolved in the water, as may be seen from the following similar experiments, which were, however, performed with water freed from oxygen, and in which the titrations were effected in an atmosphere of carbonic acid. Effect of varying tin. A new solution of stannous chloride was used. Stannous chloride added 1.0 cc. Permanganate required 1.0 cc. Stannous chloride added 10.0 cc. permanganate required 10.0 cc. Stannous chloride added 20.0 cc. Permanganate required 19.8 cc. Stannous chloride added 50.0 cc. Permanganate required 49.6 cc. Stannous chloride added 100.0 cc. Permanganate required 99.3 cc. Effect of varying bulk. Bulk 30.0 cc. Permanganate required 19.8 cc. Bulk 50.0 cc. Permanganate required 19.8 cc. Bulk 100.0 cc. Permanganate required 19.8 cc. Bulk 200.0 cc. Permanganate required 19.8 cc. Bulk 500.0 cc. Permanganate required 19.8 cc. It will be seen that in working under these conditions the results are proportional and the method satisfactory. Examination of tin phosphide. Note: phosphor tin. End note. This substance is used in the manufacture of phosphor bronze and similar alloys. It is a crystalline, imperfectly malleable, metallic substance. It is soluble in hydrochloric acid with effervescence. Phosphorated hydrogen, which inflames on the addition of a drop or two of nitric acid, being evolved. It is attacked by nitric acid, yielding a white powder of stannic phosphate. This is not easily decomposed by ammonium sulphide or readily soluble in hydrochloric acid. Phosphor tin is made up only of tin and phosphorus. For the estimation, weigh up 1 gram, place in a weighed Berlin dish, and cover with 10 cc of nitric acid and 3 or 4 cc of water. Let the reaction proceed, under a clock glass, on the water bath till complete. Remove the glass, evaporate to dryness and ignite, at first gently over a Bunsen burner and afterwards in the muffle at a red heat. Cool in the desiccator and weigh as quickly as possible when cold. The substance contains the tin as stannic oxide, SnO2, and the phosphorus as phosphoric oxide, P2O5. The increase in weight on the gram of substance taken gives the weight of the oxygen taken up by the phosphorus and tin, and since 1 gram of tin takes up only 0.271 gram of oxygen, and 1 gram of phosphorus takes up 1.29 gram, the proportion of tin to phosphorus can be calculated from the increase in weight. For example, 1 gram of a sample gave 1.3410 gram of mixed oxides, which is 0.070 gram in excess of that which would be got with pure tin. If the substance was all phosphorus, the excess would be 1.0190 gram. Consequently, the proportion of phosphorus in the substance is 0.070 divided by 1.019, or 6.87%. The tin is calculated by difference, 93.13%. Another method of separating and determining the phosphorus is as follows. Take 1 gram of the substance and add to it 15 cc of hot aqua regia. Boil till dissolved, dilute, and precipitate the tin with sulphuretted hydrogen. To the filtrate add ammonia and magnesia mixture. Filter, wash the precipitate with dilute ammonia, dry, ignite, and weigh as magnesic pyrophosphate. Calculate the phosphorus and take the tin by difference. A sample of phosphor tin gave tin 93.1% by difference, phosphorus 6.9%, total 100.0. Tin arsenide. This is met with in tin smelting. It closely resembles the phosphide, but the crystals have a duller grey appearance. It contains simply tin and arsenic. The determination is made by treating 1 gram of the substance with nitric acid and weighing the mixed oxides of tin and arsenic in the same manner as in the case of the phosphide. 1 gram of arsenic will give 1.533 gram of arsenic oxide, As2O5. Consequently, the excess of weight of the mixed oxides over 1.271 gram must be divided by 0.262. The result multiplied by 100 gives the percentage of arsenic. In consequence of the higher atomic weight of arsenic, the results by this method are not so close as with the phosphide. Each milligram of excess weight over 1.271 represents 0.38% of arsenic, As, Both in this and in the corresponding phosphide determination, care must be taken to avoid absorption of moisture by allowing the oxides to cool in a desiccator and weighing quickly. The percentage of arsenic is better determined as follows. Weigh up 1 gram of the substance, dissolve in aqua regia, dilute and pass sulphuretted hydrogen. Render alkaline with ammonia and add ammonium sulphide till the precipitate is dissolved. Add magnesia mixture. Filter off the precipitate, wash with dilute ammonia, ignite with a few drops of nitric acid, and weigh as magnesic pyrarsenate. Calculate the arsenic and take the tin by difference. A sample treated in this way gave tin 96.8% by difference, arsenic 3.2%, total 100.0. Examination of black tin. Dry the ore and reduce it to a fine powder. Weigh up 2 grams and boil with 20 cc of hydrochloric acid and 2 cc of nitric for 10 or 15 minutes. Filter and reserve the filtrate. Tungstic acid. Digest the residue with about 50 cc of water and a few cc of dilute ammonia for a few minutes, and filter. Collect the filtrate in a weighed porcelain dish, evaporate to dryness, ignite, and weigh as tungstic acid, WO3. Stannic oxide. Dry, ignite, and weigh the insoluble residue. Transfer to a porcelain boat and reduce in a current of hydrogen at a red heat for half an hour. Allow to cool whilst the hydrogen is still passing. Transfer the boat to a beaker and dissolve up the tin in 10 cc of hydrochloric acid and a cc or so of nitric. Wash out the combustion tube with some acid and add the washing to the contents of the beaker. Warm gently, dilute with water and filter. Collect, dry, ignite and weigh the insoluble residue. Through the filtrate, pass a rapid current of sulphuretted hydrogen, allow to settle and filter. Wash the precipitate with hot water, dry, calcine gently. Ignite with ammonium carbonate and weigh as stannic oxide, SnO2. The insoluble residue will in most cases retain some tin. Fuse it with fusion mixture, take up with hydrochloric acid, filter, pass sulphuretted hydrogen through the filtrate, collect and wash the sulphide of tin. Ignite and weigh as stannic oxide, and add it to that previously obtained. Copper. Pass sulphuretted hydrogen through the acid filtrate obtained in the first cleaning of the ore. Collect the precipitate, and wash first with soda solution and then with hot water. Dry, ignite, and weigh as cupric oxide, CuO. Mix the filtrate with that from the main portion of the sulphide of tin. Ferric oxide. Boil off the sulphuretted hydrogen from the mixed filtrates and peroxidize with nitric acid. Add ammonia in slight excess. Boil, filter, dry, ignite, and weigh the precipitate as ferric oxide. This will be practically pure, but the iron in it must be determined by dissolving and titrating. The filtrate from the iron may contain zinc, lime, and magnesia, but rarely in quantities sufficient to be determined. Silica, etc. The silica may be calculated from the weight of the residue insoluble in acid after the reduction of the tin in hydrogen, by deducting from it the weight of the oxide of tin subsequently found. Or it may be determined as follows. The insoluble portion is fused with fusion mixture and taken up with hydrochloric acid, as already described. On filtering, the filter will retain a portion of the silica. The rest is recovered after the removal of the stannous sulphide by evaporating to dryness, taking up with hydrochloric acid, and filtering through the same filter. It is washed, dried, ignited, and weighed as silica. The filtrate from the silica is boiled with a little nitric acid and precipitated with ammonia. The precipitate is collected, washed, ignited, and weighed as ferric oxide and alumina. Note, but it frequently contains oxide of titanium. End note. When the last is present, it is determined by fusing with bisulfate of potash and extracting with cold water. The solution is nearly neutralized with ammonia, charged with sulphurous acid, and boiled. The precipitate is collected, washed, dried, ignited, and weighed as oxide of titanium, TiO2. The difference between this weight and that of the combined oxides gives the ferric oxide and alumina. The filtrate from the mixed oxides is examined for lime and magnesia. Sulphur. Rub up 5 grams of the ore with 5 grams of nitre. Transfer to a porcelain dish and fuse over a Bunsen burner for 15 minutes. When cold, extract with water and determine the sulphur volumetrically with standard barium chloride. The sulphur may be present as sulphide or sulphate. Arsenic. Take 5 grams and evaporate with nitric acid. Dilute, add ammonia, pass sulphuretted hydrogen and filter. To the filtrate add magnesia mixture. Collect the precipitate, ignite with nitric acid and weigh as magnesic pyrarsenate. The following may be taken as an example of the composition of an impure black tin. Tungstic acid 1.8%, stannic oxide 79.0, silica 2.6, titanic oxide 0.8, copper oxide 0.9, ferric oxide 13.4, sulphur 0.4, arsenic 0.3, total 99.2. Examination of hardhead. In the smelting of tin ores, a quantity of spicer known as hardhead is produced. It is essentially an arsenide of iron carrying a considerable quantity of tin. Much of this last is present in the form of small buttons of metal distributed through the mass. The buttons can be seen on careful inspection and become evident on powdering. In assaying the substance, a variation in the usual method of sampling is required because of the quantity of metal present which cannot be powdered. After powdering as finely as possible, the coarse particles are sifted off and weighed. The weight of the powder is also taken. The method of working is best illustrated by an example. A sample of hardhead weighed 155.1 grams and gave 21.0 grams of coarse particles, equivalent to 13.5% of the whole. The fine portion weighed 134 grams, which is equivalent to 86.5%. 13.5 grams of the coarse material were dissolved in aqua regia and diluted with water to 1 litre. 10 cc's of this contain 0.135 gram of the metallic portion, which is the amount contained in 1 gram of the original hardhead. If in a determination 1 gram of the substance is wanted, weigh up 0.865 gram of the powdered portion and add to it 10 cc's of the solution. It will be seen that these together make up 1 gram of the original sample. The solution of the metallic portion must be saved until the analysis is finished. Tin and copper. Weigh up the portion of the powdered stuff equivalent to 1 gram of the sample. Transfer to a flask and cover with 10 cc's of the solution of the metallic portion and 10 cc's of aqua regia. Boil gently till oxidation is complete and the nitric acid, for the greater part, driven off. Dilute to 100 cc's with water and pass sulphuretted hydrogen for some time. Filter, wash with hot water and rinse through the funnel back into the flask. Digest with yellow sodium sulphide until only light, flocculent black precipitate is left. Filter this off. Wash with hot water, dry, calcine, treat with a little nitric acid, ignite, and weigh as copper oxide, CuO. The weight multiplied by 0.7983 gives the weight of copper. The filtrate containing the tin is rendered acid with hydrochloric acid and filtered. The precipitate is rinsed into a half-pint beaker covered with 20 cc's of hydrochloric acid and boiled down to about 20 cc's. The solution is filtered off from the sulphur and sulphide of arsenic, which, after washing with hot water, is transferred to a flask labelled arsenic. A strip of sheet zinc, 2 inches by 1 inch, is placed in the solution. The evolution of hydrogen should be brisk. In 5 or 10 minutes, decant off a few cc's of the liquid and test with sulphuretted hydrogen for tin. If no yellowish precipitate is formed, decant off the rest of the liquid and wash the precipitated metal with hot water 2 or 3 times by decantation. The metal should be in a lump. If there are any floating particles, they must be made to sink by compression with a glass rod. Transfer the washed metal to an evaporating dish 3 or 4 inches across and cover with a few cc's of hot water. Add nitric acid drop by drop till the tin is completely attacked. Evaporate nearly to dryness and add a drop or two more of nitric acid and 20 cc's of water. Boil and filter. Wash with hot water, dry, ignite, and weigh as stannic oxide, SnO2. Calculate to metallic tin by multiplying by 0.7867. Footnote: this will give almost the whole of the tin. A further portion will be got in subsequent work and must be added to this result. End footnote. The filtrate from the first treatment with sulphuretted hydrogen will probably no longer smell of the gas. Warm and pass the gas for a few minutes longer. Filter off any precipitate of sulphide of arsenic and transfer it to the flask for arsenic. Boil the filtrate, ignoring any signs of a further precipitation of arsenic, with a few cc's of nitric acid, and separate the iron as basic acetate. Wash. Reserve the filtrate for cobalt. Iron. Rinse back the basic acetate, precipitate into the flask, add ammonia, dilute with water to about 100 cc's, and pass sulphuretted hydrogen for a few minutes. Filter and wash with hot water. Collect the filtrate in the flask labelled arsenic. Boil the precipitate with dilute sulphuric acid, filter, and titrate the filtrate with the permanganate of potassium solution after boiling off the sulphuretted hydrogen. Report the result as iron. The sulphuric acid will not affect complete solution. A light black residue will remain, chiefly sulphur. This must be rinsed into the filtrate from the acetate separation. It contains cobalt. Cobalt. The filtrate from the acetate separation will have a pink colour. Render it ammoniacal and pass sulphuretted hydrogen. Collect the precipitate on a filter, dry, and ignite. Dissolve in hydrochloric acid and evaporate nearly to dryness with an excess of nitric acid. Dilute with 10 or 20 cc's of water and add potash solution in slight excess. Add acetic acid until the solution is acid and the precipitate is quite dissolved. Add 20 or 30 cc's of a strong solution of potassium nitrite and determine the cobalt as described on pages 254-256. Reader's note. In the chapter on determination of nickel. End reader's note. Boil the filtrate from the cobalt, precipitate with hydrochloric acid, render ammoniacal, and test for zinc, nickel, and manganese. The remainder of the tin will be contained in the flask labelled arsenic. Acidify with hydrochloric acid and filter. Rinse into a beaker and evaporate to a small bulk with 10 cc's of nitric acid. Dilute and filter. Dry the precipitate, consisting of stannic arsenate. Note: 2SnO2.As2O5. End note. Ignite and weigh. Calculate the tin it contains by multiplying by 0.4453 and add to that already found. Arsenic. This is determined in a separate portion. Weigh up a portion of the powder equivalent to 1 gram of the hardhead. Place in a pint flask and boil with 10 cc's of nitric acid. When action has ceased, add 10 cc's of the solution of the metallic portion, and then hydrochloric acid, a few drops at a time, till solution is complete. Warm gently in dissolving, but do not boil. Dilute to about 100 cc's, render alkaline with ammonia, and add 20 cc's of yellow ammonium sulphide. Digest at a gentle heat for about 30 minutes, filter and wash. Add 50 cc's of magnesia mixture, shake well, allow to stand for an hour, filter and wash with dilute ammonia. The precipitate is dissolved and then titrated with uranium acetate, or it is evaporated with nitric acid, ignited and weighed as pyrarsenate of magnesia. Calculate the result to arsenic, As. Sulphur. Weigh up a portion of the powder equivalent to 2 or 3 grams of the hardhead. Rub up in a mortar with 5 grams of nitre and fuse in a porcelain dish for 10 minutes. Extract with water, add 20 or 30 cc, as the case may be, of the solution of the metallics. Add 10 grams of sodic acetate and ferric chloride until the precipitate turns brown. Dilute with water to half a litre, boil, and titrate with standard baric chloride, as described under sulphur. Report as sulphur. A sample of hardhead examined in this way gave sulphur 3.00%, arsenic 27.10, tin 22.2, copper 1.64, iron 43.2, cobalt 2.6, total 99.74. Examination of tin slags. In tin smelting works, the term slag is applied to the unfused portion of the charge. It is made up of unburnt anthracite and small lumps of slag proper, together with some buttons of metallic tin. This is rarely, if ever, assayed. The slag proper, or as it is generally called, glass, is a silicate of iron, alumina, and lime, containing from 3 to 7% of tin. It is thus examined. The sample, after bruising on an iron plate, is reduced to a very fine powder by grinding in an agate mortar. In this state it is, in most cases, readily decomposed by hydrochloric acid. Determination of tin. Where the percentage of tin only is required, take 2 grams of the powdered slag and well mix with it 20 cc of hydrochloric acid and heat to boiling. Add 1 cc of nitric acid, allow to stand for 15 minutes, dilute with water and filter. Pass a rapid current of sulphuretted hydrogen for some time, allow to settle and filter. The precipitate, after washing with hot water, is dried and gently calcined until the greater part of the sulphur is burnt off. It is then strongly ignited in the muffle or over the blowpipe with the addition of a small lump of ammonic carbonate. The residue is weighed as stannic oxide, SnO2, and is calculated to metallic tin by multiplying by 0.787. The percentage on the slag is calculated in the usual way. The tin is always best determined in the examination of slags by a separate assay carried out in this way. The determination of the other constituents is thus made. Silica. Take 2 grams of the powdered slag and cover them in a small evaporating dish with 20 cc of hydrochloric acid. Mix well by stirring with a glass rod and evaporate to dryness. If, as is generally the case, tungsten is present, the solution will be blue. Take up with 20 cc of hydrochloric acid, add 1 cc of nitric acid, and reduce by boiling to about half the bulk. Add about 20 cc of water, boil and filter. Wash the residue with hot dilute hydrochloric acid. It consists of silica with the tungstic acid. Wash it back into the dish and digest with 5 or 10 cc of a cold solution of ammonic carbonate. Filter and collect the filtrate and washings in a weighed porcelain dish. Dry the residue, ignite strongly, and weigh as silica, SiO2. In certain exceptional cases this may contain some unaltered cassiterite, which is easily recognized by its appearance. Tungsten. The ammonic carbonate filtrate from the silica is evaporated to dryness, ignited strongly over the blowpipe, and weighed. The residue is tungstic acid, WO3. The tungsten may be conveniently reported in this form, although it is probably present as a lower oxide. Tin. The acid filtrate from the silica and tungstic acid is treated with sulphuretted hydrogen. The sulphide of tin is filtered off. Since the percentage of tin has been already determined, this precipitate may be neglected, or may be treated in the same way as the previous one, so as to check the result. Since some stannic chloride will have been lost in the evaporation, a low result may be expected. The tin should be reported as stannous oxide, and is calculated by multiplying the percentage of tin by 1.136. The filtrate from the tin is boiled rapidly down to remove sulphuretted hydrogen, and then peroxidized with 1 or 2 cc of nitric acid. It is cooled, transferred to a graduated flask, and diluted with water to 200 cc. Ferrous oxide and alumina. Half the filtrate from the tin, that is 100 cc, is taken, nearly neutralized with soda, and treated with sodium acetate. The basic acetate precipitate obtained on boiling is filtered off and washed. Reserve the filtrate. The precipitate is dissolved off the filter with hot dilute hydrochloric acid, and the solution thus formed is treated with a slight excess of ammonia and boiled. The precipitate is filtered off, washed with hot water, dried, ignited, and weighed as mixed ferric oxide and alumina. The ignited precipitate is then dissolved with sulphuric and hydrochloric acids, and the iron determined in the solution by titration with the solution of stannous chloride. The iron found is calculated to and reported as ferrous oxide, FeO. Note, factor equals 1.286, end note. To find the alumina, which is best estimated by difference, multiply the iron by 1.428 to get the weight of ferric oxide, and deduct this from the weight of alumina and ferric oxide found. This, of course, gives the alumina. A direct determination may be made by removing the tin from the titrated solution with sulphuretted hydrogen, filtering, nearly neutralizing with ammonia, and boiling with a few grams of hyposulfite of soda. The precipitate, filtered, washed, and ignited, is the alumina, which is weighed. The direct determination gives a slightly low result. Oxides of zinc and manganese. These are determined in the filtrate from the basic acetate precipitate by rendering alkaline with ammonia and passing a current of sulphuretted hydrogen. Generally, a small but decided precipitate of alumina comes down, together with sulphides of any zinc or manganese which is present. The precipitate is allowed to settle, dried, ignited, and weighed. The metals are separately determined in it, and the residue is counted as alumina and added to that already found. The mixed precipitate amounts to from 1 to 2% of the sample. Lime. The filtrate from the last is treated with ammonic oxalate, boiled for a few minutes, allowed to settle, and filtered. The precipitate is washed with hot water, dried, ignited, and weighed as carbonate after gentle ignition, or as lime after strong ignition in the muffle. Magnesia. The filtrate from the lime is treated with sodic phosphate and ammonia. It is well mixed by stirring and allowed to stand overnight. The precipitate is washed with dilute ammonia, dried, ignited, and weighed as pyrophosphate. Soda and potash. These are determined in the remaining half of the filtrate from the tin. The solution is rendered ammoniacal with ammonia, and treated first with sulphuretted hydrogen and then with ammonium oxalate. The precipitate is filtered off and rejected. The filtrate is evaporated in a small porcelain dish over a Bunsen burner, or on the sand bath, and towards the close, or earlier if the evaporation is not proceeding well, nitric acid is added. The evaporation is carried to dryness, and the residue heated nearly to redness. The residue, which consists of magnesia with carbonates and chlorides of the alkalies, is extracted with water and filtered. The filtrate is evaporated with hydrochloric acid in a weighed platinum dish, ignited gently and weighed. This gives the weight of the mixed chlorides of sodium and potassium, which are then separated and determined as described under potash. It must be remembered when calculating the percentage that, with the exception of the silica, tungstic acid, and tin, the determinations have been made on 1 gram of the sample. The following analysis will illustrate the composition of such a slag. Tungstic acid 1.3%, silica 39.4%, stannous oxide 8.1%, ferrous oxide 26.2%, alumina 14.8%, oxide of manganese, traces, lime 7.9%, magnesia 0.5%, alkalis calculated as soda 1.7%, total 99.9%. The end of section 30. Section 31 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 12. Tin, Tungsten, Titanium, Part 3. Titanium. Titanium only occurs as a mineral in its oxidized state, or as titanic oxide, TiO2. It is a substance which has little commercial value, and is generally recognized as one of the rare bodies. Although in small quantities, it is widely disseminated. It occurs in granite, basalt, and other igneous rocks, in quantities up to as much as 1%. It is also met with in clays and iron ores, and in river sands, in which it is often associated with stream tin. The proper minerals of titanium are rutile, TiO2, titaniferous iron, titanate of iron, and sphene, titanate and silicate of lime. The oxide of titanium, like cassiterite and quartz, is undecomposed by hydrochloric or nitric acid, so that it is generally found in the residue insoluble in acids. The titanates, however, are attacked, and a portion of the titanium dissolves, so that it must be looked for in both the filtrate and residue. Oxide of titanium, in its native form or after ignition, may be made soluble by fusing the finely divided substance with fusion mixture in a platinum dish. The resulting titanate is dissolved out of the melt by cold hydrochloric acid. The method most commonly used is fusion with bisulfate of potash. This renders the oxide of titanium soluble in cold water. The process is as follows. The substance is extracted with hydrochloric and nitric acids, and the solution reserved for further treatment. The residue is dried, moistened with sulphuric acid, and evaporated once or twice to dryness with hydrofluoric acid. It is then fused with bisulfate of potash, and the melt extracted with cold water until all soluble matter is removed. The solution is filtered. The residue may consist of unremoved silica and oxides of tantalum, niobium, and perhaps chromium. On the prolonged boiling of the filtrate, the oxide of titanium and oxide of zirconium, if any, is precipitated. Any titanium dissolved by the first extraction with acids is recovered in the following way. Sulphuretted hydrogen is passed into the acid solution, and any precipitate that may be formed is filtered off. The filtrate is oxidized, and the iron, aluminium, and titanium are separated as basic acetates. Note C under iron. End note. The precipitate is dried and fused with bisulfate of potash. The melt is extracted with cold water, filtered if necessary, and the solution rendered first faintly alkaline with ammonia, then very slightly acid with sulphuric acid. 30 or 40 cc of a saturated solution of sulphurous acid is added, and the oxide of titanium precipitated by prolonged boiling. It is filtered off, added to the precipitate previously got, ignited with ammonic carbonate towards the end, and then weighed. Detection. Titanium is detected in an insoluble residue by fusing the residue for some time in a bead of microcosmic salt. In the reducing flame it gives a violet colour, which becomes reddish-brown if much iron is present. In the oxidizing flame it gives a colourless or whitish bead. It is best detected in acid solutions by the deep brown or iodine colour developed on adding hydroxyl. A solution of this can be prepared by pouring peroxide of barium, BaO2, diffused in water, into dilute hydrochloric acid a little at a time, and keeping the acid in excess. Separation. In the usual course of an analytical separation, the hydrate of titanium will be thrown down with ferric hydrate, etc., on the addition of ammonic chloride and ammonia. It is best separated from this precipitate by fusion with bisulfate of potash, as already described. but it must be remembered that the presence of much mineral acid prevents complete precipitation when the solution is boiled. Further, if phosphates are present, the precipitate will contain phosphoric oxide. It may be freed from this by fusion with sodium carbonate. A very good method of separating titanium from iron is to add tartaric acid and ammonia to the solution, and then precipitate the iron as sulfide with sulphuretted hydrogen. The filtrate contains the titanium, which is recovered by evaporating and igniting. It may be separated from zirconia by the action of sodium carbonate, which precipitates both, but when concentrated, redissolves the zirconia. The separation from large quantities of silica is best effected by evaporating with hydrofluoric acid, which volatilizes the silicon. But sulfuric acid must be present, otherwise some titanium also will be lost, as may be seen from the following experiments. Footnote: published by P. Holland in the Chemical News, volume 55, page 27, end footnote, in which oxide of titanium, note, pure, ignited, end note, was evaporated to dryness with a quantity of hydrofluoric acid known by experiment to be sufficient to volatilize 1 gram of silica. Without sulfuric acid, 0.0466 gram of titanic oxide left 0.0340 gram, showing a loss of about 25%. With sulfuric acid, the following results were obtained. Oxide taken, 0.030 grams, left after evaporation and ignition, 0.0340 gram. Oxide taken, 0.0414 gram, left 0.0413 gram. Oxide taken, 0.0520 gram, left 0.0520 gram. Oxide taken, 0.0352 gram, left 0.0352 gram. Gravimetric determination. The titanic hydrate thrown down by ammonia, or on boiling the solution from the bisulfate, is collected, washed, dried, ignited strongly with the addition of a little ammonic carbonate, and weighed. The substance is titanic oxide, TiO2, and is generally reported as such. It contains 60.98% of titanium. It should be white if pure, note Holland, end note, white, yellow or brown, note Fresenius, end note, or black, note tidy, end note. Volumetric method. A method has been proposed based on the reduction of titanic oxide by zinc in hydrochloric acid solutions to the sesquioxide. The reduction is marked by the development of a violet or green colour, the former with chlorides and the latter when fluorides are present. The quantity of titanium reduced is measured by titrating with permanganate of potassium solution. The water used must be free from dissolved oxygen. Tungsten and tungstates. Tungsten occurs in nature only in the oxidized state, or as tungstic acid, WO3, either free, as in wolframine, or combined with oxides of manganese and iron, as in wolfram, or with lime, as in scheelite. Wolfram occurs associated with tin ores, the value of which is considerably lowered. Both wolfram and scheelite are of considerable importance as a source of tungstic acid for the manufacture of sodium tungstate, which is used as a mordant and for some other purposes, and as a source of metallic tungsten, which is used in steel making. The tungsten minerals have a high specific gravity, 6 to 7.5. On treatment with hydrochloric acid or aqua regia, they are decomposed. The yellow tungstic acid separates and remains insoluble. Tungsten itself is insoluble in nitric acid or aqua regia, but is converted into tungstic acid, WO3, by prolonged and strong ignition in air. Alloys containing tungsten leave tungstic acid after treatment with nitric acid or aqua regia. Tungstic acid may be got into solution after fusion with alkalis or alkaline carbonates. This solution gives with hydrochloric acid a white precipitate of tungstic acid, which becomes yellow on boiling, but the separation is not complete. Fusion with bisulfate of potash gives a residue which does not dissolve in water, but is soluble in ammonic carbonate. For the assay of minerals containing tungsten, these reactions are only occasionally taken advantage of for testing or purifying the separated tungstic acid. Detection. The minerals are easily recognized by their physical characters, and the yellow tungstic acid, separated by boiling with acids, is the best test for its presence. This, after decanting and washing, immediately dissolves in a few drops of dilute ammonia. A solution of tungstate acidulated with hydrochloric acid becomes intensely blue on the addition of stannous chloride and warming. Fused in a bead of microcosmic salt, it gives a clear blue colour, reddish-brown if iron is also present, in the reducing flame, but is colourless in the oxidizing flame. Solution and separation. The decomposition and solution of natural tungstates is difficult to effect, owing to the separation of tungstic acid. The method of treatment is as follows. Boil the finely powdered substance with hydrochloric acid or aqua regia till it apparently ceases to be attacked. Dilute, filter, and wash with dilute hydrochloric acid. Cover with dilute ammonia and filter the solution, which contains ammonic tungstate, into an evaporating dish. Treat the residue again with acid, and again dissolve out the separated tungstic acid with ammonia, and repeat this operation until decomposition is complete. By this means there will be obtained 1. A solution containing tungstate of ammonia, 2. An insoluble residue with silicates and oxides of tin, niobium, tantalum, etc., and 3. An acid solution containing the soluble bases. The tungstate of ammonia requires simple evaporation on the water bath and gentle ignition, in order to cause the tungstic acid to be left in an almost pure state. Possibly it may carry a little silica. Gravimetric determination. The tungstic acid is dissolved and separated as ammonic tungstate, and after evaporation is gently ignited, the heat being increased towards the end. The residual tungstic acid is fixed, so that when the ammonia has been driven off, it may be strongly heated without loss. It is a dark yellow or brown powder whilst hot, which becomes a light yellow on cooling. If any reduction has taken place, it will be more or less greenish. It is weighed when cold, and is the trioxide or tungstic acid, WO3, which contains 79.31% of tungsten. After its weight has been taken, its purity is checked by fusing with hydric potassic sulphate, extracting with water, and treating the residue with ammonic carbonate. Any silica present will be left undissolved. It should be separated and weighed, and its weight deducted from that of the tungstic acid found. Determination of tungstic acid in wolfram. Take 2 grams of the finely powdered sample and boil with 50 c.c. of hydrochloric acid for half an hour, adding 5 c.c. of nitric acid towards the end. Allow to stand overnight and boil again for 15 or 20 minutes. Dilute with an equal volume of water and filter. Wash with dilute hydrochloric acid, dissolve in a few c.c. of warm dilute ammonia, and dilute to 200 c.c. with distilled water. Allow to settle and filter. Evaporate in a weighed dish, ignite and weigh. The following analysis will illustrate the composition of a sample of Cornish wolfram as brought into the market. Tungstic acid 50.1%, cassiterite 10.9, ferrous oxide 24.6, manganese oxide 5.4, niobic oxide, alumina, etc. 3.5, silica 1.2, copper oxide 2.7, zinc oxide 0.22, arsenic 0.51, sulphur 0.20, total 99.33. Niobic and tantalic oxides. These oxides are commonly met with in samples of wolfram and tinstone, especially niobic. They are probably present in the form of columbite, a niobate of iron and manganese, and tantalite, a tantalate of the same metals. On boiling with hydrochloric acid, they are both liberated, and remain for the greater part. Note all the niobic in the insoluble residue with the tungstic acid. On removing the latter with dilute ammonia, they remain as a white insoluble precipitate, very prone to run through the filter on washing. They may be dissolved in hydrofluoric acid, either at once or after fusion with bisulfate of potash, and extraction with cold water. To the solution in hydrofluoric acid, gradually add a boiling solution of acid potassium fluoride, HFKF. Potassic fluotantalate, soluble in 200 parts of water, separates out first, and afterwards potassic fluoniobate, soluble in 12 parts of water, The separated salts, after heating with sulphuric acid and washing out the potassium sulphate formed, are ignited with ammonic carbonate and weighed as tantalic oxide, Ta2O5, and niobic oxide, Nb2O5, respectively. They are both white powders. The oxide of niobium dissolved in a bead of microcosmic salt gives a bluish colour in the reducing flame. The oxide of tantalum dissolves in the bead, but gives no colour. End of section 31. Section 32 of A Textbook of Assaying for the Use of Those Connected with Mines, by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 13. Manganese, Chromium, etc. Part 1. Manganese. Manganese occurs mainly as black oxide, MnO2, in the mineral pyrolusite, and in a less pure form in silomelane and wad. The value of the ore depends rather on the percentage of available oxygen than on the proportion of metal present. The results of assays are generally reported as so much % of the dioxide, MnO2. In smaller quantities it is very widely distributed. Manganese itself has a value for steel making, or rather for the making of Spiegeleisen and ferromanganese, which are used in the Bessemer and Siemens processes. For this purpose, the percentage of the metal, Mn, is required. Consequently, the minerals of manganese may be considered in two aspects: one as a source of oxygen, and two as a source of manganese. These will require separate consideration. The black oxide is mainly used in the preparation of chlorine, liberation of which it brings about when treated with hot hydrochloric acid, or with a mixture of common salt and sulphuric acid. The quantity of chlorine which is obtained depends upon the proportion of dioxide present. Footnote: MnO2 plus 4HCl yields MnCl2 plus Cl2 plus 2H2O. End footnote. And in assaying may either be measured by its equivalent of iodine liberated, or by the oxidizing effect on an acid solution of ferrous sulfate. When the ore also carries substances which have a reducing effect, such as ferrous compounds, such assays will give not the total dioxide, MnO2, but less, by the amount required to oxidize these impurities, and this is exactly what is required in valuing such an ore for commercial purposes. Manganese compounds are characterized by the readiness with which they may be converted into highly oxidized bodies. Solution of manganese in hydrochloric acid, rendered alkaline with ammonia, yields a clear solution. Footnote: provided a sufficiency of ammonic chloride is present, end footnote, which rapidly takes up oxygen from the air, forming a brown precipitate of the oxide Mn2O3. The addition of bromine or chlorine to such a solution determines the precipitation of a still higher oxide. Note approximately MnO2, end note. On treating a compound containing manganese with nitric acid and dioxide of lead, PbO2, the oxidation is carried still further, a purple-coloured solution of permanganic acid, HMnO4, or H2O.Mn2O7, being formed. on fusing minerals containing even traces of manganese with sodium carbonate in an open crucible, a green melt is obtained, which owes its colour to sodium manganate, Na2MnO4 or Na2O.MnO3. This salt is soluble in water, forming a green solution, which when rendered acid rapidly changes into the permanganate with the characteristic purple colour. Permanganate of potash is a salt much used in assaying, with some properties of which the student will have already become familiar. Compounds of manganese on boiling with strong hydrochloric acid yield manganous chloride, MnCl2. Footnote: with some silicates, etc., a preliminary fusion with sodium carbonate will be necessary. End footnote. The properties given above serve for the detection of manganese. The higher oxides are distinguished by causing the evolution of chlorine, with its peculiarly suffocating smell, when acted on with hydrochloric acid, while the green melt with sodium carbonate can be relied on for the recognition of manganese itself. There is no dry assay of manganese ores. Wet methods. Strong hydrochloric acid is the best solvent for ores of manganese, but where the proportion of dioxide, MnO2, is required, the solution is affected during the assay. The ore should be in a very fine state of division before treatment with acids. The separation of manganese from other metals is thus effected. Ignite in order to destroy any organic matter which may be present. Dissolve in hydrochloric acid and evaporate to dryness to separate silica. Take up with hydrochloric acid, dilute, pass sulphuretted hydrogen, and filter. Boil off the excess of gas, peroxidize the iron with a drop or two of nitric acid, and separate the iron as basic acetate, as described under iron. Footnote: instead of sodium acetate, ammonium succinate can be used. End footnote. If the iron precipitate is bulky, it is dissolved in a little hydrochloric acid, reprecipitated, and the filtrate added to the original one. Neutralize with soda and add bromine in excess. Heat gradually to boiling, allow to settle, and filter. The precipitate is impure dioxide of manganese, containing alkalis and possibly cobalt or nickel. Gravimetric determination. Dissolve the precipitate in hydrochloric acid and boil. Add a slight excess of carbonate of soda, warm, and filter. Wash with hot water, dry, carefully ignite in an open Berlin crucible, and weigh. The substance is the brown oxide Mn3O4 and contains 72.05% of manganese. If the percentage of dioxide is required, it may be calculated by multiplying the percentage of manganese by 1.582. It must be borne in mind that the manganese should never be calculated to dioxide, except when it is known to exist in the ore only in that form. Volumetric methods. The two methods are based on the oxidizing effect of manganese dioxide, and if the metal does not already exist in this form, it will require a preliminary treatment to convert it. The following method, due to Mr. J. Pattinson, effects this. Footnote: Journal of the Society of Chemical Industry, Volume 10, page 333. End footnote. A quantity of the ore containing not more than 0.25 grams of the metal, Mn, is dissolved in hydrochloric acid in a pint beaker, and if necessary 3 or 4 c.c. of nitric acid are added to peroxidize the iron, and ferric chloride is added if required, so that there may be at least as much iron as manganese. Calcium carbonate is added till the solution is slightly red, and next the redness is removed by the cautious addition of acid. 30 c.c. of zinc chloride solution, containing 15 grams of zinc per litre, are added. The liquid is brought to boil and diluted to about 300 c.c. with boiling water. 60 c.c. of a solution of bleaching powder, 33 grams to the litre, and filtered, rendered slightly greenish by acid, are then run in, and are followed by 3 grams of calcium carbonate suspended in 15 c.c. of boiling water. During effervescence, the beaker is covered. The precipitate is stirred, and 2 c.c. of methylated spirits are mixed in. The precipitate is collected on a large filter, washed with cold water and then with hot, till free from chlorine, which is tested for with starch and potassium iodide. The acid ferrous sulphate solution presently described is then measured into the beaker, and the precipitate still in the paper added. More acid is added if necessary, and the solution is diluted and titrated. In place of bleaching powder solution, 90 c.c. of bromine water containing 22 grams per litre may be used. Ferrous sulphate assay. This method, which is the one commonly used, is based on the determination of the amount of ferrous iron oxidized by a known weight of the ore. It is known that 87 parts of the dioxide will oxidize 112 parts of ferrous iron. Footnote: MnO2 plus 2 FeSO4 plus 2 H2SO4 yields Fe2 (SO4) times 3 plus MnSO4 plus 2 H2O. End footnote. Therefore 1 gram will oxidize 1.287 gram of ferrous iron, or 1 gram of ferrous iron oxidized will be equivalent to 0.7768 gram of the dioxide. The finely divided substance containing the dioxide is digested in a solution of a known quantity of iron in sulphuric acid. The iron, of course, must be in excess, which excess is determined when the ore is dissolved by titrating with standard permanganate or bichromate of potash solution. The assay resolves itself into one for the determination of ferrous iron, for which the standard solutions and method of working described under iron are used. The assay is as follows. For rich ores, 2 grams of clean soft iron wire are treated in a pint flask with 100 c.c. of dilute sulphuric acid and warmed till dissolved. Carefully sample the ore, and in one portion determine the moisture at 100 degrees centigrade. Grind the rest in a Wedgwood mortar with a little pure alcohol until free from grit. This reduces the substance to a finely divided state and assists solution. Evaporate off the alcohol and dry at 100 degrees centigrade. Mix well and keep in a weighing bottle. Weigh up 2 grams and add them to the solution of iron in the flask. Carefully wash it all down into the acid liquid. On rotating the flask, the ore will rapidly dissolve, but gentle heat may be used towards the end to complete the solution. When the residue is clean and sandy looking and free from black particles, the flask is cooled, and the residual ferrous iron is determined by titration with permanganate. The iron thus found, deducted from the 2 grams taken, will give the amount of iron peroxidized by the dioxide contained in the 2 grams of ore. This, divided by 2 and multiplied by 77.68, will give the percentage of dioxide in the sample, or multiplied by 49.41 will give that of metallic manganese. When the quantity of manganese or of the dioxide to be determined is small, it is not necessary to use 2 grams of iron. 1 gram or even less may be taken. The iron may be used in the form of a standard solution of ferrous sulphate and portions measured off, thus saving the labour of weighing. Determination of dioxide in a manganese ore. Weigh up 1 or 2 grams of the finely powdered ore. Footnote: if the ore is very rich, a smaller quantity, 0.75 or 1.5 grams, must be taken, otherwise the iron will be insufficient. End footnote. And an equal weight of pure iron wire. Dissolve the wire in 50 or 100 c.c. of dilute sulphuric acid, and when solution is complete, add the ore and warm till it too is dissolved. Cool, and titrate the remaining ferrous iron with the permanganate or bichromate of potassium solution. For example, 0.7560 gram of pyrolusite and 1.000 gram of iron were taken and treated as above. 13.9 c.c. of permanganate, note standard 100 c.c. equals 0.4920 gram iron, end note, were required. This indicates that 0.0684 gram of iron was left unoxidized by the ore. The iron oxidized then was 0.9316 gram. note 1.000 minus 0.0684, end note. Multiplying this by 0.7768, we find that 0.7237 gram is the quantity of manganese dioxide which was present. This is equivalent to 95.77%. 0.7560 to 0.7237 is equivalent to 100 to 95.77. Iodine method. It has been already stated that when dioxide of manganese is boiled with strong hydrochloric acid, chlorine is given off, and that the amount of chlorine so liberated is a measure of the dioxide present. If the chlorine is passed into a solution of potassium iodide, an equivalent of iodine will be set free. Footnote: MnO2 plus 4HCl yields MnCl2 plus 2H2O plus Cl2. Cl2 plus 2Ki yields 2KCl plus I2. End footnote. This is apparently a very indirect way of determining how much of the dioxide is present, but the reactions are very sharp, and the final determination of the iodine is an easy one. The finely powdered sample of dioxide is placed in a small flask provided with an exit tube leading into a solution of potassic iodide. Figure 60. Reader's note: Figure 60 shows a spherical flask held in a retort stand with an exit tube leading into the first of 3 glass bulbs. The second of these bulbs contains the potassium iodide solution and is completely immersed in a water bath on a tripod. The first and third bulbs are mostly above the surface of the water in the bath. The third bulb ends in a vertical tube, apparently sealed. End reader's note. On adding hydrochloric acid and boiling, the chlorine evolved is driven into the iodide solution and there absorbed. The boiling is continued till the steam and hydrochloric acid fumes have driven the last portions of the chlorine out of the flask and into the solution. In this experiment there is a strong tendency for the iodide solution to rush back into the flask. This tendency is overcome by avoiding draughts and regulating the heat, or by placing a lump of magnesite in the flask, which acts by evolving carbonic acid and so producing a steady outward pressure. When the distillation is finished, the tube containing the iodine is detached and washed out into a beaker. If the solution is strongly acid, it should be almost neutralized by the cautious addition of dilute ammonia. If crystals of iodine have separated, potassium iodide must be added in quantity sufficient to dissolve them. The condenser must be kept cool whilst the chlorine is passing into it. The solution, transferred to a beaker, is titrated with a standard solution of sodic hyposulfite. Note: 100 cc equals 1.27 gram iodine or 0.435 gram of dioxide of manganese. End note. In titrating, the solution should be cold, or not warmer than 30 degrees centigrade. The bulk may vary from 100 to 200 cc, but it is best always to work with the same volume. The hypo is run in with constant agitation until the brown colour has been reduced to a light yellow. 5 cc of starch solution are then added, and the titration cautiously continued until the end is reached. The finish is indicated by a change from blue to colourless. The assay solution may be acidified with acetic, sulphuric or hydrochloric acid before titrating with hypo, but it must be only faintly so. An excess of acid may be nearly neutralized with ammonia without interference, but excess of alkali is fatal. Bicarbonate of soda must not be used in excess. It is best to avoid it altogether. The assay solution should be titrated at once, as it weakens on standing, and the hypo solution should be standardized every 2 or 3 days, as its strength is not constant. The standard solution of hyposulfite of soda is made by dissolving 25 grams of the salt, Na2S2O3.5H2O, in water and diluting to 1 litre. 100 cc are equivalent to 1.27 gram of iodine. This solution is standardized by weighing, in a small beaker, about half a gram of iodine, to which is added a crystal or 2 of potassium iodide and a few drops of water. When dissolved, the solution is diluted to 100 cc and titrated in the manner described. The starch solution is made in the manner described under the iodide copper assay. 5 cc are used for each titration. In determining the effects of variations in the condition of the assay, a solution of iodine was used which was equivalent in strength to the hypo solution. It was made by dissolving 12.7 grams of iodine with 25 grams of potassium iodide in a little water and diluting to 1 litre. 100 cc of this solution were found, at the time of the experiments, to be equivalent to 102.0 cc of the hypo. Effect of varying temperature. The bulk of the solution was 100 cc. 20 cc of iodine were taken and 5 cc of starch solution were added towards the end as indicator. These conditions are also those of the other experiments, except where otherwise stated. Iodine being volatile, it is to be expected that with hot solutions low results will be obtained. Temperature 15 degrees, hypo required 20.4 cc. Temperature 20 degrees, hypo required 20.4 cc. Temperature 40 degrees, hypo required 20.1 cc. Temperature 60 degrees, hypo required 19.2 cc. Temperature 80 degrees, hypo required 15.5 cc. These show that the temperature should not much exceed 20 degrees. Effect of exposure of the iodine solution. 20 cc of the iodine were diluted to 100 cc and exposed for varying lengths of time in open beakers at the ordinary temperature, and then titrated. Time exposed, none. Hypo required 20.4 cc. Time exposed 1 day, hypo required 16.1 cc. Time exposed 2 days, hypo required 13.6 cc. Time exposed 3 days, hypo required 9.4 cc. Effect of varying bulk. These experiments were carried out in the usual way, bulk only varying. Bulk 100.0 cc, hypo required 20.4 cc. Bulk 200.0 cc, hypo required 20.4 cc. Bulk 300.0 cc, hypo required 20.4 cc. Bulk 500.0 cc, hypo required 20.4 cc. Effect of varying acid. These experiments were under the usual conditions, the bulk being 100 cc. The results were acetic acid, none, hypo required 20.4 cc. Acetic acid 1.5 cc, hypo required 20.7 cc. Acetic acid 30.0 cc, hypo required 20.7 cc. Hydrochloric acid, none, hypo required 20.4 cc. Hydrochloric acid 1.5 cc, hypo required 20.6 cc. Hydrochloric acid 15.0 cc, hypo required 20.9 cc. Sulphuric acid, none, hypo required 20.4 cc. Sulphuric acid 0.5 cc, hypo required 20.7 cc. Sulphuric acid 20.0 cc, hypo required 15.2 cc. Footnote: iodine probably lost by volatilization. End footnote. Nitric acid, none, hypo required 20.4 cc. Nitric acid 0.5 cc, hypo required 21.5 cc. Nitric acid 10.0 cc, hypo required, could not be titrated. In the application of this titration to the assay of manganese ores, hydrochloric acid and hydriodic acids are the only ones likely to be present. Effect of alkalis. On theoretical grounds, the presence of these is known to be inadmissible. A solution rendered faintly alkaline with ammonia required only 11.2 cc of hypo, and another with 0.5 gram of caustic soda required 4.0 cc instead of 20.4 cc as in neutral solutions. Effect of nearly neutralizing hydrochloric acid solutions with ammonia. Provided care is taken not to add excess of ammonia, this has a good effect, counteracting the interference of excess of acid. Thus 20 cc of iodine, as before, required 20.4 cc of hypo. With 15 cc of hydrochloric acid, 20.7 cc were required. but with 15 cc of acid nearly neutralized with dilute ammonia, 20.4 cc were used. Effect of the addition of starch. The addition of varying quantities of starch has no effect, provided it is added when the titration is nearly finished, as the following experiments show. Starch added 1.0 cc, hypo required 20.4 cc. Starch added 5.0 cc, hypo required 20.4 cc. Starch added 10.0 cc, hypo required 20.4 cc. Starch added 50.0 cc, hypo required 20.5 cc. But if the starch is added before the titration, the results are liable to error. Starch added 1.0 cc, hypo required 20.4 cc. Starch added 50.0 cc, hypo required 24.0 cc. The starch should be used fresh and is best made on the day it is used. After 4 days, the finishing point is not so good. Effect of varying potassium iodide. An excess of iodide is always required to keep the iodine in solution. A larger excess has little effect. Iodide added, none. Hypo required, 20.4 cc. Iodide added, 1 gram. Hypo required, 20.5 cc. Iodide added, 20 grams. Hypo required, 20.6 cc. The 20 cc of iodine used itself contained 0.5 gram of potassium iodide. Effect of foreign salts. Bicarbonate of soda added, none. Hypo required, 20.4 cc. Bicarbonate of soda added, 0.5 gram. Hypo required, 18.2 cc. Bicarbonate of soda added, 1.5 gram. Hypo required, 17.1 cc. Bicarbonate of soda added, 5.0 grams. Hypo required, 16.0 cc. The solution obviously must be free from bicarbonate of soda. This should be remembered, since when titrating arsenic assays with iodine, it must be present, and students must avoid confounding the two titrations. In some other experiments, in which 10 grams each of the salts were taken, the following results were obtained. Salt added, none. Hypo required, 20.4 cc. Salt added, ammonium chloride. Hypo required, 20.5 cc. Salt added, ammonium nitrate. Hypo required, 20.3 cc. Salt added, ammonium sulphate. Hypo required, 20.2 cc. Salt added, sodium chloride. Hypo required, 20.3 cc. Salt added, sodium nitrate. Hypo required, 20.4 cc. Salt added, sodium sulphate. Hypo required, 20.4 cc. Effect of varying iodine. Iodine added, 1.0 cc. Hypo required, 1.3 cc. Iodine added, 10.0 cc. Hypo required, 10.2 cc. Iodine added, 20.0 cc. Hypo required, 20.4 cc. Iodine added, 50.0 cc. Hypo required, 51.0 cc. Iodine added, 100.0 cc. Hypo required, 102.0 cc. Determination of dioxide in a manganese ore. Weigh up 0.25 to 0.3 gram of the powdered ore. Place in a flask, cover with 10 cc of hydrochloric acid, and close the flask with a paraffined cork and bulbs as shown in figure 60, having previously charged the bulb with 5 grams of potassium iodide in strong solution. Heat the flask and boil cautiously for about 15 minutes. Wash the contents of the bulbs into a large beaker. Nearly, but not quite, neutralize with dilute ammonia and titrate with the standard hypo. As an example, 0.2675 gram of pyrolusite was taken and required 60.3 cc of standard hypo. Note, 100 cc equal 1.185 gram iodine or 0.4042 gram manganese dioxide, MnO2, end note, which equals 0.2437 gram of the dioxide or 91.1%. Colorimetric method. When compounds of manganese free from chlorides are boiled with nitric acid and dioxide of lead (footnote: obtained as a brown powder by digesting red lead with nitric acid and filtering), end footnote, the manganese is converted into permanganic acid, which is soluble and tints the solution violet. The depth of colour depends on the amount of manganese present, and this should not much exceed 10 milligrams. A quantity of substance containing not more than this amount of manganese should be boiled for a few minutes with 25 c.c. of a solution containing 5 c.c. of nitric acid and 10 or 20 c.c. of dilute sulphuric acid with 2 or 3 grams of lead dioxide. Filter through asbestos, wash by decantation with dilute sulphuric acid, make up with distilled water to a definite bulk. Footnote: the water for dilution and the dilute sulphuric acid used for washing should be previously tested to see they have no reducing action with dilute permanganate of potassium solution. End footnote. And take a measured portion for the colorimetric determination. The standard solution of manganese is made by dissolving 0.1435 gram of permanganate of potash, KMnO4, in a little water acidulated with nitric acid and diluted to 1 litre. 1 c.c. will contain 0.05 mg of manganese. Practical exercises. 1. What percentage of manganese, Mn, is contained in permanganate of potash, KMnO4? 2. 10 c.c. of a solution of permanganate of potash is found to oxidize 10 c.c. of an acid solution of ferrous sulphate. The manganese is determined in the titrated solution by precipitation as dioxide and titrating. How much of the ferrous solution will be oxidized in the second titration? 3. What weight of potassium iodide would be just sufficient to absorb the chlorine evolved by 0.5 gram of pure dioxide of manganese? 4. What weight of iron must be dissolved up so as to have an excess of 0.25 gram after oxidation by 1 gram of pure dioxide? 5. What weight of the brown oxide, Mn2O4, will be left on igniting 1 gram of the pure dioxide? End of section 32. Section 33 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 13. Manganese, Chromium, etc. Part 2. Chromium. Chromium occurs in nature chiefly as chromite or chrome iron ore. Note: FeO, Cr2O3 with more or less MgO and Al2O3, end note, which is the chief ore. It is a constituent of some silicates and is frequently met with in very small quantities in iron ores. It occurs as chromate in crocoisite, PbCrO4, and some other rare minerals. The metal is used in steel making. Steel containing about 0.5% of it is rendered very hard, but its chief value is in its salts, the chromates. These are highly coloured compounds, generally red or yellow. Some of the insoluble chromates are used as pigments. Chromate of lead or chrome yellow is the most important. The soluble chromates, those of soda and potash, are valuable chemicals and are largely used in the preparation of pigments, dyeing and tanning, and as oxidizing agents. Chromium forms 2 important classes of compounds: chromic salts, corresponding to the oxide Cr2O3, and chromates, which contain the trioxide CrO3. Solutions of chromic salts are green, whilst those of the chromates are yellow. Chromates are reduced to chromic salts by the action of most reducing agents in the presence of an acid, and this property is used in assaying for the volumetric determination of ferrous iron, etc. The chromates in solution are more stable than other similar oxidizing agents, and consequently are generally used in the laboratory as one of the standard oxidizing agents for volumetric analysis. They have the disadvantage of requiring an outside indicator. Bichromate of potash, K2Cr2O7, is the salt generally used for this purpose. Chromic salts are oxidized to chromate by fusion with fusion mixture and niter, or by treating with chlorine in an alkaline solution. Chromic salts closely resemble those of ferric iron, and in the ordinary course of analysis, chromic hydrate, green, is precipitated together with ferric hydrate, alumina, etc., on the addition of ammonic chloride and ammonia. The ignited oxide, Cr2O3, however, is not reduced on heating to redness in a current of hydrogen. Detection. Chromium is detected by fusing the powdered substance with fusion mixture and niter. The melt is extracted with water and filtered. The filtrate is acidified with acetic acid and treated with a few drops of a solution of lead acetate. A yellow precipitate indicates chromium. Substances containing chromium impart a green colour to the borax bead in both flames. Small quantities of chromate in neutral solution can be found by the dark or violet red coloration imparted thereto on boiling with a dilute decoction of logwood. Solution and separation. Chromates and chromic salts are generally soluble in water or dilute acids. Chrome iron ore, however, and ignited chromic oxide are insoluble, and the former presents considerable difficulty on attempting to open up by the usual methods. A large number of mixtures have been tried in order to get all the chromium in a soluble form. Among these are the following. 1 part of the very finely powdered ore is fused with any of these mixtures. 1. 10 parts of bisulphate of potash. 2. 5 parts of bisulphate of potash and 5 parts of potassium fluoride. 3. 5 parts of hydric potassic fluoride. 4. 12 parts of bisulphate of potash, and afterwards with 6 parts of carbonate of soda and 6 parts of niter. 5. 8 parts of borax, afterwards with carbonate of soda till it ceases to effervesce, then with 3 parts of carbonate of soda and 3 of niter. 6. 4 parts of borax and 6 parts of fusion mixture. 7. 12 parts of caustic potash. 8. 10 parts of caustic soda and 30 of magnesia. 9. 5 parts of caustic soda and 3 of magnesia. 10. 2 parts of carbonate of soda and 1 of lime. 11. 6 parts of soda lime and 2 of chlorate of potash. 12. Sodium peroxide. Of these, numbers 1, 2, and 3 yield the chromium in a form soluble in dilute acids, as chromic salt, the rest in a form soluble in water, as potassium or sodium chromate. On boiling an insoluble chromium compound with chlorate of potash and nitric acid, the chromium passes into solution as chromate. This method, however, does not answer for chrome iron ore. In the fusion methods, the ore must be very finely powdered, well mixed with the fluxes, and subjected to a prolonged fusion in a platinum vessel at a high temperature. Undecomposed particles require refusion. The aqueous extract containing the chromate is ready for volumetric work, except in those cases where niter has been used. For gravimetric work, the solution is acidified with hydrochloric acid, then mixed with ammonia in slight excess, boiled, and filtered. The filtrate is acidified with hydrochloric acid and treated with sulphuretted hydrogen, warmed, rendered slightly alkaline with ammonia, and the gas again passed. The chromium is precipitated as chromic hydrate mixed with sulphur from the reduction with sulphuretted hydrogen. It is filtered off, washed with hot water, and ignited. It is weighed as chromic oxide. Gravimetric determination. The solution containing the chromium, freed from other metals and earths and in the form of green chromic salt, is heated to boiling. If any chromate is present, reduce it with sodium sulphite or sulphuretted hydrogen. Add ammonia in slight excess, Boil till the liquid is free from a red tint and allow to settle for a few minutes. Filter, wash with hot water, dry, and ignite strongly in a loosely covered crucible. Cool and weigh. The substance is chromic oxide, Cr2O3, and contains 68.62% of chromium. It is a dark green powder, insoluble in acids. When, as is generally the case, the chromium exists altogether as chromate, note phosphates and arsenates being absent, end note, it is best to proceed as follows. Render the solution acid with acetic acid, then add sodium acetate to the solution and heat nearly to boiling. Next, treat with a slight excess of acetate of lead and boil. Allow to settle and filter. Wash the precipitate with hot water, dry in the water oven or at a low temperature. Transfer the precipitate to a weighed Berlin crucible, burn the filter separately, ignite below redness, cool in the desiccator and weigh. The substance is lead chromate, PbCrO4, and contains 16.1% of chromium, or 23.53% of chromic oxide, Cr2O3. Volumetric method. This is based on the oxidation of ferrous iron by the solution containing the chromium as chromate. A known weight of iron, note 0.5, 1 or 1.5 gram according to the quantity of chromate, end note, is dissolved in 50 c.c. of dilute sulphuric acid. The solution containing the chromate is added, and the remaining ferrous iron titrated with the permanganate or bichromate of potassium solution, as described under iron. The iron thus found is deducted from that taken, and the difference gives the iron oxidized by the chromate. This, multiplied by 0.3101, gives the chromium, Cr, and when multiplied by 0.4529 gives the chromic oxide, Cr2O3. Colorimetric method. Small quantities of chromium may be determined after conversion into chromate colorimetrically. The solution, which should not contain more than a few milligrams in 100 c.c., is acidified with acetic acid and compared against an equal volume of water rendered acid with acetic acid and tinted with a standard bichromate of potassium solution. This standard bichromate is made by dissolving 2.827 grams of the salt in water and diluting to 1 litre. 1 c.c. will contain 1 milligram of chromium, Cr. The manner of working this assay is the same as that adopted in the other colorimetric processes. Determination of chromium in steel. Footnote: Arnold and Hardy, Chemical News, Volume 57, page 153. End footnote. Weigh up 2.4 grams, dissolve in hydrochloric acid and evaporate to dryness. Fuse with sodium carbonate and nitre, extract with water, and make up to 301 c.c. Take 250 c.c. of the clear liquor, boil with hydrochloric acid, add sodium phosphate and then ammonia in slight excess. Heat till clear. Filter off the precipitate, dissolve it in hydrochloric acid, and evaporate to dryness. Take up with a little acid, filter, and precipitate with a slight excess of ammonia. Wash, ignite, and weigh as chromium phosphate. Note 3Cr2O3, 2P2O5, end note, which contains 42.2% of chromium. Vanadium. Vanadium occurs in certain rare minerals, such as vanadinite. Note 3Pb3, open bracket, VO4, close brackets, times 2, dot PbCl2, end note. A vanadate of lead. Mottramite, a vanadate of copper and lead, and decanite, a vanadate of lead and zinc. It is occasionally found in iron and copper ores and in the slags from them. In Spanish copper precipitates it is found along with chromium, and is probably derived from the iron used for precipitating. The vanadates, like the chromates, are coloured compounds, generally yellow or red. On reduction, blue solutions are got. In their general reactions, vanadates resemble phosphates. Vanadium is detected by the red coloration produced by passing sulphuretted hydrogen into ammoniacal solutions for some time. On adding an acid to the filtered solution, a brown precipitate of the sulphide is produced. This gives with borax a colourless bead in the oxidizing and a green one in the reducing flame. It is separated by fusing the ore with potassic nitrate, extracting with water, and precipitating with baric chloride. The precipitate is boiled with dilute sulphuric acid, filtered, neutralized with ammonia, and saturated with ammonic chloride. Ammonium vanadate separates out. It is filtered off, ignited, and weighed as vanadic oxide, V2O5, containing 56.18% of vanadium. Molybdenum. Molybdenum occurs in nature chiefly as molybdenite, MoS2. It also occurs in wolfenite, a molybdate of lead, PbMoO4, and in molybdic ochre, MoO3. Molybdate of ammonia is an important reagent in the determination of phosphates, the manufacture of which compound is the chief purpose to which molybdenum is applied. Iron and copper ores frequently contain molybdenum, sometimes in quantity. Consequently, it is met with in slags and pig iron. Molybdenum forms several series of salts. In those corresponding to the lower oxides it is basic, but the trioxide, MoO3, is the acid oxide which forms a series of salts called the molybdates. All molybdenum compounds are converted into the trioxide by boiling with nitric acid. The trioxide is a white powder readily dissolved by ammonia. It fuses at a red heat and volatilizes freely in contact with air. It is slightly soluble in water. Molybdates are easily reduced with the production of coloured solutions by most reducing agents. Sulphuretted hydrogen first produces a blue tint and then precipitates a brown sulphide. The precipitation as sulphide is only complete on prolonged treatment. A green colour indicates that some molybdenum still remains in solution. The precipitated sulphide is soluble in ammonium sulphide. Detection. Molybdenum is detected by its behaviour with sulphuretted hydrogen. Molybdenite can only be mistaken for graphite, from which it is easily distinguished by yielding sulphur dioxide on roasting, and by giving, on charcoal, a yellowish-white incrustation, which becomes blue on touching it for a moment with the reducing flame. The borax bead is colourless in the oxidizing and dark brown in the reducing flame. Gravimetric determination. The solution containing the molybdate is neutralized and treated with an excess of mercurous nitrate. The precipitate is allowed to settle for some time, filtered, and washed with a dilute solution of mercurous nitrate. Then it is dried, transferred to a weighed Berlin crucible containing ignited oxide of lead, mixed, ignited, and weighed. The increase in weight gives the amount of trioxide, MoO3. This contains 66.7% of molybdenum. Uranium. Uranium occurs chiefly as pitchblende, which is an impure oxide, U3O8. It is also found as sulphate in uranochre, johannite, etc., and as phosphate in the uranites, turbinite, note, hydrated phosphate of uranium and copper, end note, and autunite, note, hydrated phosphate of uranium and lime, end note. It also occurs in some rarer minerals. The oxide is used for colouring glass, and the nitrate and acetate are used as reagents. Uranium yellow, used for enamel painting, is sodium uranate. The uranates, in which the oxide of uranium acts as an acid, are mostly insoluble and of secondary importance. Uranium forms two families of salts, uranous and uranic, corresponding to the oxides UO2 and UO3 respectively. The former are generally green and the latter yellow. Uranous salts are converted into uranic by boiling with nitric acid or other oxidizing agents. Uranic salts, on the other hand, are easily reduced by sulphuretted hydrogen, stannous chloride, or zinc. This property is made use of in determining the quantity of uranium in pure solutions by titrating with permanganate of potassium solution, as in the case with iron. Detection. The most characteristic reaction of the uranium compounds is their behaviour in the presence of alkaline carbonates, in which they are freely soluble. Even ammonium sulphide will not precipitate uranium from these solutions. On neutralizing the carbonate with an acid, a uranate of the alkali is precipitated. Ammonia or sodic hydrate (free from carbonates) give yellow precipitates which are insoluble in excess of the reagent, but are soluble in acids. Ferrocyanide of potassium gives a reddish-brown precipitate. Uranium colours the borax bead yellowish-green in the oxidizing and green in the reducing flame. Solution and separation. The compounds of uranium are soluble in acids. Powder the substance and evaporate with an excess of nitric acid. Take up with hydrochloric acid, dilute, pass sulphuretted hydrogen, and filter. Peroxidize the filtrate with a little nitric acid. Add an excess of ammonic carbonate and some ammonium sulphide, and filter. Render the solution acid, boil, and precipitate the uranium by means of ammonia. Filter off and wash it with dilute ammonic chloride. Ignite and weigh as protosesquioxide, U3O8. Gravimetric determination. The solution containing the uranium free from other metals is, if required, first peroxidized by boiling with nitric acid. Ammonia in slight excess is added to the nearly boiling solution. A yellow precipitate is formed, which is filtered off hot and washed with a dilute solution of ammonium chloride. The precipitate is dried and ignited, and weighed as U3O8, which contains 84.8% of uranium. Volumetric method. This is based on the precipitation of uranium as phosphate from acetic acid solutions and the recognition of complete precipitation by testing with potassic ferrocyanide. It is the converse of the process for the volumetric determination of phosphates. The standard solution of phosphate is prepared by dissolving 29.835 grams of hydric sodic phosphate, Na2HPO4.12H2O, in water and diluting to 1 litre. 100 c.c. will be equivalent to 2 grams of uranium. Take 1 gram of the sample, or if poor in uranium, 2 grams, and separate the uranium as described. Dissolve the precipitate in nitric acid and evaporate to a small bulk. Add 2 grams of sodium acetate, dilute with water to 100 c.c. and boil. Titrate the boiling solution with the sodium phosphate till it ceases to give a brown coloration with potassium ferrocyanide. Calculate the percentage in the usual way. End of section 33. Section 34 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 14. Earths, Alkaline Earths, Alkalies. Part 1. Alumina. Alumina, the oxide of aluminium, Al2O3, is found in nature fairly pure in the mineral corundum, transparent and coloured varieties of which form the gems sapphire and ruby. A coarser, compact variety, contaminated with oxide of iron, constitutes emery. Compounded with silica, alumina forms the base of clays and many rock-forming minerals. China clay, or kaolin, is used as a source of alumina. Bauxite, hydrated alumina, is also used for the same purpose, that is, for the preparation of sulphate of alumina. The mineral cryolite is a fluoride of aluminium and sodium. Corundum is characterized by high specific gravity, 4.0, and extreme hardness. By these it is distinguished from feldspar and similar minerals, which it somewhat resembles in general appearance. Aluminium is used for a variety of small purposes. It is white, light, and very tenacious, but owing to the difficulty of its reduction, it is expensive. Aluminium forms one series of salts which closely resemble those of ferric iron. It forms an interesting series of double sulphates, known as the alums. Common potash alum is Al2(SO4) times 3, K2SO4, 24H2O. Detection. Alumina is not precipitated from its acid solution by sulphuretted hydrogen, but it is thrown down by ammonia, with the other earths, as a white hydrate, soluble in soda and insoluble in ammonic carbonate. Filtered off and ignited, it assumes, after treatment with nitrate of cobalt, before the blowpipe, a blue colour which is characteristic. With natural compounds containing metallic oxides, this colour is masked. It is more satisfactory to make a separation in the wet way and to test the ignited oxide. Separation and solution. If the substance is insoluble in hydrochloric acid, it is finely powdered and fused with fusion mixture with the help, in the case of corundum, which is very refractory, of a little caustic soda or potash. The method of working is the same as that described for opening up silicates. See under Silica. Corundum cannot be powdered in Wedgwood or even agate mortars, since it rapidly wears these away and becomes contaminated with their powder. It is best to use a hard steel mortar and to extract the metallic particles from the bruised sample with a magnet or dilute acid. When the substance has been completely attacked and dissolved, it is evaporated to dryness with an excess of hydrochloric acid on the water bath to render any silica present insoluble. The residue is extracted with hydrochloric acid and freed from the second group of metals by means of sulphuretted hydrogen. The filtrate from this, after removing the sulphuretted hydrogen by boiling, is nearly neutralized and treated with 8 or 10 grams of hyposulfite of soda in solution. Footnote: Al2Cl6 plus 3Na2S2O3 plus 3H2O yields Al2 open bracket HO close bracket times 6 plus 6NaCl plus 3S plus 3SO2. End footnote. It is then boiled till the sulphurous oxide is driven off. The precipitate is filtered off, ignited, and weighed as alumina. It is sometimes more convenient to proceed as follows. After boiling off the sulphuretted hydrogen, peroxidize the iron with a little nitric acid, add a solution of ammonic chloride and then ammonia in very slight excess. Boil, filter, wash, ignite, and weigh the oxides. These generally consist of ferric oxide and alumina. It is a common practice to determine the iron, calculate it to ferric oxide, and so to estimate the alumina indirectly. This may be done either by igniting in a current of hydrogen and estimating the iron by the weight of oxygen lost, or by dissolving with sulphuric and hydrochloric acids and determining the iron volumetrically. It should be borne in mind that these oxides will also contain any phosphoric oxide that happens to be in the mineral. In general analyses of samples containing alumina, it may be contained in both the soluble and insoluble portions. In these cases, it is better to fuse the sample with fusion mixture before treatment with acids. The alumina in the fused mass will exist in a state soluble in acids. Gravimetric determination. Solutions containing alumina free from the other metals are diluted to a convenient bulk and heated nearly to boiling. Add chloride of ammonium and then ammonia in slight excess. Boil, allow to settle, filter, and wash with hot water. Dry the precipitate and ignite in a platinum or porcelain crucible at the strongest heat. Cool and weigh. The substance is alumina, Al2O3, which contains 52.94% of aluminium. It is only in special cases, such as the analysis of metals and alloys, that it is reported as aluminium. The percentage of alumina is generally given. Ignited alumina is difficultly soluble in acids. It is not reduced by hydrogen at a red heat. Ignited with ammonium chloride, portions are volatilized. Direct determination of alumina in the presence of iron. The iron and alumina are precipitated as hydrates by ammonia. The precipitate is dissolved in hydrochloric acid, and the iron reduced to the ferrous state. It is then added to a hot solution of potash or soda. The solution is boiled till the precipitate settles readily, filtered, and washed with hot water. The alumina is contained in the filtrate, which is acidified with hydrochloric acid, and the alumina precipitated therefrom as hydrate with ammonia, as just described. Determination of alumina in the presence of phosphates and iron. For details, see a paper by R.T. Thompson in the Journal of the Society of Chemical Industry, Volume 5, page 152. The principles of the method are as follows. If the substance does not already contain sufficient phosphoric oxide to saturate the alumina, some phosphate is added. The iron is reduced to the ferrous state, and phosphate of alumina precipitated in an acetic acid solution. It is purified by reprecipitation, ignited, and weighed as phosphate, Al2O3, P2O5, which contains 41.8% of alumina, Al2O3. Examination of clays. Moisture. Take 5 grams of the carefully prepared sample and dry in the water oven till the weight is constant. Loss on ignition. Weigh up 2 grams of the sample used for the moisture determination and ignite in a platinum crucible to redness. Cool and weigh. Silica and insoluble silicates. Weigh up another 2 grams of the dried sample and place them in a platinum dish. Moisten with water and cover with 20 cc of sulphuric acid. Evaporate and heat gently to drive off the greater portion of the free acid. Allow to cool and repeat the operation. Extract by boiling with dilute hydrochloric acid, filter, wash, dry, ignite and weigh. The quantity of insoluble silicates is determined by dissolving out the separated silica with a strong boiling solution of sodium carbonate. The residue, washed, dried and ignited, is weighed and reported as sand. Alumina and ferrous oxide. To the filtrate from the silica, add soda solution till nearly neutral, and then sodium acetate. Boil and filter off the precipitate. Reserve the filtrate. Dissolve the precipitate in hydrochloric acid and dilute to exactly 200 cc. Divide into 2 parts of 100 cc each. In one, determine the iron by reducing and titrating in the way described under volumetric iron. Calculate the percentage as ferrous oxide, unless there are reasons to the contrary. Also, calculate its weight as ferric oxide. To the other portion add ammonia in slight excess and boil. Filter, wash with hot water, dry, ignite, and weigh as mixed alumina and ferric oxide. The weight of the ferric oxide has already been determined in the first portion. Deduct it, and the difference is the weight of alumina. Lime. To the reserved filtrate, concentrated by evaporation, add ammonium oxalate and ammonia. Boil, filter, ignite strongly, and weigh as lime. Magnesia is separated from the filtrate by adding sodium phosphate. It is weighed as magnesium pyrophosphate. Potash and soda. These are determined in a fresh portion of the sample by Lawrence Smith's method, as described on page 333. Reader's note in section 35 of this recording. End reader's note. Thoria. This is an oxide of thorium, ThO2. It is only found in a few rare minerals. It is a heavy oxide, having, when strongly ignited, a specific gravity of 9.2. In the ordinary course of analysis it will be separated and weighed as alumina. It is separated from this and other earths by the following method. The solution in hydrochloric acid is nearly neutralized and then boiled with sodium hyposulfite. The thoria will be in the precipitate. It is dissolved and the solution heated with ammonium oxalate in excess. The precipitate is thorium oxalate, which is washed with hot water, dried and ignited. It is then weighed as thoria, ThO2. Thoria which has been ignited is not readily soluble in acids. Zirconia. The oxide of zirconium, ZrO2, is found in the mineral zircon, a silicate of zirconia, ZrSiO4. When heated intensely, it becomes very luminous and is used on this account for incandescent lights. In the ordinary course, it is thrown down by ammonia with the other earths, from which it is then separated. The hydrates, precipitated in the cold and washed with cold water, are dissolved in hydrochloric acid, nearly neutralized with soda, and precipitated by boiling with hyposulphite of soda. Dissolve, and from the hydrochloric acid solution, precipitate the thoria, if any, with ammonium oxalate. To the filtrate add carbonate of ammonia, which will precipitate any titanium present. The zirconia will be in solution, and is recovered by precipitating with potassium sulphate, or by evaporating the solution and igniting. It is separated from alumina by taking advantage of its insolubility in potassic hydrate. It is estimated in zircons in the following way. The powdered substance is fused with bisulphate of potash and extracted with dilute sulphuric acid. The residue is fused with caustic soda and extracted with water. The portion not dissolved, consisting of zirconate of soda, is dissolved in hydrochloric acid. The solution is diluted, filtered if necessary, and treated with ammonia in excess. The precipitate is filtered off, washed with hot water, dried, ignited, and weighed as zirconia, ZrO2. This is a white powder which is insoluble in acids. Even in hydrofluoric acid it is only slightly attacked. Cerium. Cerium occurs as silicate, note, together with the oxides of lanthanum, didymium, iron, and calcium, end note, in the mineral cerite, which is its chief source. It also occurs as phosphate in monazite and as fluoride in fluocerite. The oxalate is used in medicine. Cerium forms two classes of salts corresponding to the oxides cerous oxide, Ce2O3, and ceric oxide, CeO2. Compounds of cerium with volatile acids yield dioxide on ignition, and this, on solution in hydrochloric acid, yields cerous chloride and chlorine. In the ordinary course, cerium is thrown down along with alumina and the other earths by ammonia. It is separated by dissolving the hydrates in hydrochloric acid and oxidizing with chlorine water. On treating with oxalic acid, cerium, lanthanum, and didymium are precipitated as oxalates, which on ignition are converted into oxides. These are soluble in acids. Their solution in hydrochloric acid is nearly neutralized. Acetate of soda is then added, and an excess of sodium hypochlorite. On boiling, the cerium is precipitated as dioxide, which is filtered off, ignited, and weighed. Cerium is detected by giving with borax a bead which is yellow in the oxidizing and colourless in the reducing flame. Traces of cerium compounds boiled with dioxide of lead and nitric acid will give a yellow solution. Lanthanum and didymium occur together with cerium in cerite, and are separated with that metal as oxalates, as described under cerium. Didymium salts have a rose or violet colour, and impart, when in sufficient quantity, the same colour to the borax bead. Solutions have a characteristic absorption spectrum. The separation of lanthanum and didymium in the solution from which the cerium has been precipitated is effected by precipitating them together as oxalates, igniting, and dissolving in dilute nitric acid. This solution is then evaporated to dryness and ignited for a few minutes, just below redness. A subnitrate of didymium is formed, and remains as an insoluble residue on extracting with hot water. The separated salts are treated with ammonia and ignited, and weighed as oxides, La2O3 and Di2O3. Yttria. Yttria is found in gadolinite, and some other rare minerals. It is precipitated along with the other earths by ammonia. It is distinguished by the insolubility of its hydrate in potash, by the insolubility of its oxalate in oxalic acid, and by not being precipitated by hyposulfite of soda or potassium sulfate. Further, it is precipitated by potash in the presence of tartaric acid as an insoluble tartrate. This reaction distinguishes the members of the yttria group from most of the other earths. The other members of the group closely resemble it, and amongst them are erbia, terbia, ytterbia, scandia, etc. Beryllia. The oxide of beryllium, BeO, also known as glucina, occurs in nature mainly as silicate. Beryl, the green transparent variety of which is the emerald, is the best known of these. It is a silicate of alumina and beryllia. Footnote: 3BeO, Al2O3, 6SiO2. End footnote. Some other minerals in which it occurs are phenakite, euclase, and chrysoberyl. In the ordinary course of analysis, beryllia will be precipitated with alumina, etc., by ammonic hydrate. It is distinguished by the solubility of its hydrate in ammonic carbonate, by not being precipitated by boiling with sodium hyposulfite, and by not being precipitated by ammonic sulfide from an ammonic carbonate solution. The analysis of silicates containing beryllia is thus effected. The finely powdered substance is fused with twice its weight of potassium carbonate, and the melt is extracted with water and evaporated with a slight excess of sulphuric acid to render the silica insoluble. Treat with water, filter, and evaporate the filtrate until a crust is formed. Potash alum crystallizes out. The liquor is poured off into a warm, strong solution of ammonium carbonate. Ferric hydrate and alumina will be precipitated. They are filtered off, redissolved, and again precipitated in ammonic carbonate solution. The combined filtrates are boiled for some time and acidified slightly with hydrochloric acid. The carbon dioxide is boiled off, and the beryllia is then precipitated as hydrate with ammonia. The hydrate is washed with hot water, dried, ignited, and weighed as beryllia, BeO. Beryllia has a specific gravity of 3.08. It is white, infusible, and insoluble in water. After ignition, it is insoluble in acids, except sulphuric, but is rendered soluble by fusion with alkalis. Beryllia, in a solution of carbonate of ammonia, is precipitated as carbonate on boiling, in proportion as the carbonate of ammonia is volatilized. The hydrate is dissolved by a boiling solution of ammonic chloride, ammonia being evolved. The alkaline earths. Lime. Lime is an oxide of calcium, CaO. It occurs abundantly in nature, but only in a state of combination. The carbonate, CaCO3, found as limestone, chalk, and other rocks, and as the minerals calcite and aragonite, is the most commonly occurring compound. The hydrated sulphate, gypsum, CaSO4.2H2O, is common and is used in making plaster of Paris. Anhydrite, CaSO4, also occurs in rock masses and is often associated with rock salt. Phosphate of lime, in the forms of apatite, phosphorite, coprolite, etc., is largely mined. Lime is a component of most natural silicates. Calcium also occurs, combined with fluorine, in the mineral fluor, CaF2. In most of these, the acid is the important part of the mineral. It is only the carbonate which is used as a source of lime. Lime, in addition to its use in mortars and cements, is valuable as a flux in metallurgical operations and as a base in chemical work on a large scale. A mixture of lime and magnesia is used in the manufacture of basic fire bricks. Carbonate of lime, on ignition, especially when in contact with reducing substances, loses carbonic acid and becomes lime. This is known as quicklime. On treatment with water, it becomes hot, expands, and falls to a powder of slaked lime or calcium hydrate, CaH2O2. The hydrate is slightly soluble in water, note 0.1368 gram in 100 cc's, end note, forming an alkaline solution known as lime water. Calcium hydrate is more generally used suspended in water as milk of lime. As a flux, it is used either as limestone or as quicklime. Silica forms with lime a compound calcium silicate, which is not very fusible, but when alumina and other oxides are present, as in clays and in most rocky substances, the addition of lime gives a very fusible slag. Detection. Calcium is detected by the reddish colour which its salts impart to the flame. It is best to moisten with hydrochloric acid, note, or in the case of some silicates, to treat with ammonium fluoride, end note, before bringing the substance into the flame. When seen through a spectroscope, it shows a large number of lines, of which a green and an orange are most intense and characteristic. Calcium is detected in solution, note, after removal of the metals by treatment with sulphuretted hydrogen and ammonium sulphide, end note, by boiling with ammonium oxalate and ammonia. The lime is completely thrown down as a white precipitate. Lime is distinguished from the other alkaline earths by forming a sulphate insoluble in dilute alcohol, but completely soluble in a boiling solution of ammonium sulphate. Lime compounds are for the most part soluble in water or in dilute hydrochloric acid. Calcium fluoride must be first converted into sulphate by evaporation in a platinum dish with sulfuric acid. Insoluble silicates are opened up by fusion with fusion mixture, as described under silica. Separation. The separation of lime is effected by evaporating with hydrochloric acid to separate silica, and by treating with sulphuretted hydrogen to remove the second group of metals. If the substance contains much iron, the solution is next oxidized by boiling with a little nitric acid, and the iron, alumina, etc. are removed as basic acetates. The filtrate is treated with ammonia and sulphuretted hydrogen and allowed to settle. The filtrate from this is heated to boiling, treated with a solution of ammonium oxalate in excess, boiled for 5 or 10 minutes, allowed to settle for half an hour, and filtered. The precipitate contains all the lime as calcium oxalate. Gravimetric determination. The precipitate of calcium oxalate is washed with hot water, dried, transferred to a weighed platinum crucible, and ignited at a temperature not above incipient redness. This ignition converts the oxalate into carbonate with evolution of carbonic oxide, which burns at the mouth of the crucible with a blue flame. Footnote: CaC2O4 yields CaCO3 plus CO. End footnote. Generally, a small quantity of the carbonate is at the same time converted into lime. To reconvert it into carbonate, moisten with a few drops of ammonic carbonate solution and dry in a water oven. Heat gently over a Bunsen burner, cool and weigh. The substance is calcium carbonate, CaCO3, and contains 56% of lime, CaO. It is a white powder and should show no alkaline reaction with moistened litmus paper. Where the precipitate is small, it is better to ignite strongly over the blowpipe and weigh directly as lime. With larger quantities, and when many determinations have to be made, it is easier to make the determination volumetrically. Volumetric methods. These are carried out either by dissolving the oxalate at once in dilute sulfuric acid and titrating with permanganate of potassium solution, or by calcining it to a mixture of lime and carbonate and determining its neutralizing power with the standard solutions of acid and alkali. Titration with permanganate of potassium solution. This solution is made by dissolving 5.643 grams of the salt in water and by diluting to 1 litre. 100 cc's are equivalent to 0.5 gram of lime. The solution is standardized by titrating a quantity of oxalic acid about equivalent to the lime present in the assay. 0.5 gram of lime is equivalent to 1.125 gram of crystallized oxalic acid. The standardizing may be done with iron. The standard found for iron multiplied by 0.5 gives that for lime. the process is as follows. The calcium oxalate, having been precipitated and washed as in the gravimetric process, is washed through the funnel into a flask with hot dilute sulphuric acid, boiled till dissolved, diluted to 200 c.c. with water and heated to about 80 degrees centigrade. The standard solution of permanganate is then run in, not too quickly and with constant shaking, until a permanent pink tinge is produced. The cc's used multiplied by the standard and divided by the weight of the substance taken will give the percentage of lime. Estimation of lime by alkalimetry. The methods of determining the amount of an alkali or base by means of a standard acid solution, or conversely of determining an acid by means of a standard alkaline solution, are so closely related that they are best considered under one head. The same standard solution is applicable for many purposes, and consequently it is convenient to make it of such strength that 1 litre of it shall equal an equivalent in grams of any of the substances to be determined. Such solutions are termed normal. For example, a solution of hydrochloric acid, note HCl equals 36.5, end note, containing 36.5 grams of real acid per litre would be normal, and of equivalent strength to a solution containing either 17 grams of ammonia, note NH3 equals 17, end note, or 40 grams of sodic hydrate, note NaHO equals 40, end note, per litre. It will be seen in these cases that the normal solution contains the molecular weight in grams per litre, and if solutions of these strengths be made, it will be found that they possess equal neutralizing value. If, now, a solution containing 98 grams of sulphuric acid, note H2SO4 equals 98, end note, per litre be made, it will be found to have twice the strength of the above solution, that is, 100 c.c. of the soda would only require 50 c.c. of the acid to neutralize it. The reason for this will be seen on inspecting the equations. NaHO plus HCl yields NaCl plus H2O. 2NaHO plus H2SO4 yields Na2SO4 plus 2H2O. Acids like sulphuric acid are termed bibasic, and their equivalent is only half the molecular weight. Thus, a normal solution of sulphuric acid would contain 49 grams, 98 divided by 2, of real acid per litre. Similarly, lime and most of the bases are bibasic, as may be seen from the following equations. Hence, their equivalent will be half the molecular weight. 2HCl plus CaO yields CaCl2 plus H2O. 2HCl plus MgO yields MgCl2 plus H2O. The standard normal solution of hydrochloric acid is made by diluting 100 c.c. of the strong acid to 1 litre with water. This will be approximately normal. In order to determine its exact strength, weigh up 3 grams of recently ignited pure sodium carbonate, or of the ignited bicarbonate. Transfer to a flask and dissolve in 200 c.c. of water. When dissolved, cool, tint faintly yellow with a few drops of a solution of methyl orange, and run in the standard acid from a burette till the yellow changes to a pink. Read off the number of cc's used and calculate to how much sodium carbonate 100 cc's of the acid are equivalent. If the acid is strictly normal, this will be 5.3 grams. It will probably be equivalent to more than this. Now, calculate how much strictly normal acid would be equivalent to the standard found. For example, suppose the standard found is 5.5 gram of sodium carbonate, then 5.3 to 5.5 is equivalent to 100 to X. Note where X is the quantity of normal acid required. End note. X equals 103.8 cc's. To get the acid of normal strength, we should then add 3.8 cc's of water to each 100 cc's of the standard solution remaining. Suppose there were left 930 cc's of the approximate acid. 35.3 cc's of water must be added and mixed. It should then be checked by another titration with pure sodium carbonate. The standard solution of semi-normal alkali. The best alkali for general purposes is ammonia, but since it is volatile, especially in strong solutions, it is best to make it of half the usual strength, or semi-normal. 1 litre of this will contain 8.5 grams of ammonia, NH3, and 100 cc's of it will just neutralise 50 cc's of the normal acid. Take 100 cc's of dilute ammonia and dilute with water to 1 litre. Run into a flask 50 cc's of the standard acid, tint with methyl orange, and run in from a burette the solution of ammonia till neutralised. Less than 100 cc's will probably be used. Suppose 95 cc's were required. There should have been 100, hence there is a deficiency of 5. Then for each 95 cc's of standard ammonia left, add 5 cc's of water and mix well. 100 cc's will now be equivalent to 50 cc's of the acid. As an example of the application of this method, we may take the determination of lime in limestone, marble, and similar substances. Determination of lime in limestone. Weigh up 1 gram of the dried sample and dissolve in 25 cc's of normal acid. Cool, dilute to 100 cc's, and titrate with the semi-normal solution of alkali, using methyl orange as an indicator. Divide the cc's of alkali used by 2, subtract from 25, and multiply by 0.028 to find the weight of lime. This method is not applicable in the presence of other carbonates or oxides, unless the weight of these substances be afterwards determined and due correction be made. End of section 34. Section 35 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 14. Alkaline Earths, Alkalies, Part 2. Strontia. Strontia, the oxide of strontium, SrO, occurs in nature as sulphate in the mineral celestine, SrSO4, and as carbonate in strontianite, SrCO3. It is found in small quantities in limestones, chalk, etc. Strontia is used in sugar refining and for the preparation of coloured lights. Detection. It is detected by the crimson colour which its compounds, when moistened with hydrochloric acid, impart to the flame. The spectrum shows a large number of lines, of which a red, an orange, and a blue are most characteristic. It resembles lime in many of its compounds, but is distinguished by the insolubility of its sulphate in a boiling solution of ammonium sulphate, and by the insolubility of its nitrate in alcohol. From baryta, which it also resembles, it is distinguished by not yielding an insoluble chromate in an acetic acid solution, by the solubility of its chloride in alcohol, and by the fact that its sulphate is converted into carbonate on boiling with a solution formed of 3 parts of potassium carbonate and 1 of potassium sulphate. It is got into solution in the same manner as lime. The sulphate should be fused with fusion mixture, extracted with water, and thoroughly washed. The residue will contain the strontia as carbonate, which is readily soluble in dilute hydrochloric or nitric acid. Separation. It is separated, after removal of the silica and metals, as described under lime, by adding ammonia and ammonia carbonate, and allowing to stand for some hours in a warm place. In the absence of baryta or lime, it is filtered off and weighed as strontium carbonate, which contains 70.17% of strontia. It is separated from baryta by dissolving in a little hydrochloric acid, adding ammonia in excess, and then acidifying with acetic acid and precipitating the baryta with potassium bichromate, as described under baryta. The strontia is precipitated from the filtrate by boiling for some time with a strong solution of ammonic sulphate and a little ammonia. 50 parts of ammonic sulphate are required for each part of strontia or lime present. The precipitate is filtered off and washed first with a solution of ammonic sulphate and then with alcohol. It is dried, ignited, and weighed as strontium sulphate. Gravimetric determination. The determination of strontia in pure solution is best made by adding sulphuric acid in excess and alcohol in volume equal to that of the solution. Allow to stand overnight, filter, wash with dilute alcohol, dry, ignite at a red heat, and weigh as sulphate, SrSO4. This contains 56.4% of strontia, SrO, or 47.7% of strontium. Baryta. Baryta, oxide of barium, BaO, commonly occurs in combination with sulphuric oxide in the mineral barytes, or heavy spar, BaSO4, and in combination with carbon dioxide in witherite, BaCO3. These minerals are not unfrequently found in large quantity, note, associated with galena and other metallic sulfides, end note, in lodes. Small isolated crystals of these are frequently found in mining districts. Barium is a constituent of certain mineral waters. The minerals are recognized by their high specific gravity and their crystalline form. Compounds of barium are often used by the assayer, more especially the chloride and hydrate. The salts are, with the exception of the sulphate, generally soluble in water or hydrochloric acid. In such solutions, sulphuric acid produces a white precipitate of baric sulphate, which is practically insoluble in all acids. The dioxide, BaO2, is used for the preparation of oxygen. On strong ignition, it gives up oxygen and is converted into baryta, BaO, which, at a lower temperature, takes up oxygen from the air, reforming the dioxide. Detection. Barium is detected by the green colour its salts, especially the chloride, give to the flame. This, viewed through the spectroscope, shows a complicated spectrum, of which two lines in the green are most easily recognised and characteristic. The salts of barium give no precipitate with sulphuretted hydrogen in either acid or alkaline solutions, but with sulphuric acid they at once give a precipitate which is insoluble in acetate of soda. In solutions rendered faintly acid with acetic acid, they give a yellow precipitate with bichromate of potash. These reactions are characteristic of barium. Baryta is got into solution in the manner described under lime, but in the case of the sulphate, the substance is fused with 3 or 4 times its weight of fusion mixture. The melt is extracted with water, washed, and the residue dissolved in dilute hydrochloric acid. Separation. The separation is thus effected. The solution in hydrochloric acid is evaporated to dryness, redissolved in hot dilute hydrochloric acid, and sulphuric acid is added to the solution till no further precipitate is formed. The precipitate is filtered off and digested with a solution of ammonium acetate or of sodium hyposulphite at 50 degrees or 60 degrees centigrade to dissolve out any lead sulphate. The residue is filtered off, washed, dried, and ignited. The ignited substance is mixed with 4 or 5 times its weight of fusion mixture and fused in a platinum dish over the blowpipe for a few minutes. When cold, it is extracted with cold water, filtered and washed. The residue is dissolved in dilute hydrochloric acid and, if necessary, filtered. The solution contains the barium as baric chloride, mixed perhaps with salts of strontium or lime. To separate these, ammonia is added till the solution is alkaline, and then acetic acid in slight excess. Chromate of baryta is then thrown down by the addition of bichromate of potash as a yellow precipitate. It is allowed to settle, filtered, and washed with a solution of acetate or of nitrate of ammonia. It is dried, ignited gently, and weighed. It is BaCrO4 and contains 60.47% of baryta. Gravimetric determination. The gravimetric determination of baryta, when lime and strontia are absent, is as follows. The solution, if it contains much free acid, is nearly neutralized with ammonia, and then diluted to 100 or 200 c.c. It is heated to boiling, and dilute sulphuric acid is added till no further precipitation takes place. The precipitate is allowed to settle for a few minutes, decanted through a filter, and washed with hot water, and afterwards dried, transferred to a porcelain crucible, and strongly ignited in the muffle or over the blowpipe for a few minutes. It is then cooled and weighed as sulphate of baryta, BaSO4. It contains 65.67% of baryta, BaO. In determining the baryta in minerals which are soluble in acid, it is precipitated direct from the hydrochloric acid solution, nearly neutralized with ammonia, by means of sulphuric acid. The precipitated baric sulphate is digested with a solution of ammonic acetate and filtered, washed, ignited, and weighed. Volumetric determination. The principle and mode of working of this is the same as that given under the sulphur assay, but using a standard solution of sulphuric acid instead of one of barium chloride. The standard solution of sulphuric acid is made to contain 32.02 grams of sulphuric acid, H2SO4, or an equivalent of a soluble alkaline sulphate per litre. 100 c.c. will be equal to 5 grams of baryta. 5 grams of the substance are taken, and the baryta they contain converted into carbonate, if necessary. The carbonate is dissolved in dilute hydrochloric acid. 10 grams of sodium acetate are added, and the solution, diluted to 500 c.c., is boiled and titrated in the manner described. Lead salts must be absent in the titration, and so must strontia and lime. Ferrous salts should be peroxidized by means of permanganate or chlorate of potash. Other salts do not interfere. Magnesia. Magnesia, the oxide of magnesium, MgO, occurs in nature in the rare mineral periclase, MgO, and hydrated as brucite, MgH2O2. As carbonate, it occurs in large quantity as magnesite, MgCO3, which is the chief source of magnesia. Mixed with carbonate of lime, it forms magnesian limestone and dolomite. It is present in larger or smaller quantity in most silicates, and the minerals serpentine, talc, steatite, and meerschaum are essentially hydrated silicates of magnesia. Soluble magnesian salts occur in many natural waters, more especially the sulphate and the chloride. Kieserite, MgSO4.H2O, occurs in quantity at Stassfurt and is used in the manufacture of Epsom salts. Detection. Magnesia is best detected in the wet way. Its compounds give no colour to the flame, and the only characteristic dry reaction is its yielding a pink mass when ignited before the blowpipe, after treatment with a solution of cobalt nitrate. In solution, it is recognized by giving no precipitate with ammonia or ammonic carbonate in the presence of ammonic chloride, and by giving a white crystalline precipitate on adding sodium phosphate or arsenate to the ammoniacal solution. Magnesia differs from the other alkaline earths by the solubility of its sulphate in water. Magnesia is dissolved by boiling with moderately strong acids. The insoluble compounds are fused with fusion mixture and treated as described under silicates. Separation. It is separated by evaporating the acid solution to dryness to render silica insoluble, and by taking up with dilute hydrochloric acid. The solution is freed from the second group of metals by means of sulphuretted hydrogen, and the iron, alumina, etc. are removed with ammonic chloride, ammonia, and ammonic sulfide. The somewhat diluted filtrate is treated first with ammonia and then with carbonate of ammonia in slight excess. It is allowed to stand for an hour in a warm place and then filtered. The magnesia is precipitated from the filtrate by the addition of an excess of sodium phosphate and ammonia. It is allowed to stand overnight, filtered, and washed with dilute ammonia. The precipitate contains the magnesia as ammonic magnesic phosphate. In cases where it is not desirable to introduce sodium salts or phosphoric acid into the assay solution, the following method is adopted. The solution, freed from the other alkaline earths by ammonium carbonate, is evaporated in a small porcelain dish with nitric acid. The residue, after removing the ammonic salts by ignition, is taken up with a little water and a few crystals of oxalic acid, transferred to a platinum dish, evaporated to dryness, and ignited. The residue is extracted with small quantities of boiling water and filtered off, while the insoluble magnesia is washed. The filtrate contains the alkalies. The residue is ignited and weighed as magnesia. It is MgO. Gravimetric determination. The solution containing the magnesia is mixed with chloride of ammonium and ammonia in excess. If a precipitate should form, more ammonic chloride is required. Add sodium phosphate solution in excess, stir, and allow to stand overnight. Filter and wash the precipitate with dilute ammonia. Dry, transfer to a platinum or porcelain crucible, and ignite, finally at intense redness. Cool and weigh. The substance is magnesic pyrophosphate, Mg2P2O7. and contains 36.04% of magnesia. Volumetric method. The magnesia having been precipitated as ammonic magnesic phosphate, which is the usual separation, its weight can be determined volumetrically by the method of titration described under phosphates. The same standard solution of uranium acetate is used. Its standard for magnesia is got by multiplying the standard for phosphoric oxide by 0.5493. For example, if 100 cc's are equivalent to 0.5 gram of phosphoric oxide, they will be equivalent to, note, 0.5 times 0.5493, end note, 0.2746 gram of magnesia. The method of working and the conditions of the titration are the same as for the phosphate titration. The quantity of substance taken for assay must not contain more than 0.1 or 0.2 gram of magnesia. After precipitating as ammonic magnesic phosphate with sodium phosphate and well washing with ammonia, it is dissolved in dilute hydrochloric acid, neutralized with ammonia, and sodic acetate and acetic acid are added in the usual quantity. The solution is boiled and titrated. Examination of a limestone. Silica and insoluble silicates. Take 1 gram of the dried sample and dissolve it in 10 cc's of dilute hydrochloric acid. Filter, wash, dry, and ignite the residue. Organic matter. If the residue insoluble in hydrochloric acid shows the presence of organic matter, it must be collected on a weighed filter and dried at 100 degrees. On weighing, it gives the combined weights of organic and insoluble matter. The latter is determined by igniting and weighing again. The organic matter is calculated by difference. Lime. Where but little magnesia is present, this is determined by titration with standard acid. Take 1 gram and dissolve it in 25 cc's of normal hydrochloric acid. Tint with methyl orange and titrate with semi-normal ammonia. Divide the quantity of ammonia used by 2, deduct this from 25, and multiply the remainder by 2.8. This gives the percentage of lime. Where magnesia is present, the same method is adopted, and the magnesia, which is separately determined, is afterwards deducted. The percentage of magnesia found is multiplied by 1.4, and the result is deducted from the apparent percentage of lime got by titrating. Magnesia. Dissolve 2 grams of the limestone in hydrochloric acid and separate the lime with ammonia and ammonium oxalate. The filtrate is treated with sodium phosphate and the magnesia is weighed as pyrophosphate or titrated with uranium acetate. Iron. Dissolve 2 grams in hydrochloric acid, reduce, and titrate with standard permanganate of potassium solution. This gives the total iron. The ferrous iron is determined by dissolving another 2 grams in hydrochloric acid and at once titrating with the permanganate of potassium solution. Manganese. Dissolve 20 grams in hydrochloric acid, nearly neutralise with soda, add sodium acetate, boil and filter. To the filtrate add bromine, boil and determine the manganese in the precipitate. See page 300. Reader's note in the section on manganese. End reader's note. Phosphoric oxide. This is determined by dissolving the ferric acetate precipitate from the manganese separation in hydrochloric acid, adding ammonia in excess, and passing sulphuretted hydrogen. Filter and add to the filtrate magnesia mixture. The precipitate is collected, washed with ammonia, ignited, and weighed as pyrophosphate. The alkalies. The oxides of sodium, potassium, lithium, cesium, and rubidium, and ammonia are grouped under this head. Of these, cesia and rubidia are rare, and lithia comparatively so. They are easily distinguished by their spectra. They are characterized by the solubility of almost all their salts in water, and consequently are found in the solutions from which the earths and oxides of the metals have been separated by the usual group reagents. The solution from which the other substances have been separated is evaporated to dryness, and the product ignited to remove the ammonic salts added for the purpose of separation. The residue contains the alkali metals generally as chlorides or sulphates. Before determining the quantities of the particular alkali metals present, it is best to convert them altogether either into chloride or sulphate, and to take the weight of the mixed salts. It is generally more convenient to weigh them as chlorides. They are converted into this form, if none of the stronger acids are present, by simply evaporating with an excess of hydrochloric acid. Nitrates are converted into chlorides by this treatment. When sulphates or phosphates are present, the substance is dissolved in a little water, and the sulphuric or phosphoric acid precipitated with a slight excess of acetate of lead in the presence of alcohol. The solution is filtered, and the excess of lead precipitated with sulphuretted hydrogen. The filtrate from this is evaporated to dryness with an excess of hydrochloric acid, and the residue, consisting of the mixed chlorides, is gently ignited and weighed. In many cases, such as the analysis of slags and of some natural silicates, where the percentage of alkalis is small, the percentage of soda and potash, which most commonly occur, need not be separately determined. It is sufficient to report the proportion of mixed alkalis, which is thus ascertained. Dissolve the ignited and weighed chlorides in 100 c.c. of distilled water, and titrate with the standard solution of silver nitrate, using potassic chromate as indicator, in the manner described under chlorine. The cc of silver nitrate used gives the weight in milligrams of the chlorine present. Multiply this by 0.775 and deduct the product from the weight of the mixed chlorides. This will give the combined weight of the alkalis Na2O and K2O present. For example, 0.0266 gram of mixed chlorides required on titrating 14.2 c.c. of silver nitrate, which is equivalent to 0.0142 gram of chlorine. This, multiplied by 0.775, gives 0.0110 to be deducted from the weight of the mixed chlorides. Mixed chlorides 0.0266 gram, deduction 0.0110 gram, result mixed alkalis 0.0156 gram. Assuming this to have been got from 1 gram of a rock, it would amount to 1.56% of potash and soda. The relative proportions of the potash and soda can be ascertained from the same determination. Sodium and potassium chloride have the following composition: sodium 39.38, chlorine 60.62, total 100.00, potassium 52.46, chlorine 47.54, total 100.00. The percentage of chlorine in the mixed chlorides is calculated. It necessarily falls somewhere between 47.5 and 60.6%, and approaches the one or the other of these numbers as the proportion of the sodium or potassium preponderates. Each percent of chlorine in excess of 47.5 represents 7.63% of sodium chloride in the mixed chlorides. The percentage of potash and soda in the substance can be calculated in the usual way. Sodium chloride multiplied by 0.5302 gives its equivalent of soda, Na2O, and potassium chloride multiplied by 0.6317 gives its equivalent of potash, K2O. The weight of sodium chloride in the mixed chlorides is also calculated thus. Take the same example for illustration. Multiply the chlorine found by 2.103. This gives bracket 0.0142 times 2.103 close bracket equals 0.02987. From the product, deduct the weight of the mixed chlorides found. Product 0.02987, mixed chlorides 0.02660, difference 0.00327. The difference multiplied by 3.6288 gives the weight of sodium chloride in the mixture. In this case it equals 0.0118 gram. The potassium chloride is indicated by the difference between this and the weight of the mixed chlorides. It equals 0.0148 gram. We have now got sodium chloride 0.0118 gram, potassium chloride 0.0148 gram, from 1 gram of the rock taken. Multiplying these by their factors, we have, note soda equals 0.0118 times 0.5302, potash 0.0148 times 0.6317, end note. Soda equals 0.625%, potash equals 0.935%. Concentration of the alkalis. With the exception of magnesia, all the other bases are separated from the alkalis in the ordinary course of work, without the addition of any reagent which cannot be removed by simple evaporation and ignition. Consequently, with substances soluble in acids, successive treatment of the solution with sulphuretted hydrogen, ammonia, ammonic sulfide, and ammonic carbonate, filtering where necessary, will yield a filtrate containing the whole of the alkalis with ammonic salts and, perhaps, magnesia. The filtrate is evaporated in a small porcelain dish with the addition of nitric acid towards the finish. It is carried to dryness and ignited. The residue is taken up with a little water, treated with a few crystals of oxalic acid, and again evaporated and ignited. The alkaline salts are extracted with water and filtered from the magnesia into a weighed platinum dish. The solution is then evaporated with an excess of hydrochloric acid, ignited at a low red heat, and weighed. The residue consists of the mixed alkaline chlorides. For substances, such as most silicates and similar bodies, not completely decomposed by acids, Lawrence-Smith's method is generally used. This is as follows. Take from 0.5 to 1 gram of the finely powdered mineral and mix, by rubbing in the mortar, with an equal weight of ammonium chloride. Then mix with 8 times as much pure calcium carbonate, using a part of it to rinse out the mortar. Transfer to a platinum crucible and heat gently over a Bunsen burner until the ammonic chloride is decomposed, 5 or 10 minutes. Raise the heat to redness and continue at this temperature for about 3/4 of an hour. The crucible must be kept covered. Cool and turn out the mass into a 4-inch evaporating dish. Wash the crucible and cover with distilled water and add the washings to the dish. Dilute to 60 or 80 cc and heat to boiling. Filter and wash. Add to the filtrate about 1.5 gram of ammonium carbonate. Evaporate to about 40 cc and add a little more ammonic carbonate and some ammonia. Filter into a weighed platinum dish and evaporate to dryness. Heat gently to drive off the ammonic chloride and ignite to a little below redness. Cool and weigh. The residue consists of the mixed alkaline chlorides. Separation of the alkali metals from each other. Sodium and lithium are separated from the other alkali metals by taking advantage of the solubility of their chlorides in the presence of platinic chloride, and from one another by the formation of an almost insoluble lithic phosphate on boiling with a solution of sodium phosphate in a slightly alkaline solution. Cesium, rubidium and potassium yield precipitates with platinic chloride which are somewhat soluble and must be precipitated from concentrated solutions. Cesium and rubidium are separated from potassium by fractional precipitation with platinum chloride. Their platinochlorides, being less soluble than that of potassium, are precipitated first. 100 parts of boiling water dissolve 5.18 of the potassium platinochloride, 0.634 of the rubidium salt, and 0.377 of the corresponding cesium compound. The separation of lithium, cesium and rubidium is seldom called for owing to their rarity. The details of the separation of potassium from sodium are described under potassium. Ammonia compounds are sharply marked off from the rest by their volatility, and it is always assumed that they have been removed by ignition. If left in the solution, they would count as potassium compounds. They will be considered under ammonia. End of section 35. Section 36 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 14. Earths, Alkaline Earths, Alkalies, Part 3. Sodium. Sodium is the commonest of the alkali metals. It is found in nature chiefly combined with chlorine as common salt, NaCl. This mineral is the source from which the various compounds of sodium in use are prepared. Sodium occurs abundantly as nitrate, NaNO3, in Chile saltpeter, and as silicate in various minerals, such as albite or soda feldspar. It occurs as fluoride in cryolite, Na3AlF6, and as carbonate in natron, etc. Sulphates are also found. Sodium is very widely diffused, few substances being free from it. The detection of sodium is easy and certain, owing to the strong yellow colour its salts impart to the flame. This, when viewed by the spectroscope, shows a single yellow line. Footnote, resolved into two with a powerful spectroscope. End footnote. The extreme delicacy of this test limits its value because of the wide diffusion of sodium salts. It is more satisfactory to separate the chloride, which may be recognized by its taste, flame coloration, fusibility, and negative action with reagents. The chloride dissolved in a few drops of water gives, with potassium metantimoniate, a white precipitate of the corresponding sodium salt. Sodium salts are dissolved out from most compounds on treatment with water or dilute acids. Insoluble silicates are decomposed and the alkali rendered soluble by Lawrence Smith's method, which has just been described. The separation of the sodium from the mixed chlorides is effected in the following way. The chlorides are dissolved in a little water and the potassium separated as platinochloride. The soluble sodium platinochloride, with the excess of platinum, is boiled, mixed with sulphuric acid, evaporated to dryness, and ignited. On extracting with water, filtering, evaporating, and igniting, sodium sulphate is left, and is weighed as such. It is more usual, and quite as satisfactory, to calculate the weight of the sodium chloride by difference from that of the mixed chlorides, by subtracting that of the potassium chloride, which is separately determined. For example, 1 gram of a rock gave mixed chlorides 0.0266 gram and 0.0486 gram of potassic platinochloride. This last is equivalent to 0.0149 gram of potassium chloride. Mixed chlorides found 0.0266. Deduct potassium chloride 0.0149, leaves sodium chloride 0.0117. The weight of sodium chloride found multiplied by 0.5302 gives the weight of the soda, Na2O. Gravimetric determination. The solution, which must contain no other metal than sodium, is evaporated in a weighed platinum crucible or dish. Towards the finish, an excess, not too great, of sulphuric acid is added, and the evaporation is continued under a loosely fitting cover. The residue is ignited over the blowpipe, a fragment of ammonic carbonate being added towards the end, when fumes of sulphuric acid cease to be evolved. This ensures the removal of the excess of acid. The crucible is cooled in the desiccator and weighed. The substance is sulphate of soda, Na2SO4, and contains 43.66% of soda, Na2O, or 32.38% of sodium, Na. Volumetric methods. There are various methods used for the different compounds of sodium. There is no one method of general application. Thus, with common salt, the chlorine is determined volumetrically, and the sodium, after deducting for the other impurities, is estimated by difference. With sodic carbonate and caustic soda, a given weight of the sample is titrated with standard acid, and the equivalent of soda estimated from the alkalinity of the solution. With sodium sulphate, a modification of the same method is used. To a solution of 3.55 grams of the salt contained in a half-litre flask, 250 cc of a solution of baryta water is added. The volume is made up to 500 cc with water. The solution is mixed and filtered. Half of the filtrate is measured off, treated with a current of carbonic acid, and then boiled. It is transferred to a half-litre flask, diluted to the mark, shaken up, and filtered. 250 cc of the filtrate, representing a quarter of the sample taken, is then titrated with standard acid. The standard acid is made by diluting 250 cc of the normal acid to 1 litre. The cc's of acid used, multiplied by 2, gives the percentage. A correction must be made to counteract the effect of impurities in the baryta, as well as errors inherent in the process. This is small, and its amount is determined by an experiment with 3.55 grams of pure sodium sulphate. Examination of common salt. Moisture. Powder and weigh up 10 grams of the sample into a platinum dish. Dry in a water oven for an hour, and afterwards heat to bare redness over a Bunsen burner. Cool and weigh. The loss gives the water. Chlorine. Weigh up 2 separate lots of 1 gram each. Dissolve in 100 cc of water and determine the chlorine by titrating with the standard silver nitrate solution, using chromate of potash as indicator. See chlorine. Insoluble matter. Dissolve 10 grams of the salt in water with the help of a little hydrochloric acid. Filter off the sediment, wash, ignite, and weigh. This residue is chiefly sand. Dilute the filtrate to 500 cc. Lime. Take 250 cc of the filtrate, render ammoniacal, and add ammonium oxalate. Wash, dry, and ignite the precipitate. Weigh as lime, CaO. Magnesia. To the filtrate from the lime, add phosphate of soda. Allow to stand overnight, filter, wash with dilute ammonia, dry, ignite, and weigh as pyrophosphate. Sulphuric oxide. To the remaining 250 cc of the filtrate from the insoluble, add an excess of barium chloride. Collect, wash, dry, ignite, and weigh the barium sulphate. Sodium. It is estimated by difference. The following may be taken as an example. Moisture, 0.35. Insoluble matter, 0.40. Lime, 0.40. Magnesia, 0.05. Sulphuric oxide, 0.60. Chlorine, 59.60. Sodium, 38.60. Total, 100.00. Potassium. Potassium occurs in nature as chloride in the mineral sylvine, KCl, and more abundantly combined with magnesium chloride in carnallite, KCl.MgCl2.6H2O. It occurs as nitrate in niter, KNO3, and as silicate in many minerals, such as orthoclase, or potash felspar, and muscovite, or potash mica. Potassium compounds are detected by the characteristic violet colour they impart to the flame. The presence of sodium salts masks this tint, but the interference can be neutralised by viewing the flame through a piece of blue glass. Viewed through the spectroscope, it shows a characteristic line in the red and another in the violet. These, however, are not so easy to recognise or obtain as the sodium one. Concentrated solutions of potassium salts give a yellow crystalline precipitate with platinum chloride, and a white crystalline one with the acid tartrate of soda. For these tests, the solution is best neutral. These tests are only applicable in the absence of compounds other than those of potassium and sodium. Gravimetric determination. This process serves for its separation from sodium. Take 1 gram of the sample and dissolve it in an evaporating dish with 50 c.c. of water. Acidify with hydrochloric acid in quantity sufficient, if the metals are present as chlorides, to make it acid, or if other acids are present, in at least such quantity as will provide the equivalent of chlorine. Add 3 grams of platinum in solution as platinum chloride, and evaporate on a water bath to a stiff paste, but not to dryness. Moisten with a few drops of platinic chloride solution without breaking up the paste by stirring. Cover with 20 c.c. of strong alcohol, and wash the crystals as much as possible by rotating the dish. Allow to settle for a few moments and decant through a filter. Wash in the same way 2 or 3 times, until the colour of the filtrate shows that the excess of the platinum chloride used is removed. Wash the precipitate onto the filter with a jet of alcohol from the wash bottle. Clean the filter paper, using as little alcohol as possible. Dry in the water oven for an hour. Brush the precipitate into a weighed dish and weigh it. It is potassium platinochloride, K2PtCl6, and contains 16.03% of potassium, or 30.56% of potassium chloride, KCl, which is equivalent to 19.3% of potash, K2O. If the filter paper is not free from precipitate, burn it and weigh separately. The excess of weight over that of the ash will be due to platinum and potassic chloride, Pt and 2KCl. This multiplied by 1.413 will give the weight of the potassic platinochloride from which it was formed. It must be added to the weight of the main precipitate. The mixed alkaline chlorides obtained in the usual course of analysis are treated in this manner. The quantity of platinum added must be about 3 times as much as the mixed chlorides weigh. Volumetric methods. These are the same as with soda. Examination of commercial carbonate of potash. The impurities to be determined are moisture, silica and insoluble matter, chlorine, sulphuric oxide and oxide of iron. These determinations are made in the ways described under the examination of common salt. The potassium is determined by converting it into chloride and precipitating with platinum chloride, etc., as just described. Available alkali. Weigh up 23.5 grams of the sample, dissolve in water and make up to 500 c.c. Take 50 c.c., tint with methyl orange and titrate with the normal solution of acid. The c.c. of acid used multiplied by 2 gives the percentage of available alkali calculated as potash, K2O. Soda. This is calculated indirectly in the following way. Deduct from the potassium found the quantity required for combination with the chlorine and sulphuric oxide present, and calculate the remainder to potash, K2O. The apparent surplus excess of available alkali is the measure of the soda present. Carbon dioxide. The cc of acid used in the available alkali determination multiplied by 2.2 and divided by 2.35 gives the percentage of carbon dioxide. Lithium. Lithia, the oxide of lithium, Li2O, occurs in quantities of 3 or 4% in various silicates, such as lepidolite or lithia mica, spodumene, and petalite. It also occurs as phosphate in triphtylene. it is a constituent of the water of certain mineral springs. A spring at Wheal Clifford contained as much as 0.372 gram of lithium chloride per litre. In small quantities, lithia is very widely diffused. The detection of lithia is rendered easy by the spectroscope. Its spectrum shows a red line lying about midway between the yellow sodium line and the red one of potassium. It also shows a faint yellow line. The colour of the flame, a crimson, is characteristic. The reactions of the lithium compounds lie between those of the alkalis and of the alkaline earths. Solutions are not precipitated by tartaric acid nor by platinic chloride. The oxide is slowly soluble in water. The carbonate is not freely soluble. Lithia is completely precipitated by sodic phosphate, especially in hot alkaline solutions. In its determination, the mixed alkaline chlorides obtained in the separation of the alkalis are dissolved in water, a solution of soda is added in slight excess, and the lithia precipitated with sodic phosphate. Before filtering, it is evaporated to dryness and extracted with hot water rendered slightly ammoniacal. The residue is transferred to a filter, dried, ignited, and weighed. The precipitate is lithium phosphate, 3Li2O, P2O5, and contains 38.8% of lithia. The separation of lithia from magnesia is not given by the usual authorities. Wohler recommends evaporating the solution to dryness with carbonate of soda. On extracting the residue with water, the lithia dissolves out and is determined in the filtrate. 100 parts of water dissolve at the ordinary temperature 0.769 parts of lithium carbonate, Li2CO3. The basic magnesia compound is almost insoluble in the absence of carbon dioxide and ammonium salts. Cesium. The oxide of cesium, cesia, Cs2O, is found associated with lithia in lepidolite, etc., and together with rubidium in many mineral waters. The mineral pollux is essentially a silicate of alumina and cesia. It contains 34.0% of the latter oxide. Cesium is best detected by the spectroscope, its spectrum being characterized by 2 lines in the blue and 1 in the red. The latter is about midway between the lithium and sodium lines. If not detected by the spectroscope, or specially looked for, cesia would in the ordinary course of work be separated with the potash and weighed as potassium platinochloride. Cesia is separated from all the other alkalis by adding to the acid solution of the mixed chlorides a strongly acid cold solution of antimonious chloride. The acid used must be hydrochloric. The cesium is precipitated as a white crystalline precipitate, CsCl.SbCl3, which is filtered off and washed when cold with strong hydrochloric acid, since it is decomposed by water or on warming. The precipitate is washed into a beaker and treated with sulphuretted hydrogen. After filtering off the sulphide of antimony, the solution leaves on evaporation the cesium as chloride. Rubidium. Rubidium occurs widely diffused in nature, but in very small quantities. It is generally associated with cesium. It is detected by the spectroscope, which shows 2 violet lines and 2 dark red ones. Like cesium, it is precipitated with platinic chloride, and in the ordinary course of work would be weighed as potassium. It is separated from potassium by fractional precipitation with platinic chloride. Rubidium platinochloride is much less soluble than the potassium salt. Ammonium. It is usual to look upon the salts of ammonia as containing a compound radical, note NH4 equals Am, endnote, which resembles in many respects the metals of the alkalis. Ammonium occurs in nature as chloride in sal ammoniac, AmCl, as sulphate in mascagnine, Am2SO4, as phosphate in struvite, AmMgPO4.12H2O. Minerals containing ammonium are rare and are chiefly found either in volcanic districts or associated with guano. Ammonia and ammonium sulphide occur in the waters of certain Tuscan lagoons, which are largely worked for the boracic acid they contain. The crude boracic acid from this source contains from 5 to 10% of ammonium salts. It is from these that the purer forms of ammonium compounds of commerce, known as from volcanic ammonia, are derived. But the bulk of the ammonia of commerce is prepared from the ammoniacal liquors obtained as byproducts in the working of certain forms of blast furnaces and coke ovens, and more especially in gas making. Ammonia hardly comes within the objects of assaying, but it is largely used in the laboratory, and the assayer is not unfrequently called on to determine it. Ammonium salts are mostly soluble in water. In strong solutions they give a yellow precipitate of ammonium platinochloride on the addition of chloride of platinum, and with the acid tartrate of soda yield a white precipitate of hydric ammonic tartrate. These reactions are similar to those produced with potassium compounds. Heated with a base such as lime or sodic hydrate, ammonium salts are decomposed, yielding ammonia gas, NH3, which is readily soluble in water. The solution of this substance is known as ammonic hydrate or ammonia. They are volatilized on ignition, either with or without decomposition, according to the acid present. This fact is of importance in analytical work, since it allows of the use of alkaline solutions and reagents, which leave nothing behind on heating. It must be remembered, however, that although ammonic chloride is volatile, it cannot be volatilized in the presence of substances which form volatile chlorides without loss of the latter. For example, ferric oxide and alumina are thus lost, volatilizing as chlorides, and there are some other compounds, notably ammonic magnesic arsenate, which on heating to redness suffer reduction. The presence of ammonic chloride in such cases must be avoided. Detection. Compounds of ammonium are detected by their evolving ammonia when mixed or heated with any of the stronger bases. The ammonia is recognized by its odor, by its alkaline reaction with litmus paper, and by yielding white fumes when brought in contact with fuming acid. In consequence of the use of ammonium salts and ammonia as reagents, it is necessary to make a special test for and determination of ammonium. Footnote: ammonium compounds are frequently produced when dissolving metals in nitric acid, or when nitrates are heated in the presence of the metals. End footnote. In the ordinary course of work it will be lost on ignition. The determination presents little difficulty and is based on the method used for its detection. Solution and separation. Although ammonium salts are soluble in water, there is no necessity for dissolving them. The compound containing the ammonia is boiled with an alkaline solution, and the liberated ammonia condensed and collected. The substance is weighed out into a flask of about 200 cc capacity. The flask is closed with a rubber cork perforated to carry a 20 cc pipette and a bulb exit tube. The latter is connected with a receiver, which is a small flask containing dilute hydrochloric acid. Figure 61. Reader's note. Figure 61 shows two round bottom flasks, one on a retort stand over a Bunsen burner, the other on the bench beside it. They are connected by a glass tube running from high up in the upper flask to below the liquid level in the lower flask. In the upper flask, the stem of a bulb pipette passes through the flask's stopper into the liquid in the flask. The upper stem of the pipette is closed with a tap. In the lower flask, there is an outlet tube to handle expanding gas, with a Z bend in it. End reader's note. The flask containing the substance is corked, and the greater part of the soda solution is run in from the pipette. The solution is then boiled. The ammonia volatilizes and is carried over into the hydrochloric acid, with which it combines to form ammonic chloride. The distillation is carried on gently until the bulk of the liquid is driven over. The ammonia in the receiver will be mixed only with the excess of hydrochloric acid. This separation is used in all determinations. Gravimetric determination. The contents of the flask are transferred to a weighed platinum dish and evaporated on the water bath. It is dried until the weight is constant. the chloride of ammonium remains as a white mass which, after cooling in a desiccator, is weighed. It contains 33.72% of ammonium, NH4, or 31.85% of ammonia, NH3. On heating over the Bunsen burner, it is completely volatilized, leaving no residue. Volumetric determination. Weigh up 1.7 gram of the substance and place it in the flask. Measure off 50 c.c. of the normal solution of acid, place them in the receiver, and dilute with an equal volume of water. Run in through the pipette, by opening the clip, 20 c.c. of a strong solution of soda. Boil until the ammonia has passed over, and then aspirate a current of air through the apparatus. Disconnect the receiver and tint its contents with methyl orange. Titrate the residual acid with a semi-normal solution of alkali. Divide the cc's of the alkali solution used by 2 and deduct from the 50 cc's. The difference will give the number of cc's of the normal acid solution neutralized by the ammonia distilled over. Each cc of acid so neutralized represents 1% of ammonia in the sample. If the results are to be reported as ammonium, 1.8 gram of the sample is taken instead of 1.7. Colorimetric determination. This is effected by means of Nessler's reagent, which strikes a brown colour with traces of ammonia, even with a few hundredths of a milligram in 100 cc of liquid. With larger quantities of ammonia, the reagent gives a precipitate. This reagent is a strongly alkaline solution of potassic mercuric iodide and is thus made. Nessler's solution. Dissolve 17 grams of mercuric chloride in 300 c.c. of water and add the solution to one of 35 grams of potassium iodide in 100 c.c. of water until a permanent precipitate is produced. Both solutions must be cold. Then make up to a litre by adding a 20% solution of potash. Add more of the mercuric chloride, a little at a time, until a permanent precipitate is again formed. Allow to settle, decant, and use the clear liquor. 4 or 5 cc's are used for each 100 cc's of liquid to be tested. A standard solution of ammonia is made by dissolving 0.315 gram of ammonic chloride in water and diluting to 100 cc's. 10 cc's of this are taken and diluted to 1 litre. 1 cc contains 0.01 milligram of ammonia, NH3. In working, the solution containing the ammonia is diluted to a definite volume and to such an extent that 50 cc's of it shall not contain more than 0.02 or 0.03 milligram of ammonia. 50 cc's of it are transferred to a Nessler glass and mixed with 2 cc's of Nessler's reagent. The colour is noted and an estimate made as to the amount of ammonia it indicates. A measured quantity of the standard ammonia, judged to contain about as much ammonia as that in the assay, is then put into another Nessler glass. It is diluted to 50 cc's with water and mixed with 2 cc's of Nessler. After standing a minute or two, the colours in the 2 glasses are compared. If the tints are equal, the assay is finished, but if the standard is weaker or stronger than the assay, another standard containing more or less ammonia, as the case may be, must be prepared and compared with the assay. 2 such experiments will generally be sufficient, but if not, a third must be made. The addition of more standard ammonia to the solution to which the Nessler has already been added does not give a satisfactory result. When the ammonia in 50 cc's has been determined, that in the whole solution is ascertained by a suitable multiplication. By 10, for example, if the bulk was 500 cc's, or by 20 if it was a litre. Distilled water is used throughout. It must be free from ammonia, and is best prepared by distilling an ammonia-free spring water. End of section 36. Section 38 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 15. Oxygen and Oxides. The Halogens. Water. Water occurs in minerals in two forms, free and combined. The term moisture ought strictly to be limited to the first, although, as has already been explained, it is more convenient in assaying to apply the term to all water which is driven off on drying at 100 degrees centigrade. The combined water is really a part of the mineral itself, although it may be driven off at a high temperature, which varies with the base. In some cases a prolonged red heat is required, whilst with crystallized salts it is sometimes given off at the ordinary temperatures. This latter phenomenon, known as efflorescence, is mostly confined to artificial salts. The determination of the combined water may often be made by simply igniting the substance from which the moisture has been removed. The quantity of water may be determined either indirectly by the loss, or directly by collecting it in a calcium chloride tube and weighing. In some cases, in which the loss on ignition does not give simply the proportion of combined water, it can be seen from the analysis to what else the loss is due, and after a proper deduction the amount of water can be estimated. For example, 1 gram of crystallized iron sulfate was found to contain on analysis 0.2877 gram of sulphuric oxide, and on igniting another gram, 0.2877 gram of ferric oxide was left. As the salt is known to be made up of ferrous oxide, sulphuric oxide, and combined water, the combined water can be thus calculated. 0.2877 gram of ferric oxide is equal to 0.2589 gram of ferrous oxide. Footnote: Fe2O3 to Fe2O is equivalent to 0.287 to 0.2589. End footnote. And consequently the loss on ignition has been diminished by 0.0288 gram, which is the weight of oxygen absorbed by the ferrous oxide during calcining. The loss on ignition was 0.7123 gram, to which must be added 0.0288 gram. Hence 0.7411 gram is the weight of the combined sulphuric oxide and water present. Deducting the weight of sulphuric oxide found, 0.2877 gram, there is left for combined water 0.4534 gram. The composition of 1 gram of the dry salt is then water 0.4534, sulphuric oxide 0.2877, ferrous oxide 0.2589, total 1.0000. The following is another example. A sample of malachite lost on ignition 28.47%, leaving a residue which was found on analysis to be made up of oxide of copper, note, equal to 70.16% on the mineral, end note, and silica and oxide of iron, note, equal to 1.37%, end note. Carbon dioxide and water, but nothing else, was found to be present, and the carbon dioxide amounted to 19.64%. Deducting this from the loss on ignition, we have 8.82 as the percentage of water present. The analysis was then reported as follows: cupric oxide 70.16, equal to 56.0%, copper; silica and ferric oxide 1.37, carbon dioxide 19.64, water 8.82, total 99.99. Direct determination of combined water. Transfer about 3 grams of the substance to a piece of combustion tube, 8 or 10 inches long, attached, as in figure 63, at one end to a U-tube containing sulphuric acid, and at the other end to a calcium chloride tube. The last is weighed previous to the determination. The tube should be warmed to ensure complete dryness, and must be free from a misty appearance. Aspirate a current of air through the apparatus. Heat the mineral by means of a Bunsen burner, cautiously at first, and afterwards to redness, if necessary. The water is driven off and condenses in the calcium chloride tube, which is afterwards cooled and weighed. The increase in weight is due to the water. If the substance gives off acid products on heating, it is previously mixed with some dry oxide of lead or pure calcined magnesia. Reader's note: Figure 63 shows a horizontal combustion tube over a Bunsen burner. At the left end, air enters via two U-tubes, and at the right end leaves via a single U-tube. The leftmost U-tube has 3 bulbs at the base, with presumably sulphuric acid in. The second U-tube is not mentioned in the text and presumably contains calcium chloride to complete the dehydration of the incoming air. The U-tube at the right contains the weighed calcium chloride for the absorption of water. End reader's note. Examination of water. The assayer is occasionally called on to test water for the purpose of ascertaining the nature and quantity of the salts contained in it, and whether it is or is not fit for technical and drinking purposes. In mineral districts, the water is generally of exceptional character, being more or less charged not only with earthy salts, but also frequently with those of the metals. Distilled water is only used by assayers in certain exceptional cases, so that by many it would be classed among the rarer oxides. Water of ordinary purity will do for most purposes, but the nature and quantity of the impurities must be known. The following determinations are of chief importance. Total solids at 100 degrees centigrade. Where simply the amount is required, take 100 cc and evaporate on the water bath in a weighed dish, then dry in the water oven and weigh. Total solids ignited. The above residue is very gently ignited, keeping the heat well below redness, and again weighed. A larger loss than 4 or 5 parts per 100,000 on the water requires an explanation. Chlorine. Take 100 cc of the water in a porcelain dish, add 2 cc of a 5% solution of neutral potassic chromate, and titrate with a neutral standard solution of nitrate of silver, made by dissolving 4.789 grams of crystallized silver nitrate in distilled water and diluting to 1 litre. The addition of the nitrate of silver is continued until the yellow of the solution assumes a reddish tint. The reaction is very sharp. Each cc of nitrate of silver used is equal to 1 part by weight of chlorine in 100,000 of water. At inland places this rarely amounts to more than 1 in 100,000, but near the sea it may amount to 3 or 5. More than this requires explanation, and generally indicates sewage pollution. Nitric pentoxide, N2O5. It is more generally reported under the heading nitrogen as nitrates. Take 250 cc of the water and evaporate to 2 or 3 cc. Acidulate with a few drops of dilute sulphuric acid and transfer to a nitrometer, using strong sulphuric acid to wash in the last traces. The sulphuric acid must be added to at least twice the bulk of the liquid. Shake up with mercury. The mercury rapidly flours and nitric oxide is given off if any nitrate is present. The volume of the nitric oxide, corrected to normal temperature and pressure, multiplied by 0.25, gives the parts of nitrogen per 100,000, or multiplied by 0.965 will give the nitric pentoxide in parts per 100,000. In well and spring waters, the nitrogen may amount to 0.3 or 0.4 parts per 100,000, or in richly cultivated districts, 0.7 or 0.8 parts per 100,000. An excess of nitrates is a suspicious feature and is generally due to previous contamination. Ammonia. Take 500 cc of the water and place them in a retort connected with a Liebig's condenser. Add a drop or two of a solution of carbonate of soda and distill over 100 cc. Collect another 50 cc separately. Determine the ammonia in the distillate colorimetrically with Nessler's solution as described under ammonia, and compare with the standard solution of ammonic chloride containing 0.0315 gram of ammonic chloride in 1 litre of water. 1 cc contains 0.01 milligram of ammonia. The second distillate will show little, if any, ammonia in ordinary cases. The amounts found in both distillates are added together and expressed in parts per 100,000. Waters, other than rain and tank waters, which contain more than 0.003 per 100,000 are suspicious. Organic matter. The organic matter cannot be determined directly, but for ordinary purposes it may be measured by the amount of permanganate of potassium which it reduces, or by the amount of ammonia which it evolves on boiling with an alkaline permanganate of potassium solution. A. Albuminoid ammonia. To the residue left after distilling the ammonia, add 50 c.c. of a solution made by dissolving 200 grams of potash and 8 grams of potassium permanganate in 1,100 c.c. of water and rapidly boiling till the volume is reduced to 1 litre. Note: this should be kept in a well-stoppered bottle and be occasionally tested to see that it is free from ammonia. End note. Continue the distillation, collecting 50 c.c. at a time, until the distillate is free from ammonia. 3 or 4 fractions are generally sufficient. Determine the ammonia colorimetrically as before. If the total albuminoid ammonia does not exceed 0.005 in 100,000, the water may be regarded as clean as regards organic matter. If it amounts to more than 0.015, it is dirty. B. Oxygen consumed. A standard solution of permanganate of potash is made by dissolving 0.395 gram of the salt in water and diluting to 1 litre. Each cc equals 0.01 mg of available oxygen. The following are also required. 1. A solution of sodium hyposulphite containing 1 gram of the salt, note Na2S2O3.5H2O, end note, in 1 litre of water. 2. Dilute sulphuric acid, made by adding 1 part of the acid to 3 of water and titrating with the permanganate solution till a faint pink persists after warming for several hours. 3. Starch paste. 4. Potassium iodide solution. Take 250 c.c. of the water in a stoppered bottle. Add 10 c.c. of sulphuric acid and 10 c.c. of the permanganate and allow to stand in a warm place for 4 hours. Then add a few drops of the solution of potassium iodide and titrate the liberated iodine with hypo, using starch paste towards the end as an indicator. To standardize the hyposulphite, take 250 c.c. of water and 10 c.c. of sulphuric acid and a few drops of potassium iodide. Then run in 10 c.c. of the permanganate solution and again titrate. About 30 c.c. of the hypo will be used. The difference in the 2 titrations, divided by the last and multiplied by 10, will give the cc's of permanganate solution used in oxidizing the organic matter in the 250 c.c. of water. Each cc represents 0.04 parts of oxygen in 100,000. Metals. These may for the most part be estimated colorimetrically. Lead. Take 100 cc of the water in a Nessler tube and add 10 cc of sulphuretted hydrogen water, and compare the tint, if any, against a standard lead solution, as described under colorimetric lead. Report in parts per 100,000. Copper. Proceed as with the last mentioned metal, but if lead is also present, boil down 500 cc to about 50 cc, then add ammonia, filter, and estimate the copper in the blue solution, as described under colorimetric copper. Iron. Take 50 cc, or a smaller quantity if necessary, dilute up to the mark with distilled water, and determine with potassium sulfocyanate, as described under colorimetric iron. Zinc. Zinc is the only other metal likely to be present, and since it cannot be determined colorimetrically, it must be separately estimated during the examination of the total solids. Examination of total solids. Evaporate 500 cc to dryness with a drop or 2 of hydrochloric acid. Take up with hydrochloric acid, filter, ignite, and weigh the residue as silica. To the filtrate, add a little ammonic chloride and ammonia. Boil and filter, ignite, and weigh the precipitate as oxide of iron and alumina. Collect the filtrate in a small flask, add a few drops of ammonium sulphide, or pass sulphuretted hydrogen. Cork the flask and allow to stand overnight. Filter, wash, and determine the zinc gravimetrically as oxide of zinc. If copper or lead were present, they should have been previously removed with sulphuretted hydrogen in the acid solution. To the filtrate, add ammonic oxalate and ammonia. Boil for some time, allow to stand, filter, wash, ignite, and weigh as lime. Evaporate the filtrate with nitric acid and ignite. Take up with a few drops of dilute hydrochloric acid, add baric hydrate in excess, evaporate, and extract with water. The residue contains the magnesia. Boil with dilute sulphuric acid, filter, precipitate it with phosphate of soda and ammonia, and weigh as pyrophosphate. The aqueous extract contains the alkalies with the excess of barium. Add sulphuric acid in slight excess, filter, evaporate, and ignite strongly. The residue consists of the sulphates of the alkalies, which are separately determined as described under potash. Sulphuric oxide, SO3. Take 200 cc and boil to a small bulk with a little hydrochloric acid. Filter, if necessary. Add baric chloride solution in slight excess to the hot solution. Filter, ignite, and weigh as baric sulphate. Carbon dioxide, free. Carbon dioxide exists in waters in two forms, free and combined. The latter generally occurs as bicarbonate, although on analysis it is more convenient to consider it as carbonate and to count the excess of carbon dioxide with the free. The method is as follows. To determine the free carbon dioxide, take 100 cc of the water, place them in a flask with 3 cc of a strong solution of calcium chloride and 2 cc of a solution of ammonic chloride. Next, add 50 cc of lime water. The strength of the lime water must be known. Make up to 200 cc with distilled water, stop the flask, and allow the precipitate to settle. Take out 100 cc of the clear solution with a pipette and titrate with the standard solution of acid. Footnote: 100 cc contain 1 gram of sulphuric acid. End footnote. The number of cc's required multiplied by 2 and deducted from that required for the 50 cc of lime water and then multiplied by 0.0045 will give the carbon dioxide present other than as normal carbonates. Carbon dioxide combined as normal carbonate. 100 cc of the water are tinted with phenacetylene or lacmoid, then heated to near boiling and titrated with standard acid. The number of cc's used multiplied by 0.0045 will give the weight in grams of the combined carbon dioxide. Free acid. In some waters, especially those from mining districts, there will be no carbonates. On the contrary, there may be free mineral acid or acid salts. In these cases, it is necessary to determine the amount of acid, other than carbon dioxide, present, in excess of that required to form normal salts. This is done in the following way. Make an ammoniacal copper solution by taking 13 grams of copper sulphate, CuSO4.5H2O, dissolving in water, adding solution of ammonia until the precipitate first formed has nearly dissolved, and diluting to 1 litre. Allow to settle and decant off the clear liquid. The strength of this solution is determined by titrating against 10 or 20 cc of the standard solution of sulphuric acid. Note: 100 cc equals 1 gram H2SO4. End note. The finishing point is reached as soon as the solution becomes turbid from precipitated cupric hydrate. At first, as each drop falls into the acid solution, the ammonia and cupric hydrate combine with the free acid to form ammonic and cupric sulphates, but as soon as the free acid is used up, the ammonia in the next drop not only precipitates an equivalent of cupric hydrate from the solution, but also throws down that carried by itself. This method is applicable in the presence of metallic sulphates other than ferric. The standardizing and titration should be made under the same conditions. Since sulphuric acid and sulphates are predominant in waters of this kind, it is most convenient to report the acidity of the water as equivalent to so much sulphuric acid. Dissolved oxygen. For the gasometric method of analysing for dissolved oxygen, and for the Schützenberger's volumetric method, the student is referred to Sutton's volumetric analysis. The following is an easy method of estimating the free oxygen in a water. Take 20 c.c. of a stannous chloride solution. Note about 20 grams of the salt with 10 c.c. of hydrochloric acid to the litre. End note. Add 10 c.c. of hydrochloric acid and titrate in an atmosphere of carbon dioxide with standard permanganate of potassium solution. Note, made by dissolving 1.975 gram of the salt in 1 litre of water. 1 cc equals 0.5 mg of oxygen. End note. A similar titration is made with the addition of 100 cc of the water to be tested. Less permanganate will be required in the second titration, according to the amount of oxygen in the water, and the difference multiplied by 0.5 will give the weight of the oxygen in milligrams. Small quantities of nitrates do not interfere. In reporting the results of the analysis, it is customary to combine the acids and bases found on some such principle as the following. The sulphuric oxide is calculated as combined with the potash and reported as potassic sulphate, K2SO4. The balance of the sulphuric oxide is then apportioned to the soda and reported as sulphate of soda, Na2SO4. If any is still left, it is reported as calcium sulphate, CaSO4, and after that as magnesic sulphate, MgSO4. When the sulphuric oxide has been satisfied, the chlorine is distributed, taking the bases in the same order, then the nitric pentoxide, and lastly the carbon dioxide. But any method for thus combining the bases and acids must be arbitrary and inaccurate. It is extremely improbable that any simple statement can represent the manner in which the bases and acids are distributed whilst in solution. And since different chemists are not agreed as to any one system, it is better to give up the attempt and simply state the results of the analysis. This has only one inconvenience. The bases are represented as oxides, and since some of them are present as chlorides, the sum total of the analysis will be in excess of the actual amount present by the weight of the oxygen equivalent to the chlorine present as chloride. The following is an example of such a statement. Total solids dried at 100 degrees centigrade, 28.73 parts per 100,000. Chlorine, 1.70 parts per 100,000. Nitrogen as nitrate, 0.03 parts per 100,000. Ammonia, 0.001 parts per 100,000. Albuminoid ammonia, 0.004 parts per 100,000. Oxygen consumed in 4 hours, 0.01 parts per 100,000. The solids were made up as under: potash, 0.38 per 100,000 of the water. Soda, 2.01 per 100,000 of the water. Magnesia, 1.44 per 100,000 of the water. Lime, 10.55 per 100,000 of the water. Ferric oxide, 0.01 per 100,000 of the water. Silica, 0.30 per 100,000 of the water. Sulphuric oxide, 3.69 per 100,000 of the water. Nitrogen pentoxide, 0.11 per 100,000 of the water. Carbon dioxide, 8.38 per 100,000 of the water. Chlorine, 1.70 per 100,000 of the water. Volatile and organic matter, 0.66 per 100,000 of the water. Total, 29.23. Less oxygen equivalent to chlorine found, 0.39. Total, 28.84. For the preparation of distilled water, the apparatus shown in Figure 64 is convenient for laboratory use. It consists of a copper retort heated by a ring gas burner and connected with a worm condenser. Reader's note: Figure 64 is described well in the text. End reader's note. Practical exercise. A mineral on analysis gave the following results: water 44.94%, sulphuric oxide 28.72%, ferrous iron 13.92%, ferric iron 0.35%, copper 6.1%. The mineral was soluble in water and showed nothing else on testing. How would you report the analysis? Calculate the formula for the salt. End of section 38. Section 37 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Part 3. Non-Metals. Chapter 15. Oxygen and Oxides, the Halogens. Part 1. Oxygen. Oxygen occurs in nature in the free state, forming 23% by weight or 21% by volume of the atmosphere. But since it is a gas, its presence is easily overlooked and its importance underestimated. Except in the examination of furnace gases, etc., the assayer is not often called upon to determine its quantity, but it forms one of his most useful reagents, and there are many cases where he cannot afford to disregard its presence. It occurs not only in the air, but also dissolved in water. Ordinary waters containing on an average 0.00085% by weight, or 0.85 parts per 100,000. Chemically, it is characterized by its power of combining, especially at high temperatures, with the other elements, forming an important class of compounds called oxides. This combination, when rapid, is accompanied by the evolution of light and heat. Hence, oxygen is generally called the supporter of combustion. This property is taken advantage of in the operation of calcining, scorifying, cupelling, etc. The importance of a free access of air in all such work is seen when it is remembered that 1 litre of air contains 0.2975 gram of oxygen, and this quantity will only oxidize 0.1115 gram of carbon, 0.2975 gram of sulphur, or 3.849 grams of lead. Oxidation takes place at the ordinary temperature with many substances. Examples of such action are seen in the weathering of pyrites, rusting of iron, and, in the assay office, the weakening of solutions of many reducing agents. For methods of determining the percentage of oxygen in gases for technical purposes, the student is referred to Winkler and Lunge's Technical Gas Analysis. Oxides. Oxides are abundant in nature, almost all the commercially occurring bodies being oxidized. Water, H2O, contains 88.8% of oxygen. Silica, lime, alumina, magnesia, and the other earths are oxides, and the oxides of the heavier metals are in many cases important ores, as for example cassiterite, SnO2, hematite, Fe2O3, magnetite, Fe3O4, and pyrolusite, MnO2. In fact, the last named mineral owes its value to the excess of oxygen it contains, and may be regarded as an ore of oxygen rather than of manganese. Most of the metals, when heated to redness in contact with air, lose their metallic lustres and become coated with, or, if the heating be prolonged, altogether converted into, oxide. This oxide was formerly termed a calx, and has long been known to weigh more than the metal from which it was obtained. For example, 1 part by weight of tin becomes, on calcining, 1.271 parts of oxide. Note putty powder. End note. The student will do well to try the following experiments. Take 20 grams of tin and heat them in a muffle on a scorifier, scraping back the dross as it forms, and continuing the operation until the whole of the metal is burnt to a white powder and ceases to increase in weight. Footnote: this will require 2 or 3 hours to thoroughly complete. It is best to powder the oxide first produced and recalcine. End footnote. Take care to avoid loss, and when cold, weigh the oxide formed. The oxide should weigh 25.42 grams, which increase in weight is due to the oxygen absorbed from the air and combined with the metal. It can be calculated from this experiment, if there has been no loss, that oxide of tin contains 21.33% of oxygen and 78.67% of tin. Oxidation is performed with greater convenience by wet methods, using reagents such as nitric acid, which contain a large proportion of oxygen loosely held. Such reagents are termed oxidizing agents. Besides nitric acid, permanganate of potash, bichromate of potash, and peroxide of hydrogen are largely used for this purpose. 1 cc of nitric acid contains as much oxygen as 2.56 litres of air, and the greater part of this is available for oxidizing purposes. Try the following experiment. Take 2 grams of tin and cover in a weighed Berlin dish with 20 cc of dilute nitric acid. Heat till decomposed, evaporate to dryness, ignite and weigh. The 2 grams of tin should yield 2.542 grams of oxide. The increase in weight will be proportionately the same as in the previous experiment by calcination, and is due to oxygen, which in this case has been derived from the nitric acid. The percentage of oxygen in this oxide of tin, or in any of the oxides of the heavier metals, may be directly determined by heating such oxides in a current of hydrogen, and collecting and weighing the water formed. It is found by experiment that 88.86 parts by weight of oxygen, combining with 11.14 parts of hydrogen, form 100 parts of water. So that from the weight of water formed it is easy to calculate the amount of oxygen the oxide contained. Take 1 gram of the dried and powdered oxide and place it in a warm, dry combustion tube. Place the tube in a furnace and connect at one end with a hydrogen apparatus, provided with a sulphuric acid bulb for drying the gas, and at the other with a weighed sulphuric acid tube for collecting the water formed. The apparatus required is shown in Figure 62. Reader's note: Figure 62 is described clearly in the text. End reader's note. Pass hydrogen through the apparatus, and when the air has been cleared out, light the furnace. Continue the heat and current of hydrogen for half an hour, or longer if necessary. Allow to cool. Draw a current of dry air through the weighed tube. Weigh. The increase in weight gives the amount of water formed, and this multiplied by 0.8886 gives the weight of the oxygen. The percentage of oxygen thus determined should be compared with that got by the oxidation of the metal. It will be practically the same. The following results can be taken as examples. 20 grams of tin, calcined as described, gave 25.37 grams of oxide. 2 grams of tin oxidized with nitric acid and ignited gave 2.551 grams of oxide. 1 gram of the oxide of tin on reduction in a current of hydrogen gave 0.2360 gram of water, equivalent to 0.2098 gram of oxygen, and left 0.7900 gram of metal. 10 grams of ferrous sulfate gave, on strong ignition, 2.898 grams of ferric oxide, Fe2O3, instead of 2.877. Footnote: no magnetic oxide was formed. End footnote. The student should similarly determine the percentage of oxygen in oxides of copper and iron. The former oxide may be prepared by dissolving 5 grams of copper in 50 cc of dilute nitric acid, evaporating to dryness, and strongly igniting the residue. The oxide of iron may be made by weighing up 10 grams of powdered ferrous sulfate, note equal to 2.014 grams of iron, end note, and heating, at first gently, to drive off the water, and then at a red heat, until completely decomposed. The weight of oxide in each case should be determined, and the percentage of oxygen calculated. Compare the figures arrived at with those calculated from the formula of the oxides, CuO and Fe2O3. It would be found in a more extended series of experiments that the same metal will, under certain conditions, form two or more oxides differing among themselves in the amount of oxygen they contain. These oxides are distinguished from one another by such names as higher and lower oxides, peroxides, protoxides, dioxides, etc. The oxides may be conveniently classified under three heads. 1. Those that are reduced to metal by heat alone, such as the oxides of mercury, silver, platinum, gold, etc. 2. Those which are reduced by hydrogen at a red heat, which includes the oxides of the heavy metals. 3. Those which are not reduced by these means, good examples of which are silica, alumina, the alkalis, and the alkaline earths. Another important classification is into acid, basic, and neutral oxides. The oxides of the non-metallic elements, such as sulphur, carbon, phosphorus, etc., are, as a rule, acid, and the more oxygen they contain, the more distinctly acid they are. The oxides of the metals are nearly all basic, and, as a rule, the less oxygen they contain, the more distinctly basic they are. The basic oxides, which are soluble in acids, give rise to the formation of salts when dissolved therein. During the solution, water is formed, but no gas is evolved. The oxide dissolved, in each case, neutralizes an equivalent of the acid used for solution. Footnote: for example, CaO plus 2HCl yields CaCl2 plus H2O. PbO plus H2SO4 yields PbSO4 plus H2O. MgO plus 2HNO3 yields Mg bracket NO3 close bracket twice plus H2O. Al2O3 plus 6HCl yields Al2Cl6 plus 3H2O. Fe2O3 plus 3H2SO4 yields Fe2 bracket SO4 close bracket times 3 plus 3H2O. End footnote. The basic properties of many of these can be taken advantage of for their determination. This is done in the case of soda, potash, lime, etc., by finding the quantity of acid required to neutralize a given weight of the substance. There are some oxides which, under certain conditions, are acid to one substance, a stronger base, and basic to another, a stronger acid. For example, the oxides of lead and of tin, as also alumina, dissolve in caustic soda, acting as acids, whilst on the other hand they combine with sulphuric or hydrochloric acid, playing the parts of bases. The oxides known as earths, when ignited, are, many of them, insoluble in acids, although easily dissolved before ignition. It is common, in complete analyses of minerals, to meet with cases in which the sum total of the elements found falls short of the amount of ore taken, and here oxygen must be looked for. For example, this occurs in the case of a mixture of pyrites with oxide of iron, or in a mixture of sulphides and sulphates. The state in which the elements are present and the percentage, say of sulphides and sulphates, can in many cases be determined, but this is not always required. When the difference between the sum total and the elements found is small, it is reported as oxygen and loss. When, however, it is considerable, the oxygen may be reported as such, and its amount be either determined directly in the way already described, or calculated from the best determination that can be made of the relative amounts of oxides, sulphides, sulphates, etc. present. Such cases require a careful qualitative analysis to find out that the substance is present, and then the separation of each constituent is made as strictly as possible. These remarks apply especially to ores of the heavy metals. The separation of the constituents is effected with suitable solvents applied in proper order. The soluble sulphates, for example, are extracted with water, the oxides by the dilute acids or alkalis in which they are known to be soluble. The oxygen in the sulphates and oxides thus obtained is estimated by determining the sulphur and metals in the solutions, and calculating the amount of oxygen with which they combine. The metals of the earths and alkalis are almost invariably present as oxides, and are reported as such, except it is known that they are present in some other form, such as fluoride or chloride. Thus, silica, alumina, lime, water, etc. appear in an analysis, even in those cases where oxygen and loss is also mentioned. As an example of such a report, take the following analysis of Spanish pyrites. Sulphur 49.00, iron 43.55, copper 3.20, arsenic 0.47, lead 0.93, zinc 0.35, lime 0.10, silica etc. 0.63, water 0.70, oxygen and loss 1.07, total 100.00. The following example will illustrate the mode of calculating and reporting. A mineral occurring as blue crystals soluble in water and found on testing to be a mixed sulphate of iron and copper gave on analysis the following results: water 44.51%, sulphuric oxide 28.82%, copper 8.44%, ferrous iron 11.81%, ferric iron 0.38%, zinc 0.28%, total 94.24. There is here a deficiency of 5.76% due to oxygen. Nothing else could be found, and it is known that in the sulphates the metals exist as oxides. By multiplying the weight of the copper by 1.252, the weight of copper oxide, CuO, will be ascertained. In this case it equals 10.57%. The ferrous iron multiplied by 1.286 will give the ferrous oxide, FeO, in this case 15.19%. The ferric iron multiplied by 1.428 will give the ferric oxide, Fe2O3, in this case 0.54%. The zinc multiplied by 1.246 will give the zinc oxide, ZnO. In this case it equals 0.35%. The analysis will be reported as water 44.51, sulphuric oxide 28.82, copper oxide 10.57, equal to copper 8.44%, ferrous oxide 15.19, ferric oxide 0.54, zinc oxide 0.35, total 99.98. The following, A, is an analysis of a sample of South American copper ore, which will serve as a further illustration. The analysis shows the presence of 6.89% of ferrous oxide and some oxide of copper. The analysis of B is that of an ore from the same mine after an imperfect roasting. It will be seen that the carbonates have been converted into sulphates. If the total sulphur simply had been determined and the sulphate overlooked, the oxygen and loss would have been 5.65%, an amount which would obviously require an explanation. Water: A 0.25, B 0.59. Organic matter: A 0.54, B none. Sulphur: A 29.50, B 21.33. Copper: A 10.92, B 9.80. Copper 9.57, copper oxide 0.28. Iron: A 32.09, B 39.73. Iron 34.32, ferric oxide 7.73. Lead: A 0.35, B 0.12. Zinc: A 0.86, B 0.69. Cobalt: A 0.06, B 0.11. Lime: A 5.25, B 7.69. Magnesia: A 2.33, B 2.55. Sulphuric oxide: A 1.00, B 5.30. Carbon dioxide: A 8.87, B none. Insoluble silicates: A 5.12, B 8.38. Oxygen and loss: A 2.86, B 2.47. B only: potash 0.15, and soda 1.09. Totals A 100.00, B 100.00. End of section 37. Section 39 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 15. Oxygen and Oxides, the Halogens. Part 3. The halogens. There is a group of closely allied elements to which the name halogen, note salt producer, end note, has been given. It comprises chlorine, bromine, iodine, and fluorine. These elements combine directly with metals, forming as many series of salts, chlorides, bromides, iodides, and fluorides, corresponding to the respective oxides, but differing in their formulae by having two atoms of the halogen in the place of one atom of oxygen. For example, ferrous oxide is FeO, and ferrous chloride is FeCl2. And again, ferric oxide is Fe2O3, whilst ferric chloride is Fe2Cl6. These salts differ from the carbonates, nitrates, etc. in containing no oxygen. Consequently, it is incorrect to speak of such compounds as chloride of potash, fluoride of lime, etc., since potash and lime are oxides. It is important to bear this in mind in reporting analyses in which determinations have been made, say, of chlorine, magnesia, and potash, or of fluorine, silica, and alumina. It is necessary in all such cases to deduct from the total an amount of oxygen equivalent to the halogen found, except of course where the base has been determined and recorded as metal. Compounds containing oxides and fluorides, etc., do not lend themselves to the method of determining the halogen by difference. For example, topaz, which according to Dana has the formula Al2SiO4F2, would yield in the ordinary course of analysis alumina 55.4%, silica 32.6%, fluorine 20.6%, total 108.6. The oxygen equivalent to 20.6% fluorine may be found by multiplying the percentage of fluorine by 0.421. It is 8.7% and must be deducted. The analysis would then be reported thus: alumina 55.4%, silica 32.6%, fluorine 20.6%, total 108.6, less oxygen equivalent to fluorine 8.7, total 99.9. Take as an illustration the following actual analysis by F.W. Clarke and J.S. Diller. Alumina 57.38%, silica 31.92, fluorine 16.99, potash 0.15, soda 1.33, water 0.20, total 107.97. Deduct oxygen equivalent 7.16, total 100.81. In calculating the factor for the oxygen equivalent, divide the weight of one atom of oxygen, 16, by the weight of two atoms of the halogen. For example, with chlorine it would be 16 divided by 71, or 0.2253. With bromine, 16 divided by 160, or 0.1000. With iodine, 16 divided by 254, or 0.063. And with fluorine, 16 divided by 38, or 0.421. Chlorine and chlorides. Chlorine occurs in nature chiefly combined with sodium as halite or rock salt, NaCl. With potassium it forms sylvine, KCl, and together with magnesium, carnallite. Note KCl, MgCl2.6H2O. End note. Of the metalliferous minerals containing chlorine, kerargyrite or horn silver, AgCl, and atacamite, an oxychloride of copper, note CuCl2.3Cu open bracket HO close bracket twice end note are the most important. Apatite, note phosphate of lime end note, and pyromorphite, note phosphate of lead end note, contain a considerable amount of it. Chlorine is a gas of a greenish colour, possessing a characteristic odour, and moderately soluble in water. It does not occur native, and is generally prepared by the action of an oxidizing agent on hydrochloric acid. It combines directly with metals at the ordinary temperature, even with platinum and gold, forming chlorides, which, except in the case of silver, are soluble. It is important in metallurgy because of the extensive use of it in extracting gold by chloridizing processes. It is also used in refining gold. Detection. Compounds containing the oxides of chlorine are not found in nature because of the readiness with which they lose oxygen. By reduction they yield a chloride, the form in which chlorine is met with in minerals. In testing, the compound supposed to contain a chloride is boiled with water, or in some cases dilute nitric acid. To the clear solution containing nitric acid, a few drops of nitrate of silver solution are added. If on shaking a white curdy precipitate, soluble in ammonia, separates out, it is sufficiently satisfactory evidence of the presence of chlorides. Solution and separation. The chlorides are generally soluble in water, and are got into solution by extracting with warm dilute nitric acid. Or, if insoluble, the substance is fused with carbonate of soda, extracted with water, and the filtrate acidified with nitric acid. For the determination, it is not necessary to obtain the solution of the chloride free from other acids or metals. If tin, antimony, mercury, or platinum is present, it is best to separate by means of sulphuretted hydrogen. The chloride is determined in the solution after removal of the excess of the gas. Where traces of chlorides are being looked for, a blank experiment is made to determine the quantity introduced with the reagents. 100 c.c. of ordinary water contains from 1 to 3 milligrams of chlorine. On the addition of nitrate of silver to the nitric acid solution, chloride of silver separates out. This is free from other substances, except perhaps bromide and iodide. Gravimetric determination. Freely mix the solution containing the chloride with dilute nitric acid. Filter, if necessary, and treat with nitrate of silver. Heat nearly to boiling, and when the precipitate has settled, filter and wash with hot distilled water. Dry, and transfer to a weighed Berlin crucible. Burn the filter paper separately, and convert any reduced silver into chloride by alternate treatment with drops of nitric and of hydrochloric acid. Add the main portion to this and heat cautiously till the edges of the mass show signs of fusing. Note about 260 degrees. End note. Cool in the desiccator and weigh. The substance is chloride of silver, AgCl, and contains 24.73% of chlorine. The precipitated chloride is filtered and washed as soon as possible after settling, since on exposure to light it becomes purple and loses a small amount of chlorine. Volumetric method. There are several volumetric methods, but that based on the precipitation of silver chloride in neutral solution by means of a standard solution of silver nitrate, note using potassium chromate as indicator, end note, is preferred. Silver chromate is a red-coloured salt, and when silver nitrate is added to a solution containing both chloride and chromate, the development of the red colour marks off sharply the point at which the chloride is used up. Silver chromate is decomposed and consequently decolorized by solution of any chloride. The solution for this method must be neutral, since free acid prevents the formation of the red silver chromate. If not already neutral, it is neutralized by titrating cautiously with a solution of soda. In a neutral solution, other substances, such as phosphates and arsenates, also yield a precipitate with a solution of nitrate of silver, and will count as chloride if they are not removed. The standard solution of nitrate of silver is made by dissolving 23.94 grams of the salt, AgNO3, in distilled water, and diluting to 1 litre. 100 cc's are equal to 0.5 gram of chlorine. The indicator is made by adding silver nitrate to a strong neutral solution of yellow chromate of potash, K2CrO4, till a permanent red precipitate is formed. The solution is allowed to settle, and the clear liquid decanted into a stoppered bottle labelled chromate indicator for chlorine. Standardise the silver nitrate by weighing up 0.5 gram of pure sodium chloride or potassium chloride. Transfer to a flask and dissolve in distilled water. Dilute to 100 cc's. Fill an ordinary burette with the standard silver solution and, after adjusting, run into the flask a quantity sufficient to throw down the greater part of the chlorine. Add a few drops of the chromate indicator and continue the addition of the silver nitrate until the yellow colour of the solution becomes permanently tinted red after shaking. This shows that the chlorine is all precipitated and that the chromate is beginning to come down. The further addition of a couple of drops of the silver solution will cause a marked difference in the tint. Read off the quantity run in and calculate the standard. 1 gram of sodium chloride contains 0.6062 gram of chlorine, and 1 gram of potassium chloride contains 0.4754 gram. For the determination of small quantities of chloride, a few milligrams, the same method is used, but the standard solution is diluted so that each cc is equal to 1 milligram of chlorine, and the chromate indicator is added before titrating. The standard solution is made by measuring off 200 cc's of the solution described above and diluting with distilled water to 1 litre. Bromine and bromides. Bromine closely resembles chlorine in the nature of its compounds. It does not occur free in nature, but is occasionally found in combination with silver as bromargyrite, AgBr, and together with chloride in embolite. It mainly occurs as alkaline bromides in certain natural waters. Nearly all the bromine of commerce is derived from the mother liquors of salt works, i.e. the liquors from which the common salt has been crystallized out. Bromine combines directly with the metals, forming a series of salts, the bromides. In ordinary work they are separated with and, except when specially tested for, counted as chlorides. They are detected by adding chlorine water to the suspected solution and shaking up with carbon bisulfide. Bromine colours the latter brown. Iodine and iodides. Iodine does not occur in nature in the free state, and iodides are rare, iodargyrite or iodide of silver, AgI, being the only one which ranks as a mineral species. Iodates are sometimes found associated with Chile saltpeter, which is an important source of the element. Iodine and iodides are largely used in the laboratory and have already been frequently referred to. It is used as an oxidizing agent in a similar manner as permanganate and bichromate of potash, especially in the determinations of copper, arsenic, antimony, and manganese. Iodine is not readily soluble in water, but dissolves easily in a concentrated solution of potassium iodide. Its solutions are strongly coloured. A drop of a dilute solution colours a large volume of water decidedly yellow. On the addition of starch paste, this becomes blue. The delicacy of this reaction is taken advantage of in titrations to determine when free iodine is present. The blue colour may be alternately developed and removed by the addition of iodine, or an oxidizing agent, and hyposulphite of soda, or some other reducing agent. In decolorizing, the solution changes from blue or black to colourless or pale yellow, according to circumstances. Sometimes the solution, instead of remaining colourless, gradually develops a blue which recurs in spite of the further addition of the reducing agent. In these cases, the conditions of the assay have been departed from, or, and this is more often the case, there is some substance present capable of liberating iodine. Iodine forms a series of salts, the iodides, resembling in many respects the chlorides. These can be obtained by direct combination of the metals with iodine. Detection. Free iodine is best recognised by the violet vapours evaporated from the solution on heating, and by the blue or black colour which it strikes on the addition of starch paste. Iodides are detected by boiling with strong solutions of ferric sulphate or chloride. Iodine is liberated, distilled over, and collected. Chlorine also liberates iodine from iodides, and this reaction is frequently made use of in assaying. A process based on this is described under manganese. All substances which liberate chlorine on boiling with hydrochloric acid, dioxides, bichromates, permanganates, etc., are determined in a similar way. Solution and separation. Most iodides are soluble in water or dilute acids. The separation is effected by distilling the substance with solution of ferric sulphate and collecting the vapour in a dilute solution of sulphurous acid or arsenite of soda. On the completion of the distillation, the iodine will be in the distillate as iodide, and the gravimetric determination is made on this. Gravimetric determination. To the solution containing the iodine as iodide, and which is free from chlorides and bromides, add a little dilute nitric acid and nitrate of silver till no further precipitate is produced. Filter off, wash with hot water, and dry. Clean the filter paper as much as possible and burn it. Collect the ash in a weighed porcelain crucible, add the main portion, and heat to incipient fusion. Cool and weigh. The substance is silver iodide and contains 54.03% of iodine. Volumetric method. This is for the titration of free iodine, and is practically that which is described under manganese. The substance to be determined is distilled with ferric sulphate, and the iodine is collected in a solution of potassium iodide, in which it readily dissolves. If flaky crystals separate out in the receiver, more potassium iodide crystals are added. When the distillation is finished, the receiver is disconnected, and its contents washed out into a beaker and titrated with hypo. The standard solution of hypo is made by dissolving 19.58 grams of hyposulphite of soda, note Na2S2O3.5H2O, in water and diluting to 1 litre. 100 cc's are equal to 1 gram of iodine. To standardise the solution, weigh up 0.25 gram of pure iodine in a small beaker. Add 2 or 3 crystals of potassium iodide. Cover with water, and when dissolved, dilute to 50 or 100 cc's. Titrate and calculate the standard. Fluorine and fluorides. Fluorine is frequently met with as calcium fluoride or fluorspar, CaF2. It occurs less abundantly as cryolite, Na3AlF6, a fluoride of aluminium and sodium, which is used in glass making. Certain other rarer fluorides are occasionally met with. Fluorine is also found in apatite and in some silicates, such as topaz, tourmaline, micas, etc. Hydrofluoric acid is used for etching glass and opening up silicate. It attacks silica, forming fluoride of silicon, SiF4, which is volatile. Silica is, by this means, eliminated from other oxides, which, in the presence of sulphuric acid, are fixed. The commercial acid is seldom pure and generally weak, and the acid itself is dangerously obnoxious. The use of ammonium fluoride or sodium fluoride and a mineral acid is more convenient. Determinations of this kind are made in platinum dishes enclosed in lead or copper vessels in a well-ventilated place. Fluorspar is useful as a flux in dry assaying. It renders slags, which would otherwise be pasty, quite fluid. Fluorides generally are fusible and impart fusibility to substances with which they form weak compounds. Their fluxing action does not depend on the removal of silicon as fluoride. Detection. Fluorides in small quantity are easily overlooked unless specially sought for. In larger amounts, they are recognised by the property hydrofluoric acid has of etching glass. A watch glass is warmed and a layer of wax is melted over the convex side. When cold, some lines are engraved on the waxed surface with any sharp-pointed instrument. The substance to be tested is powdered and moistened in a platinum dish with sulphuric acid. The watch glass is filled with cold water and supported over the dish. The dish is then carefully warmed, but not sufficiently to melt the wax. After a minute or two the glass is taken off and the wax removed. If the substance contained fluorine, the characters will be found permanently etched on the glass. An equally good but more rapid test is to mix the powdered substance with some silica and to heat the mixture in a test tube with sulphuric acid. Silicon fluoride is evolved, and if a moistened glass rod is held in the tube, it becomes coated with a white deposit of silica formed by the decomposition of the silicon fluoride by the water. This is also used as a test for silica, but in this case the substance is mixed with a fluoride, and the experiment must obviously be carried out in a platinum vessel. Separation and determination. The determination of fluorine is difficult. In the case of fluorides free from silicates, such as fluorspar, it is determined indirectly by decomposing a weighed portion with sulphuric acid, evaporating, igniting, and weighing the residual sulphate. The increase in weight multiplied by 0.655 gives the weight of fluorine. In the presence of silica, this method does not answer because of the volatilization of silicon fluoride. In these cases, Wöhler adopted the following plan, which resembles that for the indirect determination of carbon dioxide. Mix the weighed substance in a small flask with powdered silica and sulphuric acid. The mouth of the flask is closed with a cork carrying a tube, which is filled, the first half with calcium chloride and the second half with pumice coated with dried copper sulphate. The apparatus is weighed quickly and then warmed till decomposition is complete. A current of dry air is aspirated for a minute or two, and the apparatus again weighed. The loss in weight gives that of the silicon fluoride, SiF4, which, multiplied by 0.7307, gives the weight of fluorine. Fresenius uses the same reaction, but collects and weighs the silicon fluoride. The finely powdered and dried substance is mixed with 10 or 15 times its weight of ignited and powdered silica. The mixture is introduced into a small dry flask, connected on one side with a series of drying tubes, and on the other with an empty tube to condense any sulphuric acid. To this last is joined a drying tube containing chloride of calcium and anhydrous copper sulphate. This is directly connected with a series of 3 weighed tubes in which the fluoride of silicon is collected. The last of these is joined to another drying tube. The first weighed tube contains pumice and cotton wool moistened with water. The second tube contains soda lime as well as, in the upper half of the second limb, fused calcium chloride between plugs of wool. The third tube is filled half with soda lime and half with fused calcium chloride. The distilling flask containing the substance mixed with silica is charged with 40 or 50 c.c. of sulphuric acid and placed on the hot plate. Alongside it is placed a similar dry flask containing a thermometer, and the temperature in this is kept at 150 degrees or 160 degrees centigrade. A current of air is sent through the tubes during the operation, which takes from 1 to 3 hours for from 0.1 to 1 gram of the substance. A correction is made by deducting 0.001 gram for every hour the dried air has been passed through. The increase in weight of the 3 tubes gives the weight of the silicon fluoride. Penfield uses a similar arrangement, but passes his silicon fluoride into an alcoholic solution of potassium chloride. Silica and potassium silicofluoride are precipitated, and hydrochloric acid is set free. Footnote: 3SiF4 plus 4KCl plus 2H2O yield 2K2SiF6 plus SiO2 plus 4HCl. End footnote. The acid thus liberated is titrated with a standard solution of alkali in the alcoholic solution, and from the amount of free acid found, the fluorine is calculated. The weight of hydrochloric acid, HCl, found multiplied by 1.562 gives the weight of the fluorine. With this method of working, fewer U-tubes are required. The exit tube from the flask is bent so as to form a small V, which is kept cool in water. This is directly connected with the U-tube containing the alcoholic solution of potassium chloride. The flask with the assay is heated for about 2 hours, and a current of dry air is aspirated throughout the determination. Fluoride of silicon is a gas not easily condensed to a liquid, but is immediately decomposed by water or moist air. End of section 39. Section 40 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 16. Sulphur and Sulphates. Sulphur occurs native in volcanic districts and is mined in Sicily, Italy and California in considerable quantities. Combined with metals, note sulphides, endnote, it is common in all mineral districts. Iron pyrites, FeS2, is the most abundant source of this element. Sulphates, such as gypsum, are fairly common, but have no value so far as the sulphur in them is concerned. In coal, it exists as an impurity, occurring partly as a constituent of organic compounds. Sulphur, whether free or combined with metals, forms on burning sulphurous oxide, SO2, which by the action of oxidizing agents and water is converted into sulphuric acid. It forms two oxides, sulphurous, SO2, and sulphuric, SO3, which combine with bases to form sulphites and sulphates. Sulphites are of little importance to the assayer and are converted into sulphates by the action of nitric acid and other oxidizing agents. The native sulphides, when acted on with hydrochloric acid, give off sulphuretted hydrogen. With nitric acid or aqua regia, sulphates are formed, and more or less sulphur separated. Sulphur is detected in sulphides by the irritating odour of sulphurous oxide given off on roasting, by the evolution of sulphuretted hydrogen when treated with hydrochloric acid, or by a white precipitate of barium sulphate formed when barium chloride is added to the aqua regia solution. Dry assay. There is no method of general application. Free or native sulphur may be volatilized, condensed and weighed, but pyrites only gives up a portion of its sulphur when heated in a closed vessel, while most sulphides and all sulphates give up none at all. In the determination of sulphur in brimstone, 10 grams of the substance are taken, placed in a small porcelain dish, heated over a Bunsen burner in a well-ventilated place, and ignited. When the sulphur has been completely burnt off, the residue, which consists chiefly of sand, is collected and weighed. In a separate portion, the moisture and arsenic are determined. The amounts of these are deducted from the loss in the first experiment. The difference, multiplied by 10, gives the percentage of sulphur. Wet methods. Solution. All sulphates, excepting those of lead, barium, strontium and lime, are soluble in water or dilute acid. All sulphides, except cinnabar, are converted into sulphates by the action of nitric acid at a gentle heat, or, better, by the action of a mixture of 3 volumes of nitric acid and 1 volume of hydrochloric acid. This last attacks cinnabar as well. With most substances, it is difficult to convert the whole of the sulphur into sulphuric acid. The sulphur separates out at first as a dark spongy mass, which, on continued treatment, changes to light-coloured flakes. When the solution becomes concentrated and the temperature rises sufficiently, the sulphur fuses into one or more honey-coloured globules, which, owing to the small surface they oppose to the acid, are very slowly oxidized. It is not desirable to assist the formation of these globules, therefore the temperature is kept as low as possible and strong nitric acid is used. When such globules form, it is best to allow the solution to cool, when the globules will solidify. They can then be filtered off and picked out from the insoluble residue, dried, weighed, ignited, and again weighed, the loss being counted as sulphur. With iron pyrites, this difficulty seldom occurs. Metallic sulphides, when fused with an excess of nitre, are completely oxidized. If the ore is rich in sulphur, some inert body, such as sodium chloride or, better, sodium carbonate, is added to dilute the action. With pure sulphur, the action is so energetic as to cause an explosion, so that care should be taken. With burnt ores, incompletely calcined pyrites, there is sufficient oxide of iron present to prevent too rapid action. These fusions with nitre are best conducted in a platinum dish covered with a piece of platinum foil. The ore is ground with the nitre to ensure complete mixing. The heat need not be excessive, so that a single Bunsen burner placed beneath the dish will suffice. If the bottom of the dish is seen to be red hot, it is sufficient. On cooling and extracting with water, the sulphur will pass into solution as potassium sulphate, which is then filtered off from the insoluble oxides of iron, copper, etc. The filtrate, after having been treated with a large excess of hydrochloric acid, evaporated to dryness, and redissolved in water, is ready for the determination. Lead sulphate may be dissolved by boiling with ammonium acetate. The insoluble sulphates of barium, strontium, and lime are decomposed by fusing with 4 or 5 times their weight of fusion mixture. The alkaline sulphates are then dissolved out with water and filtered off from the insoluble residue. The filtrate is rendered acid with hydrochloric acid. Separation. The determination of the sulphuric acid in these solutions by precipitation with barium chloride also serves as a separation, but in hot acid solutions containing copper, and more especially iron, salts, the baric sulphate has a strong tendency to carry down amounts of those bodies, varying no doubt with the conditions of the precipitation. Boiling hydrochloric acid fails to completely extract them. Moreover, the use of hot concentrated hydrochloric acid causes a loss by dissolving barium sulphate. Nitric acid and nitrates must be decomposed by prolonged boiling and evaporation with hydrochloric acid. The iron may be removed by adding a slight excess of ammonia to the faintly acid solution, filtering off, and washing the precipitated ferric hydrate with hot water. By slightly acidulating the filtrate with hydrochloric acid, it will be rendered ready for the determination. Gravimetric method. This assay is one of those which strikingly shows the necessity of getting the assay solution under proper conditions in order to obtain satisfactory results. The method has been repeatedly investigated, and the conclusion arrived at that it can be correct only by accident. Yet there are many chemists who get good results and place considerable faith in its accuracy. This can only be due to differences in the manner of working. It is generally understood that nitric acid or nitrates must be absent, and our experience fully confirms this. Precipitations in nitrate solutions are worthless, as the following experiments show. In each experiment, the bulk of the solution was 150 cc's. The solutions contained 10 grams of nitre, were freely acid with hydrochloric acid, and were precipitated while boiling with slight excess of baric chloride. Sulphuric acid taken 0.020 gram, found 0.019 gram. Sulphuric acid taken 0.050 gram, found 0.047 gram. Sulphuric acid taken 0.100 gram, found 0.098. Sulphuric acid taken 0.500 gram, found 0.526. Sulphuric acid taken 1.004 gram, found 1.126 gram. Sulphuric acid taken 1.000 gram, found 1.126. All the precipitates were boiled with hydrochloric acid and thoroughly washed before weighing. The results of some other experiments on this subject are given under sulphur in the Examination of Commercial Copper, page 207. The solution having been obtained free from nitrates and chlorates, and containing but little free hydrochloric acid, is largely diluted, heated to boiling, and precipitated with a moderate excess of a solution of chloride of barium. Note, 8 parts of the crystallized barium chloride are sufficient for 1 of sulphur. End note. It is allowed to settle for half an hour and then decanted through a filter. The precipitate is shaken up with boiling water, rendered slightly acid, filtered, washed, dried, ignited, and weighed. The ignited precipitate, when pure, is white, and is not decomposed at a red heat. It is barium sulphate, BaSO4, and contains 13.73% of sulphur, or 34.33% of sulphuric oxide SO3. Determination of sulphur in pyrites. Weigh up half a gram of the dried and powdered sample and treat with 10 cc of a mixture of 3 volumes of nitric acid and 1 volume of hydrochloric acid, occasionally heating. Evaporate to dryness, treat with 5 cc of hydrochloric acid and again evaporate. Take up with 1 cc of hydrochloric acid and 100 cc of hot water. Filter through a small filter and wash. The residue may contain sulphates of lead, barium or lime. It must be separately examined if the total sulphur is wanted. The filtrate is heated and rendered slightly alkaline with ammonia. Filter off the precipitated ferric hydrate through a quick filter and wash with hot water. If necessary, evaporate the bulk to about 200 cc, render faintly acid with hydrochloric acid and add 20 cc of solution of barium chloride. Allow to stand for half an hour and decant through a filter. Wash with hot water, dry, ignite and weigh. Pure pyrites contains 53.33% of sulphur. Volumetric method. This is based upon the easy conversion of all sulphur compounds into sulphates by fusion with nitre or by oxidation with nitric acid, and on the determination of the sulphate formed by titration in an acetic acid solution with baric chloride. Footnote: BaCl2 plus Na2SO4 yields BaSO4 plus 2NaCl. End footnote. The finishing point is determined by filtering off portions of the assay solution and testing with sulphuric acid. A slight excess of baric chloride will cause a precipitate. The process may be divided into 1. The preparation of the solution, and 2. The titration. Preparation of the solution. Weigh up from 1 to 5 grams of the dried and powdered substance, and mix intimately with 4 grams of powdered nitre. Clean out the mortar with another gram of nitre and add this as a cover. Heat in a platinum crucible for 15 minutes at a low temperature. Cool and extract with water in an evaporating dish about 9 inches across and holding 700 or 800 cc. Add 10 grams of sodium acetate and 10 cc of acetic acid and dilute to half a litre. Boil. The solution is ready for titrating. Substances which lose sulphur on heating, such as pyrites, are thus treated. Weigh up 1 gram and evaporate nearly to dryness with 10 cc each of nitric and hydrochloric acids. Take up with 10 cc of hydrochloric acid and again boil down to a small bulk. Dilute and transfer to a 9-inch evaporating dish. Add 10 grams of sodium acetate and 5 cc of acetic acid. Dilute to half a litre and boil. The solution is ready for titrating. Sulphates may be dissolved up in the dish itself with the help of a cc or so of hydrochloric acid. Sodium acetate and acetic acid are then added, and after dilution and boiling, the solutions are at once titrated. The solution before titration must contain no free mineral acid, but 5 or 10 cc of acetic acid should be present. It must contain 10 grams of sodium acetate, or sufficient to convert any free mineral acid into its corresponding sodic salt, or, if chlorides, nitrates or sulphates of the metals are present, sufficient to decompose them. If a precipitation occurs, as in the case with ferric salts, etc., the solution is titrated with the precipitate in it. The titration. The standard solution of barium chloride is made by dissolving 76.25 grams of the crystallized salt, BaCl2.2H2O, in distilled water and diluting to 1 litre. 100 cc will equal 1 gram of sulphur. As indicator, use dilute sulphuric acid. The strength of the solution may be checked by the titration of 5 grams of ferrous sulphate, oxidized with permanganate of potassium or a few drops of nitric acid, which should require 57.5 cc of the barium chloride solution, or any pure sulphate of known composition can be used. Anhydrous salts should be preferred. Fill an ordinary 100 cc burette with the solution of barium chloride. The evaporating dish containing the assay solution is placed on a round burner, as shown in figure 65. Reader's note: description omitted, as the burner and dish are described well in the text. End reader's note. and the solution is kept steadily boiling. An ordinary Bunsen burner flame will cause bumping and should not be used. Run in the standard solution in quantity known to be insufficient. Then withdraw a portion of about 2 cc with a pipette and filter through a fine filter paper into a test tube. Run in another 0.5 cc of the standard solution and withdraw and filter into a test tube another portion of 2 cc, and continue this operation until half a dozen or more portions have been drawn off. The test tubes should be arranged in order in a stand resting on a piece of paper, so that each test tube representing 0.5 cc of the standard baric chloride may have its value recorded beneath it. Figure 66. Reader's note, figure 66 shows 12 test tubes in a test tube rack, each with a small funnel and filter paper in its top, and a small volume of liquid in the bottom. The liquid is clear in the first 7 test tubes and is gradually darker across the last 5. End reader's note. Add to each test tube 3 drops of dilute sulphuric acid. That which shows the first appearance of a precipitate marks the point at which the titration is complete. Suppose, for example, that the test tube marked 48.5 cc shows no precipitate, while that at 49.0 cc shows one. It is evident that the finishing point lies between these readings. With a little practice, one can judge from the appearance of the precipitate in the 49 cc tube whether a quarter cc should be deducted or not. It is better to add dilute sulphuric acid and to watch for the appearance of a precipitate in the test tube than to add baric chloride and look for its non-appearance. Besides, baric chloride is much less likely to be present in a test tube as impurity than sulphates are. In this way, the chance of error from what are termed accidental causes is diminished. The following experiments show the effect of variation in the conditions of titration. Make a standard solution of sulphuric acid by diluting 43.65 grams of sulphuric acid, specific gravity 1.6165, to 1 litre. 100 cc will contain 1 gram of sulphur. An equivalent solution may be made by dissolving 100.62 grams of sodium sulphate crystals, Na2SO4.10H2O, or 86.88 grams of ferrous sulphate, FeSO4.7H2O, in water, oxidizing the latter, and diluting to 1 litre. The order in which these experiments are given is that in which they were made in an investigation into the conditions under which the titration could most accurately be effected. Effect of hydrochloric and nitric acids. The titrations were performed in the manner already described, but sodic acetate and acetic acid were absent. 20 cc of the standard solution of sulphuric acid were used. Hydrochloric acid present 0.0 cc, baric chloride required 20.0 cc. Hydrochloric acid present 1.0 cc, baric chloride required 20.0 cc. Hydrochloric acid present 2.0 cc, baric chloride required 19.7 cc. Hydrochloric acid present 5.0 cc, baric chloride required 12.5 cc. Nitric acid present 0.0 cc, baric chloride required 20.0 cc. Nitric acid present 1.0 cc, baric chloride required 19.5 cc. Nitric acid present 2.0 cc, baric chloride required 18.0 cc. Nitric acid present 5.0 cc, baric chloride required 10.0 cc. These show clearly the interference of free mineral acids, although very dilute hydrochloric acid, 1 cc in 500 of water, has no effect. Effect of acetic and citric acids. A similar series of experiments with these acids gave the following results. Acetic acid present 0.0 cc, baric chloride required 20.0 cc. Acetic acid present 5.0 cc, baric chloride required 20.0 cc. Acetic acid present 50.0 cc, baric chloride required 20.0 cc. Acetic acid present 100.0 cc, baric chloride required 20.0 cc. Citric acid present 0 gram, baric chloride required 20.0 cc's. Citric acid present 1 gram, baric chloride required 20.0 cc's. Citric acid present 5 grams, baric chloride required 20.0 cc's. These acids do not interfere. Effect of sodic acetate and acetic acid. In each of these experiments 5 cc's of acetic acid was present. Sodium acetate added 0 gram, baric chloride required 20.0 cc's. Sodium acetate added 1 gram, baric chloride required 20.0 cc's. Sodium acetate added 10 grams, baric chloride required 20.0 cc's. Sodium acetate added 50 grams, baric chloride required 20.0 cc's. As sodic acetate and acetic acid did not interfere, it became desirable to make some experiments on the finishing point. The first object sought for was the smallest amount of the standard baric chloride in 500 cc's of water required to give an indication when tested in the manner already described. Note: the condition of assay solution given first, then baric chloride required. End note. Water only 0.05 cc's. With 10 grams of sodium acetate and 5 cc's of acetic acid, 0.05 cc's. The same with 5 grams of niter, 0.10 cc's. Like the last, but with 5 grams of salt instead of niter, 0.10 cc's. These show that as small an amount of baric chloride solution as is equal to only 0.000002 gram of sulphur in the 2 cc's of solution tested yields a decided precipitate on the addition of 3 drops of sulphuric acid. To determine whether the same finishing point is obtained on testing the filtered portions in the test tubes with baric chloride as is obtained on testing with sulphuric acid, a titration was made with 20 cc's of standard solution of sulphuric acid, together with the usual quantities of sodic acetate and acetic acid, and 2 lots of 2 cc's were filtered into 2 sets of test tubes after each addition of the standard baric chloride. To one series, 3 drops of baric chloride solution were added, and to the other 3 drops of sulphuric acid. The results were: baric chloride added 19.5 cc's, with dilute sulphuric acid clear, with baric chloride solution cloudy. Baric chloride added 19.75 cc's, with dilute sulphuric acid clear, with baric chloride solution cloudy. Baric chloride added 20.0 cc's, with dilute sulphuric acid finished, with baric chloride solution finished. Baric chloride added 20.25 cc's, with dilute sulphuric acid cloudy, with baric chloride solution clear. Baric chloride added 20.5 cc's, with dilute sulphuric acid cloudy, with baric chloride solution clear. The 2 methods of testing give the same result, but this balance is disturbed in the presence of much niter, the indications with baric chloride being disturbed by an opalescence for some cc's beyond the finishing point. In solutions containing free hydrochloric or nitric acid, a precipitate is obtained with either baric chloride or sulphuric acid. Effect of varying sulphur. In these and the subsequent experiments, the titrations were performed in the presence of 10 grams of sodic acetate and 10 cc's of acetic acid, in the manner already described. Standard sulphuric acid used 5.0 cc's. Baric chloride required 5.0 cc's. Standard sulphuric acid used 10.0 cc's. Baric chloride required 10.0 cc's. Standard sulphuric acid used 20.0 cc's. Baric chloride required 20.0 cc's. Standard sulphuric acid used 50.0 cc's. Baric chloride required 50.0 cc's. Standard sulphuric acid used 100.0 cc's. Baric chloride required 100.0 cc's. Effect of varying temperature. With 5 cc's of standard sulphuric acid titrated at 15 degrees centigrade, 5 cc's of baric chloride were required, but with larger quantities the results were altogether unsatisfactory when titrated cold. Effect of varying bulk. Bulk 100.0 cc, baric chloride required 20.0 cc. Bulk 200.0 cc, baric chloride required 20.0 cc. Bulk 500.0 cc, baric chloride required 20.0 cc. Bulk 1000.0 cc, baric chloride required 20.5 cc. Considerable variation in bulk has no effect, but 500 cc is the most convenient volume to work with. It is well to occasionally replace the water boiled off during titration. Effect of foreign salts. In all these experiments 20 cc of sulphuric acid were used, and the titration was performed in the ordinary way. Sodic chloride added 0 grams, baric chloride required 20.0 cc. Sodic chloride added 5 grams, baric chloride required 20.0 cc. Sodic chloride added 10 grams, baric chloride required 19.7 cc. Ammonic chloride added 0 grams, baric chloride required 20.0 cc. Ammonic chloride added 5 grams, baric chloride required 20.0 cc. Ammonic chloride added 10 grams, baric chloride required 19.5 cc. Calcic chloride added 0 grams, baric chloride required 20.0 cc. Calcic chloride added 1 gram, baric chloride required 20.0 cc. Calcic chloride added 2 grams, baric chloride required 19.2 cc. Calcic chloride added 5 grams, baric chloride required 19.0 cc. Zinc chloride added 0 grams, baric chloride required 20.0 cc. Zinc chloride added 1 gram, baric chloride required 20.0 cc. Zinc chloride added 3 grams, baric chloride required 20.0 cc. Zinc chloride added 5 grams, baric chloride required 20.0 cc. Ferrous chloride added 0 grams, baric chloride required 20.0 cc. Ferrous chloride added 1 gram, baric chloride required 19.7 cc. Ferrous chloride added 3 grams, baric chloride required 19.5 cc. Ferrous chloride added 5 grams, baric chloride required 19.0 cc. Ferric chloride added 0 grams, baric chloride required 20.0 cc. Ferric chloride added 1 gram, baric chloride required 20.0 cc. Ferric chloride added 3 grams, baric chloride required 20.0 cc. Ferric chloride added 5 grams, baric chloride required 20.0 cc. Copper chloride added 0 grams, baric chloride required 20.0 cc. Copper chloride added 1 gram, baric chloride required 20.0 cc. Copper chloride added 3 grams, baric chloride required 20.0 cc. Copper chloride added 5 grams, baric chloride required 20.0 cc. Potassic nitrate added 0 grams, baric chloride required 20.0 cc. Potassic chloride added 1 gram, baric chloride required 20.0 cc. Potassic nitrate added 5 grams, baric chloride required 20.0 cc. Potassic nitrate added 10 grams, baric chloride required 19.0 cc. Potassic nitrite added 0 grams, baric chloride required 20.0 cc. Potassic nitrite added 1 gram, baric chloride required 20.0 cc. Potassic nitrite added 5 grams, baric chloride required 20.0 cc. Sodic phosphate added 0 grams, baric chloride required 20.0 cc. Sodic phosphate added 1 gram, baric chloride required 22.5 cc. Sodic arsenate added 0 grams, baric chloride required 20.0 cc. Sodic arsenate added 1 gram, baric chloride required 20.5 cc. In the absence of ferric salts, phosphates and arsenates count as sulphur. In 2 series of experiments for determining the effect of varying amounts of sulphur in the form of ferrous sulfate, we obtained the following results. In the first series, the assay solution was prepared in the manner we have described for pyrites, and in the second series by fusion with nitre. Sulphur added 0.050 grams, baric chloride required 1 5.0 cc, 2 4.7 cc. Sulphur added 0.100 gram. Baric chloride required 1 10.0 cc. 2 10.0 cc. Sulphur added 0.200 gram. Baric chloride required 1 20.0 cc. 2 20.0 cc. Sulphur added 0.500 gram. Baric chloride required 1 50.0 cc. 2 50.0 cc. Sulphur added 1.000 gram. Baric chloride required 1 100.0 cc. 2 100.0 cc. More than 5 grams of nitre must not be used in an assay, and since the requisite amount of nitre considerably exceeds that sufficient to oxidise the sulphur, not more than 0.5 gram of unoxidised sulphur should be present in the portion of the sample weighed up for determination. When the amount of sulphur present is not known within reasonable limits, the test portions may be tried with a drop of baric chloride solution instead of sulphuric acid, so that the diminishing quantity of precipitate may give warning of an approach to the finishing point. Determination of sulphur in blend. Weigh up 1 gram of dried and powdered blend, and mix and fuse with 5 grams of nitre in the manner described. Place the dish and its contents in the titrating dish, extract with water, add 10 grams of sodium acetate and 10 cc of acetic acid. Remove and wash the platinum dish and dilute to 500 cc. Boil and titrate. In the example, duplicate determinations required A 32.0 cc, B 32.25 cc, giving an average of 32.1% of sulphur. Determination of sulphur in chalcopyrite. Note yellow copper ore. End note. Take 1 gram of the finely powdered sample and 5 grams of nitre. Sprinkle a little of the nitre in a small Wedgwood mortar, place the ore on it, and cover with 2 or 3 grams more of the nitre. Rub up together and transfer to a small porcelain dish. Clean out the mortar with the rest of the nitre and add to the contents of the dish. Cover with a piece of platinum foil and heat gently with a Bunsen burner till the nitre melts and the stuff shows signs of deflagrating. Remove the heat and allow the action to go on by itself for a minute or so, then heat over the Bunsen burner for 10 minutes. Cool, transfer the whole to the titrating dish, boil with 500 cc of water, remove the small dish and foil, add sodic acetate and acetic acid, and titrate. For example, 1 gram required 34.5 cc of barium chloride. Note standard equals 1.005 gram sulphur. End note. Which is equivalent to 34.7% sulphur. The theoretical percentage is 34.8. Determination of sulphur in chalcocite. Note grey copper ore. End note. Proceed as in the last experiment, but since the action with nitre is more moderate, no special precautions need be taken on heating. A platinum dish may be used. An example, which was heated for 30 minutes, required 20.5 cc of the barium chloride solution. This is equivalent to 20.6% of sulphur. The theoretical yield is 20.2%. Determination of sulphur in pyrites. Take 1 gram of the finely powdered sample, cover with 10 cc of nitric acid, and when action has ceased, evaporate to a small bulk. Add 3 or 4 cc of hydrochloric acid, and again evaporate to a paste. Take up with 1 or 2 cc of dilute hydrochloric acid, dilute with water, transfer to a titrating dish, add 10 grams of sodic acetate and 5 cc of acetic acid, and dilute with water to 500 cc. Boil and titrate. An example, with 1 gram of a pure crystallized pyrites required 52.7 cc of the barium chloride solution, which is equivalent to 53.0% of sulphur. Theory requires 53.3% of sulphur. Determination of sulphur in mispickle. Take 1 gram of the powdered ore and evaporate with 10 cc of nitric acid, and take up with 3 or 4 cc of hydrochloric acid. If any globules of sulphur remain, again evaporate with nitric acid. Dilute and transfer to the titrating dish. Add 10 grams of sodic acetate, dilute with water, boil and titrate. The mispickel carries, according to theory, exactly sufficient iron to precipitate the arsenic as ferric arsenate in an acetic acid solution, so no more iron need be added. The ferric arsenate will separate out as a yellowish-white flocculent precipitate. An example required in duplicate experiment 18.5 c.c. and 18.7 c.c. of barium chloride, equivalent to 18.7% of sulphur. The formula FeS2.FeAS2 requires 19.6%, but the sulphur generally varies considerably from this amount. Determination of sulphur in burnt ores. Take 5 grams of the dried and powdered ore and rub up with 4 grams of nitre. Transfer to the platinum dish. Clean out the mortar with another gram of nitre and add this as a cover. Heat and extract with water as before. Add the sodium acetate and acetic acid and titrate. Burnt ores carry from 2.5 to 5% of sulphur. A series of 4 determinations gave baric chloride required 12.6 c.c., percentage of sulphur 2.52, gravimetric results 2.45%. Baric chloride required 29.9 c.c., percentage of sulphur 5.98, gravimetric results 5.84%. Baric chloride required 18.1 c.c., percentage of sulphur 3.62, gravimetric results 3.53%. Baric chloride required 22.0 c.c., percentage of sulphur 4.40, gravimetric results 4.43%. For ores carrying less than 1% of sulphur, take 10 grams for the assay. Determination of sulphuric oxide, SO3, in sulphates. When the sulphur exists in the sample received by the assayer in an oxidized state as sulphate, it is usual to report it in terms of sulphuric oxide, SO3. In this case, the metal must also be reported as oxide. For example, an analysis of copper sulphate would be thus reported: oxide of copper, CuO, 31.8%, sulphuric oxide, SO3, 32.1%, water 36.1%, total 100.0. The percentage of sulphur multiplied by 2.5 gives the percentage of sulphuric oxide. Thus, a sample of copper sulphate containing 12.85% of sulphur will contain 12.85 times 2.5, or 32.12% of sulphuric oxide. In minerals and metallurgical products, it is common to find the sulphur in both conditions, i.e. as sulphate and sulphide. Generally, in these, the percentage of sulphur only is wanted, but this will depend entirely on commercial requirements, and not on the fancy of the assayer. Soluble sulphates are determined separately by extracting with small quantities of cold water, so as to avoid the separation of basic sulphates, or, if the sulphides present are not at the same time attacked, by dilute hydrochloric acid. Lead sulphate may be extracted by boiling with ammonic acetate, whilst barium, strontium, and perhaps calcium sulphate will mainly be found in the residue insoluble in acids. Weigh up from 2 to 5 grams of the material according to the amount of sulphur judged to be present, and dissolve them in the titrating dish with 1 c.c. of hydrochloric acid and 50 c.c. of water. Add 10 grams of sodic acetate and 10 c.c. of acetic acid. Dilute, boil, and titrate. In the case of ferric salts, half the quantity of acetic acid will be better, as then the ferric ion will be precipitated, and a colourless solution will be left, in which the end reaction is more readily distinguished. Determined in this way, 5 gram samples of the following salts gave the results indicated below. Salt, copper sulphate, barium chloride required, 64.25 c.c., sulphuric oxide, 32.12%. Salt, magnesium sulphate, barium chloride required, 65.25 c.c., sulphuric oxide, 32.62%. Salt, zinc sulphate, barium chloride required, 56.25 c.c., sulphuric oxide, 28.12%. Salt, ferrous sulphate, barium chloride required, 58.25 c.c., sulphuric oxide, 29.12%. Salt, sodium sulphate, Barium chloride required 51.25 cc's. Sulphuric oxide 25.60%. Determination of sulphuric oxide in barytes. Note heavy spar. End note. Fuse 2 grams of the powdered mineral with 5 grams of fusion mixture for 5 minutes, and when cold extract with water. Filter, acidulate the filtrate with an excess of 10 c.c. of acetic acid. Dilute, boil, and titrate. For example, a transparent crystallized sample required 27.0 c.c. of barium chloride, which is equivalent to 13.6% of sulphur, or 34.0% of sulphuric oxide. Theory requires 34.3% of the latter. Since both carbonate of soda and potash are liable to contain sulphates, a blank determination should be made on 5 grams of the fusion mixture, and the amount found be deducted from that got in the assay. Practical exercises. 1. The price of sulphur in an ore being 4d halfpenny per unit in the northern markets, what would be the price of a ton of ore containing 49% of sulphur? What would be the effect on the price of an error of 0.25% in the assay? 2. Barytes carries 50% of sulphur, and on calcining yields 70% of its weight of burnt ore. Supposing the burnt ore carries 3.5% of sulphur, what proportion of the sulphur will have been removed in the calcining? 3. How would blende compare with pyrites as a source of sulphur for sulphuric acid making? 4. How would you determine the percentage of sulphuric oxide in a sample of gypsum? What is sulphuric oxide, and what relation does it bear to sulphur? 5. A mineral contains 20.7% of water, 32.4% of lime, and 18.6% of sulphur. What is its probable composition? What experiment would you try to determine the accuracy of your conclusion? Selenium occurs in nature combined with copper, mercury, and lead in certain rare minerals. In small quantities it is found in many ores. It is detected in solution by the red precipitate produced on boiling the acid solution with sodium sulphite. This reaction is used for its determination. Solution. The solution is affected by boiling with nitric acid or aqua regia, or by fusing with nitre. To separate the selenium, the solution is evaporated with an excess of hydrochloric acid and a little sodium or potassium chloride. This destroys any nitric acid that may be present, and reduces selenic acid, H2SeO4, to selenious, H2SeO3. The solution is diluted with water and treated with a solution of sulphite of soda. It is warmed and at last boiled. The selenium separates as a red precipitate, which on boiling becomes denser and black. It is collected on a weighed filter, washed with hot water, dried at 100 degrees centigrade, and weighed as pure selenium. Selenium can be precipitated with sulphuretted hydrogen as a sulphide, which is readily soluble in ammonium sulphide. This sulphide may be oxidized with hydrochloric acid and chlorate of potash, and the selenium separated in the manner described. Tellurium. Tellurium occurs in nature native, and in combination with gold, silver, bismuth, and lead. It is sometimes met with in assaying gold ores. It may be detected by the purple colour it imparts to strong sulphuric acid when dissolved in the cold, and by the black precipitate of metallic tellurium which its solutions yield on treatment with a reducing agent. Telluric acid is reduced to tellurous with evolution of chlorine on boiling with hydrochloric acid. Solution is affected by boiling with aqua regia or by fusing with nitre and sodium carbonate. Separation. Tellurium closely resembles selenium in its reactions. It is separated and determined in the same way. Like it forms a sulphide soluble in ammonium sulphide. It is distinguished from selenium by the insolubility, in a solution of cyanide of potassium, of the metal precipitated by sodium sulphite, whereas selenium dissolves, forming a soluble potassic selenocyanide. Footnote: Se plus KCy equals KCySe. End footnote. For the determination, solution is affected by fusing with nitre and sodium carbonate, dissolving out the tellurate of potash with water, and boiling with hydrochloric acid. Tellurous compounds are formed with evolution of chlorine, and the solution, on treating with a reducing agent (such as sulphurous acid or stannous chloride), yields metallic tellurium, which is washed, dried at 100 degrees centigrade, and weighed. End of section 40. Section 41 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 17. Arsenic, Phosphorus, Nitrogen. Arsenic. The chief source of the arsenic of commerce is arsenical pyrites, or mispickle, which contains about 45% of arsenic, As. Arsenic also occurs as a constituent of several comparatively rare minerals, and as an impurity it is very widely distributed. White arsenic is an oxide of arsenic, and is obtained by roasting arsenical ores and refining the material, crude arsenic, which condenses in the flues. Arsenic itself is volatile, and many of its compounds have the same property. It forms two well-defined series of salts corresponding to the oxides: arsenious oxide, As2O3, and arsenic oxide, As2O5. These combine with bases to form arsenites and arsenates, respectively. Boiling with nitric acid converts the lower into the higher oxide, and powerful reducing agents, such as cuprous chloride, have the opposite effect. Arsenic may be detected by dissolving the substance in hydrochloric acid or in aqua regia (avoiding an excess of nitric acid), and adding a little of this solution to the contents of a small flask in which hydrogen is being made by the action of zinc and hydrochloric acid. The ignited jet of hydrogen assumes a blue colour if arsenic is present, and a cold porcelain dish held in the flame (figure 67) becomes coated with a dark deposit of metallic arsenic. Reader's note: Figure 67 shows a conical flask with some liquid in it. A thistle funnel passes through the stopper to below the surface of the liquid. Another glass tube passes through the stopper from near the top of the flask to one end of a U-tube. The other end of the U-tube is connected to a glass tube which tapers to a nozzle. There is a flame at the tip of the nozzle. A hand is drawn holding the rounded base of a small evaporating dish to the flame. End reader's note. Antimony produces a similar effect, but is distinguished by the insolubility of its deposit in a cold solution of bleaching powder. Arsenites are distinguished by the volatility of the chloride, by decolorizing a solution of permanganate of potassium, and by immediately giving a yellow precipitate with sulphuretted hydrogen. Arsenates are distinguished, after converting into soda salts, by boiling with carbonate of soda and neutralizing, by giving with nitrate of silver a red precipitate, and with magnesia mixture a white crystalline one. Dry assay. There is no dry assay which is trustworthy. The following method is sometimes used to find the proportion of arsenious oxide in crude arsenic. Weigh up 5 grams of the dried sample and place them in a clean, dry test tube about 6 inches long. Tie a small filter paper over the mouth of the tube so as to prevent air currents. Heat the tube cautiously so as to sublime off the white arsenic into the upper part of the tube. Cut off the bottom of the test tube by wetting whilst hot. Scrape out the arsenic and weigh it. The weight gives an approximate idea of the quantity, and the colour of the quality of the white arsenic obtainable from the sample. Some workers (sellers) weigh the residue and determine the white arsenic by difference. In determining the percentage of moisture in these samples, the substance is dried on a water bath or in a water oven. Wet methods. Solution. Where, as in crude arsenic, the substance is arsenious oxide, As2O3, mixed with impurities, the arsenic is best got into solution by warming with caustic soda and neutralizing the excess with hydrochloric acid. it will be present as sodium arsenite. Metals and alloys are acted on by means of nitric acid, or the arsenic may be at the same time dissolved and separated by distilling with a strongly acid solution of ferric chloride, in the way described under volumetric methods. With minerals, mats, etc., solution is thus effected. The finely powdered substance is mixed in a large platinum or porcelain crucible with from 6 to 10 times its weight of a mixture of equal parts of carbonate of soda and nitre. The mass is then heated gradually to fusion and kept for a few minutes in that state. When cold, it is extracted with warm water and filtered from the insoluble residue. The solution, acidified with nitric acid and boiled, contains the arsenic as sodium arsenate. With mispickel and those substances which easily give off arsenic on heating, the substance is first treated with nitric acid, evaporated to dryness, and then the residue is treated in the way just described. When the arsenic is present as arsenite or arsenide, distillation with an acid solution of ferric chloride will give the whole of the arsenic in the distillate, free from any metal except perhaps tin as stannic chloride. With arsenates, dissolve the substance in acid, and then add an excess of soda. Pass sulphuretted hydrogen into the solution, warm and filter. Acidulate the filtrate and pass sulphuretted hydrogen. Decant off the liquid through a filter, and digest the precipitate with ammonic carbonate. Filter, and reprecipitate with hydrochloric acid and sulphuretted hydrogen. Allow to stand in a warm place and filter off the yellow sulphide of arsenic. Wash it into a beaker, clean the filter paper if necessary with a drop or two of dilute ammonia, evaporate with 10 c.c. of dilute nitric acid to a small bulk, and filter off the globules of sulphur. The filtrate contains the arsenic as arsenic acid. Gravimetric method. Having got the arsenic into solution as arsenic acid, and in a volume not much exceeding 50 c.c., add about 20 c.c. of dilute ammonia and 20 c.c. of magnesia mixture. Stir with a glass rod and allow to settle overnight. Filter and wash with dilute ammonia, avoiding the use of large quantities of wash water. Dry, transfer the precipitate to a Berlin crucible, and clean the filter paper thoroughly. Burn this paper carefully and completely, and add the ash to the contents of the crucible, together with 4 or 5 drops of nitric acid. Evaporate with a Bunsen burner and slowly ignite, finishing off with the blowpipe or muffle. Cool and weigh. The ignited precipitate is pyrarsenate of magnesia, Mg2As2O7, and contains 48.4% of arsenic, As. Instead of igniting the precipitate with nitric acid, it may be collected on a weighed filter paper, dried at 100 degrees centigrade, and weighed as ammonic magnesic arsenate. Note 2Am MgAsO4.H2O, end note, which contains 39.5% of arsenic. The results in this case are likely to be a little higher. The drying is very tedious and is likely to leave behind more water than is allowed for in the formula. In a series of determinations in which the arsenic was weighed in both forms, the results were, reader's note, there are 4 columns: ammonic magnesic arsenate, arsenic, magnesium pyrarsenate, arsenic. All figures are given in grams, end reader's note. Ammonic magnesic arsenate 0.0080, arsenic 0.0032, magnesium pyrarsenate 0.0065, arsenic 0.0031. Ammonic magnesic arsenate 0.0400, arsenic 0.0158, magnesium pyrarsenate 0.0330, arsenic 0.0160. Ammonic magnesic arsenate 0.0799, arsenic 0.0316, magnesium pyrarsenate 0.0633, arsenic 0.0306. Ammonic magnesic arsenate 0.1600, arsenic 0.0632, magnesium pyrarsenate 0.1287, arsenic 0.0623, ammonic magnesic arsenate 0.4000, arsenic 0.1580, magnesium pyrarsenate 0.3205, arsenic 0.1551, ammonic magnesic arsenate 0.7990, arsenic 0.3156, magnesium pyrarsenate 0.6435, arsenic 0.3114. Volumetric methods. There are two methods, one for determining the arsenic in the lower and the other in the higher state of oxidation. In the first mentioned method, this is done by titrating with a standard solution of iodine, and in the latter with a solution of uranium acetate. Where the arsenic already exists as arsenious oxide, or where it is most conveniently separated by distillation as arsenious chloride, the iodine method should be used. But when the arsenic is separated as ammonium magnesic arsenate or as sulphide, the uranium acetate titration should be adopted. Iodine process. This is based on the fact that sodium arsenite in a solution containing an excess of bicarbonate of soda is indirectly oxidized by iodine to sodium arsenate. Footnote: Na3ASO3 plus H2O plus 2I yields Na3ASO4 plus 2HI. The acid is at once neutralized. End footnote. And that an excess of iodine may be recognized by the blue colour it strikes with starch. The process is divided into two parts: 1, the preparation of the solution, and 2, the titration. Preparation of the solution. For substances like crude arsenic, in which the arsenic is present as arsenious oxide, the method is as follows. Take a portion which shall contain from 0.25 to 0.5 gram of the oxide, place in a beaker, and cover with 10 c.c. of sodic hydrate solution. Warm till dissolved. Put a small piece of litmus paper in the solution, and render acid with dilute hydrochloric acid. Add 2 grams of bicarbonate of soda in solution, filter if necessary, and dilute to 100 c.c. The solution is now ready for titrating. Where the arsenic has to be separated as arsenious chloride, the process is as follows. Footnote: Mr. Thomas Gibb is the originator of this ingenious process. End footnote. Weigh up 1 gram of the finely powdered ore. Note: metals should be hammered out into a thin foil or be used as filings. End note. And place in a 16-ounce flask provided with a well-fitting cork, and connected with a U-tube, as shown in the drawing, figure 68. Figure 68 shows a round flask on a stand over a Bunsen burner. The flask is stoppered, and a glass tube leads up from the flask and down to a U-tube in a large container of water. The bottom of the U-tube is divided into 3 bulbs. End reader's note. The U-tube should contain 2 or 3 c.c. of water, and is cooled by being placed in a jar or large beaker of cold water. The water used for cooling should be renewed for each assay. Pour on the assay in the flask 50 c.c. of a ferric chloride mixture made by dissolving 600 grams of calcium chloride and 300 grams of ferric chloride in 600 c.c. of hydrochloric acid, and making up to 1 litre with water. Firmly cork up the apparatus and boil over a small Bunsen burner flame for 15 or 20 minutes, but avoid evaporating to dryness. Disconnect the flask and pour away its contents at once to prevent breakage of the flask by their solidification. The arsenic will be condensed in the U-tube, together with the greater part of the hydrochloric acid. Transfer the distillate to a beaker, washing out the tube 2 or 3 times with water. Add a small piece of litmus paper, neutralise with ammonia, render faintly acid with dilute hydrochloric acid, add 2 grams of bicarbonate of soda in solution, and dilute to 250 c.c. The solution is now ready for titrating. The arsenic comes over in the early part of the distillation, as will be seen from the following experiment, made on 1 gram of copper precipitate, in which experiment the distillate was collected in separate portions at equal intervals, and the arsenic in each portion determined. Time distilling 5 minutes. Iodine required 12.0 c.c. equivalent to arsenic in the distillate 0.0450 gram. Time distilling 5 minutes. Iodine required 0.17 cc, equivalent to arsenic in the distillate 0.0005 gram. Time distilling 5 minutes. Iodine required 0.0 cc. Time distilling 5 minutes. Iodine required 0.0 cc. Time distilling to dryness. Iodine required 0.0 cc. The volume of each distillate was about 5 cc. In this operation, the metals are converted into chlorides by the action of ferric chloride, which gives up a part of its chlorine and becomes reduced to the ferrous salt. The calcium chloride does not enter into the chemical reaction, but raises the temperature at which the solution boils, and is essential for the completion of the distillation. Footnote: by taking hold of the water present, it may prevent the dissociation of arsenious chloride. End footnote. 2 experiments with material containing 3.48% of arsenic gave 1 with ferric chloride alone 2.74%, and 2 with the addition of calcium chloride 3.48%. It is always necessary to make a blank determination with 1 gram of electrotype copper to find out the amount of arsenic in the ferric chloride mixture. Footnote: it is difficult to get ferric chloride free from arsenic, but the following treatment will remove 80 or 90% of the arsenic contained in the commercial material. Dissolve 2 or 3 pounds of ferric chloride with the smallest amount of water that will affect solution, with the addition of 100 c.c. of hydrochloric acid. Add a solution of sulphurous acid in quantity sufficient to reduce 2 or 3% of the iron to the ferrous state. Allow it to stand a week, and then boil to remove the hydrochloric acid added. Nitric acid, which is prejudicial, is also removed by this treatment. End footnote. Unfortunately, a correction is always required. This amounts to about 0.15% of arsenic on each assay, even when the mixture has been purified, and this constitutes the weakness of the method, since in some cases the correction is as much as, or even greater than, the percentage to be determined. The acid distillate containing the arsenious chloride may be left for an hour or so without much fear of oxidation, but it is safer to neutralise and then to add the bicarbonate of soda, as the following experiments show. Several portions of a solution, each having a bulk of 100 c.c., were exposed for varying lengths of time, and the arsenic in each determined. Time exposed, none. Acid solutions. Iodine required 18.2 c.c. equal to 0.0136 gram of arsenic found. Neutralised solutions. Iodine required 18.1 c.c. equals 0.0136 gram of arsenic found. Time exposed 1 hour. Acid solution. Iodine required 18.2 c.c. equal to 0.0136 gram arsenic found. Neutralised solutions. Iodine required 18.2 c.c. equals 0.0136 gram arsenic found. Time exposed 2 hours. Acid solutions. Iodine required 17.7 c.c. equals 0.0133 gram arsenic found. Neutralised solutions. Iodine required 18.0 c.c. equals 0.0135 gram arsenic found. Time exposed 4 hours. Acid solutions. Iodine required 17.5 c.c. equals 0.0131 gram arsenic found. Neutralised solutions. Iodine required 18.4 c.c. equals 0.0138 gram arsenic found. Time exposed 5 hours. Acid solutions. Iodine required 17.0 c.c. equals 0.0127 gram arsenic found. Neutralised solutions. Iodine required 18.3 c.c. equals 0.0137 gram arsenic found. The titration. Make a standard solution of iodine by weighing up in a beaker 16.933 grams of iodine and 30 grams of potassium iodide in crystals. Add a few cc's of water, and when dissolved, dilute to 1 litre. 100 cc's will equal 0.500 gram of arsenic. A solution of starch similar to that used in the iodide copper assay will be required. Use 2 cc's for each assay. Variations in the quantity of starch used do not interfere, but the solution must be freshly prepared, as after 7 or 8 days it becomes useless. To standardize the iodine solution, weigh up 0.3 grams of white arsenic. Dissolve in caustic soda, neutralize. After acidulating, add 2 grams of bicarbonate of soda and 2 cc's of the starch solution, and dilute to 200 cc's with cold water. Fill a burette having a glass stopcock with the iodine solution, and run it into the solution of arsenic, rapidly at first and then more cautiously, till a final drop produces a blue colour throughout the solution. Calculate the standard in the usual way. White arsenic contains 75.76% of arsenic. The following experiments show the effect of variation in the conditions of the titration. Make a solution of arsenic by dissolving 6.60 grams of white arsenic in 100 cc's of sodic hydrate solution. Render slightly acid with hydrochloric acid. Add 10 grams of bicarbonate of soda and dilute to 1 litre. 100 cc's will contain 0.50 gram of arsenic. Effect of varying temperature. The reaction goes on very quickly in the cold, and since there is no occasion for heating, all titrations should therefore be carried out cold. Effect of varying bulk. In these experiments, 20 cc's of arsenic solution were taken, 2 grams of bicarbonate of soda and 2 cc's of starch solution added, and water supplied to the required bulk. The results were bulk 50.0 cc's, iodine required 20.0 cc's. Bulk 100.0 cc's, iodine required 20.0 cc's. Bulk 250.0 cc's, iodine required 20.0 cc's. Bulk 500.0 cc's, iodine required 20.0 cc's. Considerable variation in bulk does not interfere. Effect of varying bicarbonate of soda. This salt must be present in each titration in considerable excess to prevent the interference of free acid. The bicarbonate must be dissolved without heating, as neutral carbonates should be avoided. Bicarbonate added 1 gram. Iodine required 20.1 cc's. Bicarbonate added 2 grams. Iodine required 20.0 cc's. Bicarbonate added 5 grams. Iodine required 20.1 cc's. Bicarbonate added 10 grams. Iodine required 20.0 cc's. These results show that large variation in the quantity of bicarbonate has no effect. Effect of free acid. In these experiments, the arsenic taken, the starch, and the bulk were as before, but no bicarbonate was added. In one case, the solution was rendered acid with 5 cc's of acetic acid, and in the other with 5 cc's of hydrochloric acid. In both cases, the interference was strongly marked, and no satisfactory finishing point could be obtained. This was much more marked with the hydrochloric acid. Effect of foreign salts. The process for getting the arsenic into solution will exclude all metals except tin, but the solution will be charged with sodium or ammonium salts in the process of neutralizing, so that it is only necessary to see if these cause any interference. The alkaline hydrates, including ammonia, are plainly inadmissible, since no free iodine can exist in their presence. Monocarbonates similarly interfere, but to a much less extent. Hence the necessity for rendering the assay distinctly acid before adding the bicarbonate of soda. With 20 cc's of arsenic solution, and with bulk, soda and starch as before, the results obtained were: with 20 grams of ammonic chloride, iodine required 20.0 cc's. With 20 grams of sodium chloride, iodine required 20.0 cc's. With 20 grams of sodium acetate, iodine required 20.0 cc's. With 0.050 gram of tin as stannic chloride, iodine required 19.6 cc's. Without any addition, 20.0 cc's. The interference of the stannic salt is probably mechanical, the precipitate carrying down some arsenious acid. Effect of varying arsenic. With bulk, starch and soda as before, but with varying arsenic, the results were: arsenic added 1.0 cc, iodine required 1.1 cc, arsenic added 10.0 cc, iodine required 9.9 cc, arsenic added 20.0 cc, iodine required 20.0 cc, arsenic added 50.0 cc, iodine required 50.0 cc, arsenic added 100.0 cc, iodine required 100.0 cc. Determination of arsenic in metallic copper. Put 1 gram of the copper filings, freed from particles of the file with a magnet, into a 16-ounce flask, and distill with the ferric chloride mixture as above described. Neutralise the distillate, acidify, add bicarbonate of soda and starch, dilute, and titrate with the standard solution of iodine. Footnote: when the amount of arsenic to be estimated is small, as in refined coppers, it is better to use a weaker solution of iodine. This is made by diluting 200 cc of the standard solution with water to 1 litre. Each cc will equal 0.1% if 1 gram of the metal has been taken for the assay. End footnote. Make a blank determination with 1 gram of electrotype copper, proceeding exactly as with the assay, and deduct the amount of arsenic found in this experiment from that previously obtained. Working in this way on a copper containing 0.38% of arsenic and 0.80% of antimony, 0.38% of arsenic was found. Determination of white arsenic in crude arsenic. Weigh out 1 gram of the dried and powdered substance, or 0.5 gram if rich, and digest with 10 cc of a 10% solution of soda. Dilute to about 50 cc and filter. Render faintly acid with hydrochloric acid, and filter if necessary. Add 2 or 3 grams of bicarbonate of soda in solution, then 5 cc of starch, and titrate the cold solution with the standard solution of iodine. The following is an example. 1 gram of crude arsenic required 53.7 cc iodine. 100 cc iodine equals 0.6000 gram white arsenic. 100 to 53.7 is equivalent to 0.6 to 0.3222, or 32.2%. With the test tube method of dry assaying, this same sample gave results varying from 33 to 35% of white arsenic, which, judging from its appearance, was impure. Uranic acetate process. This may be looked upon as an alternative to the gravimetric method. It is applicable in all cases where the arsenic exists in solution as arsenic acid or as arsenate of soda. The process may be considered in 2 parts: 1, the preparation of the solution, and 2, the titration. Preparation of the solution. If the arsenic has been separated as sulphide, it is sufficient to attack it with 10 or 15 cc of nitric acid, and to heat gently till dissolved, avoiding too high a temperature at first. Afterwards, continue the heat till the separated sulphur runs into globules and the bulk of the acid has been reduced to 3 or 4 cc. Dilute with 20 or 30 cc of water, put in a piece of litmus paper, and add dilute ammonia until just alkaline. Then add 5 cc of the sodium acetate and acetic acid solution, which should make the solution distinctly acid. Dilute to 150 cc and heat to boiling. The solution is ready for titrating. When the arsenic exists in a nitric acid solution mixed with much copper, it is separated in the way described under Examination of Commercial Copper. Note Arsenic and Phosphorus. End note. Pages 208-209. If the arsenic has been separated as ammonium magnesium arsenate and phosphates are known to be absent, dissolve the precipitate, note after filtering but without washing, end note, in dilute hydrochloric acid. Add dilute ammonia till a slight precipitate is formed, and then 5 cc of the sodium acetate and acetic acid solution. Dilute to 150 cc and heat to boiling. Titrate. If phosphates are present, note which will always be the case if they were present in the original substance and no separation with sulphuretted hydrogen has been made, end note, the phosphorus will count in the subsequent titration as arsenic, note 1 part of phosphorus counting as 2.5 parts of arsenic, end note. It will be necessary to dissolve the mixed arsenate and phosphate of magnesia in hydrochloric acid. Add about 4 or 5 times as much iron, as ferric chloride, as the combined phosphorus and arsenic present will unite with, and separate by the basic acetate process as described under phosphorus in the examination of commercial copper, page 209. Obviously, when phosphates are present, it is easier to separate the arsenic as sulfide than to precipitate it with the magnesia mixture. The titration. The standard solution of uranium acetate is made by dissolving 34.1 grams of the salt, with the help of 25 c.c. of acetic acid, in water, and diluting to 1 litre. The water and acid are added a little at a time and warmed till solution is affected, then cooled and diluted to the required volume. 100 c.c. will equal 0.50 gram of arsenic. The sodic acetate and acetic acid solution is made by dissolving 100 grams of sodic acetate in 500 c.c. of acetic acid and diluting with water to 1 litre. 5 c.c. are used for each assay. The solution of potassic ferrocyanide used as indicator is made by dissolving 10 grams of the salt in 100 c.c. of water. To standardize the solution of uranium acetate, weigh up a quantity of white arsenic, As2O3, which shall be about equivalent to the arsenic contained in the assay, 0.1 or 0.2 gram. Transfer to a flask and dissolve in 10 c.c. of nitric acid with the aid of heat. Evaporate to a small bulk, taking care to avoid the presence of hydrochloric acid. Dilute with water, add a small piece of litmus paper, render faintly alkaline with ammonia, then add 5 c.c. of the sodic acetate mixture. Dilute to 150 c.c. and heat to boiling. Fill an ordinary burette with the uranium acetate solution and run into the assay a quantity known to be insufficient. Again, heat for a minute or two. Arrange a series of drops of the solution of ferrocyanide of potassium on a porcelain slab, and with the help of a glass rod, bring a drop of the assay solution in contact with one of these. If no colour is produced, run in the uranium acetate 1 c.c. at a time, testing after each addition, till a brown colour is developed. It is best to overdo the assay and to count back. It is not necessary to filter off a portion of the assay before testing with the ferrocyanide, since the precipitate, uranic arsenate, has no effect. The following experiments show the effect of variation in the conditions of titration. Make a solution of arsenic acid by dissolving 4.95 grams of arsenious acid, As2O3, in a covered beaker with 35 c.c. of nitric acid. Evaporate down to 7 or 8 c.c. and dilute with water to 1 litre. 100 c.c. will contain 0.375 gram of arsenic. Use 20 c.c. for each experiment. Effect of varying temperature. It is generally recommended to titrate the boiling solution, since it is possible that the precipitation is only complete on boiling. Low results are obtained in a cold solution, the apparent excess of uranium acetate striking a colour at once. On boiling, however, it ceases to do so. Consequently, the solution should always be boiled directly before testing. In 4 experiments made in the way described, but with 20 c.c. of a solution of arsenic acid stronger than that given, note 100 c.c. equals 0.5 gram arsenic, end note. The results at varying temperatures were: temperature 15 degrees centigrade, uranium required 18.0 c.c. Temperature 30 degrees centigrade, uranium required 18.5 c.c. Temperature 70 degrees centigrade, uranium required 18.5 c.c. Temperature 100 degrees centigrade, uranium required 18.7 c.c. Effect of varying bulk. These experiments were like those last mentioned, but were titrated boiling, and the volume was varied. Bulk 50.0 cc, uranium required 14.0 cc. Bulk 100.0 cc, uranium required 14.0 cc. Bulk 200.0 cc, uranium required 14.5 cc. Bulk 300.0 cc, uranium required 15.0 cc. Considerable variations in bulk are to be avoided. Effect of varying sodium acetate. These experiments were carried out like those last noticed, but the bulk was 150 cc, and varying amounts of sodic acetate were added in excess of the quantity used in the experiments previously described. Sodic acetate added 0 gram, uranium required 14.5 cc. Sodic acetate added 1 gram, uranium required 14.5 cc. Sodic acetate added 10 grams, uranium required 16.0 cc. Sodic acetate added 20 grams, uranium required 18.0 cc. It is evidently important that the quantity of this salt present in each titration be measured out so as to avoid variation. Effect of varying the sodium acetate and acetic acid solution. Acetic acid also affects the results, but in the opposite direction, by preventing the precipitation of uranium arsenate. With varying volumes of the solution now under notice, the results were: solution added 0.0 cc, uranium required 14.5 cc. Solution added 5.0 cc, uranium required 14.5 cc. Solution added 10.0 cc, uranium required 14.5 cc. Solution added 15.0 cc, uranium required 14.0 cc. Solution added 20.0 cc, uranium required 13.2 cc. Solution added 30.0 cc, uranium required 10.0 cc. Solution added 40.0 cc, uranium required 6.0 cc. Solution added 50.0 cc, uranium required 2.0 cc. These show that the quantity ordered, 5 cc, must be adhered to. Effect of foreign salts. In these experiments 10 grams of the salt, the effect of which it was desired to determine, were added to a solution in other respects resembling those previously used. Salt added ammonic sulphate, uranium required 15.5 cc. Salt added ammonic nitrate, uranium required 15.5 cc. Salt added ammonic chloride, uranium required 15.3 cc. Salt added magnesium sulphate, uranium required 15.3 cc. Without any addition, 15.0 cc were required, and in another experiment in which 30 grams of ammonic salts were present, 15.6 cc of uranium solution were required. Such variations in the amount of ammonic salts as occur in ordinary working are unimportant. Phosphates, of course, interfere. In fact, the uranium acetate solution can be standardized by titrating with a known weight of phosphate and calculating its equivalent of arsenic. Thus, in an experiment with 0.6 gram of hydric sodic phosphate, note Na2HPO4.12H2O, end note, equivalent to 0.05195 gram of phosphorus or 0.1256 gram of arsenic, 23.25 cc of a solution of uranium acetate were required. The same solution, standardized with white arsenic, gave a standard of which 100 cc equals 0.5333 gram arsenic. On this standard, the 0.6 gram of sodic phosphate should have required 23.5 cc. Experiments in which 0.1 gram of bismuth and 0.1 gram of antimony were present, with 0.1 gram of arsenic, showed no interference on the titration. Ferric or aluminic salts would remove their equivalent of arsenic, and consequently must be removed before titrating. Effect of varying arsenic. Varying amounts of metallic arsenic were weighed up and dissolved in nitric acid, etc., and titrated. Arsenic taken, 0.010 gram. Arsenic found 0.010 gram. Arsenic taken 0.050 gram. Arsenic found 0.050 gram. Arsenic taken 0.100 gram. Arsenic found 0.100 gram. Arsenic taken 0.200 gram. Arsenic found 0.197 gram. These experiments show that the method yields good results within these limits. Determination of arsenic in mispickle. Weigh up 1 gram of the dried and powdered ore and evaporate to near dryness with 20 c.c. of dilute nitric acid. Make up to 100 c.c. with water and pass sulphuretted hydrogen to reduce the ferric ion to the ferrous state. Then add 20 c.c. of dilute ammonia and again pass sulphuretted hydrogen. Warm, filter, and evaporate the filtrate to drive off the excess of ammonia. Then add 10 c.c. of nitric acid and boil down till the sulphide of arsenic at first precipitated is dissolved. Neutralise, add 5 c.c. of sodium acetate and acetic acid solution, transfer to a pint flask, boil and titrate. For example, an impure sample of ore required in duplicate assay of half a gram each. When treated in the above mentioned way, 39.6 and 39.5 c.c. of the uranium acetate solution. Note 100 c.c. equals 0.537 gram of arsenic. End note. Equivalent to 0.2114 gram of arsenic, or 42.3%. An alternative method is as follows. Powder the ore very finely and weigh up 0.5 gram. Place in a 2 3/4 inch Berlin dish and add strong nitric acid 1 drop at a time until the action ceases. With care, there need be no very violent reaction. Dry over a water bath. Cover with 2 grams of niter, and over this spread 5 grams of a mixture of equal parts of niter and carbonate of soda. Fuse in a muffle or over a large gentle blowpipe flame for 4 or 5 minutes. This will spoil the dish. Allow to cool and boil out in a larger dish with 100 c.c. of water. Filter and wash into an 8-ounce flask. Acidify the liquor with nitric and boil down to about 100 c.c. The acid should not be in too large excess, but an excess is needed to destroy nitrites. Neutralise with soda or ammonia, add 5 c.c. of the mixture of sodium acetate and acetic acid. Titrate with uranium acetate. Determination of arsenic, As, in crude arsenic. The method given under the iodine titration simply determines that portion of the arsenic which is present in the substance as arsenious oxide, or white arsenic. The following method will give the total arsenic in the sample. It would be incorrect to report this as so much % of arsenious oxide, although it may be reported as so much % of arsenic, equivalent to so much % of white arsenic. Thus, arsenic 30.0%, equivalent to white arsenic 39.6%. The equivalent of white arsenic is calculated by multiplying the percentage of arsenic by 1.32. The method of determining the percentage of arsenic is as follows. Boil 1 gram of the sample with 10 c.c. of nitric acid. When the bulk of the solution has been reduced to 1/2 and red fumes are no longer evolved, dilute with a little water and filter into a flask. Neutralise the filtrate, add 5 c.c. of sodic acetate solution, boil and filter. The precipitate, ferric arsenate, is transferred to a small beaker, treated with 5 c.c. of dilute ammonia, and sulphuretted hydrogen passed through it. The iron sulphide is filtered off, and the filtrate evaporated with an excess of nitric acid. When the solution is clear, it is neutralised, and 1 or 2 c.c. of sodic acetate solution having been added, is then mixed with the first filtrate. The solution is boiled and titrated. A sample treated in this way required 49.2 c.c. of the uranium acetate solution. Note 100 c.c. equals 0.537 gram of arsenic, end note, equivalent to 26.4%. Determination of arsenic in brimstone. Take 10 grams of the substance and powder in a mortar. Rub up with 10 c.c. of dilute ammonia and a little water. Rinse into a pint flask. Pass a current of sulphuretted hydrogen and warm on a hot plate for a few minutes. Filter, acidulate the filtrate with sulphuric acid, filter off the precipitate, attack it with 10 c.c. of nitric acid, and proceed as in the other determinations. Practical exercises. 1. Miss Pickle contains 45.0% of arsenic. To how much white arsenic will this be equivalent? 2. How would you make a standard solution of iodine so that 100 c.c. shall be equivalent to 1 gram of white arsenic? 3. What weight of arsenic is contained in 1 gram of pyrarsenate of magnesia, and what weight of ammonic magnesic arsenate would it be equivalent to? 4. The residue, after heating 10 grams of crude arsenic, weighed 0.62 gram. What information does this give as to the composition of the substance? If another 10 grams of the substance heated on a water bath lost 0.43 gram, what conclusions would you draw, and how would you report your results? 5. If a sample of copper contained 0.5% of arsenic, and 1 gram of it were taken for an assay, how much standard uranium acetate solution would be required in the titration? End of section 41. Section 42 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 17. Arsenic, Phosphorus, Nitrogen. Phosphorus and Phosphates. Phosphorus rarely occurs among minerals except in its highest oxidized state, phosphoric oxide, P2O5, in which it occurs abundantly as rock phosphate, a variety of apatite which is mainly phosphate of lime. Phosphates of most of the metallic oxides are found. Phosphoric oxide in small quantities is widely diffused, and is a constituent of most rocks. Its presence in varying amounts in iron ores is a matter of importance, since it affects the quality of the iron obtainable from them. Phosphorus occurs in alloys in the unoxidized state. It is directly combined with the metal, forming a phosphide. In this manner it occurs in meteoric iron. The alloy, phosphor-bronze, is made up of copper, tin, zinc, and phosphorus. Phosphates are mined in large quantities for the use of manure manufacturers and for making phosphorus. Phosphorus and arsenic closely resemble each other in their chemical properties, more especially those which the assayer makes use of for their determination. Phosphorus forms several series of salts, but the phosphates are the only ones which need be considered. Pyrophosphate of magnesia, which is the form in which phosphoric oxide is generally weighed, differs from the ordinary phosphate in the proportion of base to acid. Metaphosphates differ in the same way. If these are present, it must be remembered they act differently with some reagents from the ordinary phosphates, which are called orthophosphates. They are, however, all convertible into orthophosphates by some means which will remove their base, such as fusion with alkaline carbonates, boiling with strong acids, etc. Footnote: the constitution of these phosphates may be thus illustrated. Magnesic metaphosphate, MgO.P2O5. Magnesic pyrophosphate, 2MgO.P2O5. Magnesic orthophosphate, 3MgO.P2O5. End footnote. Phosphides are converted into phosphates by the action of nitric acid or other oxidizing agents. Dilute acids, when they act on the substance, evolve phosphoretted hydrogen, pH 3. The student should be on his guard against losing phosphorus in this manner. There is no dry assay for phosphorus, All assays for it are made either gravimetrically or volumetrically. The separation of phosphoric oxide is made as follows. The ore or metal is dissolved in acid and evaporated to render the silica insoluble. It is taken up with hydrochloric acid, diluted with water, and treated with sulphuretted hydrogen. The filtrate is boiled to get rid of the excess of gas, and treated with nitric acid to peroxidize the iron present. If the iron is not present in more than sufficient quantity to form ferric phosphate with all the phosphorus present, some ferric chloride is added. The iron is then separated as basic acetate. The precipitate will contain the phosphorus together with any arsenic acid not reduced by the sulphuretted hydrogen. The precipitate should have a decided brown colour. The precipitate is washed, transferred to a flask, and treated first with ammonia and then with a current of sulphuretted hydrogen. The filtrate from this, acidulated with hydrochloric acid and, if necessary, filtered, contains the phosphorus as phosphoric acid. This method is not applicable in the presence of alumina, chromium, titanium, or tin if the solution is affected with nitric acid. The precipitate obtained by the action of nitric acid on tin retains any phosphoric or arsenic oxide that may be present. A method of separation more generally applicable and more convenient to work is based on the precipitation of a yellow phosphomolybdate of ammonia. Footnote: the composition of which is MoO2 90.74%, P2O5 3.14%, NH4 twice O 3.57%, H2O 2.55% equals 100.00%. End footnote. By the action of an excess of ammonic molybdate upon a solution of a phosphate in nitric acid, dissolve the substance by treatment with acid and evaporate to dryness. Take up with 10 c.c. of nitric acid and add 20 grams of ammonic nitrate together with a little water. Next, put in the solution of ammonium molybdate in the proportion of about 50 c.c. for each 0.1 gram of phosphoric oxide judged to be present. Warm to about 80 degrees centigrade and allow to stand for an hour. Filter and wash with a 10% solution of ammonic nitrate. It is not necessary that the whole of the precipitate be placed on the filter, but the beaker must be completely cleaned. Dissolve the precipitate off the filter with dilute ammonia and run the solution into the original beaker. Run in from a burette, slowly and with stirring, magnesia mixture, using about 15 c.c. for each 0.1 gram of phosphoric oxide. Allow to stand for 1 hour. The white crystalline precipitate contains the phosphorus as ammonium magnesium phosphate. Phosphate of lead is decomposed by sulphuric acid. The lead is converted into the insoluble lead sulphate, and the phosphoric acid is dissolved. Phosphate of copper and phosphate of iron may be treated with sulphuretted hydrogen, the former in an acid and the latter in an alkaline solution. Phosphate of alumina is generally weighed without separation of the alumina, since this requires a fusion. In all cases, the aim is to get the phosphoric oxide either free or combined with some metal whose phosphate is soluble in ammonia. Yearsley's method of separation is as follows. 1 to 10 grams of the sample are treated with hydrochloric acid and evaporated to dryness, with the addition, if any pyrites is present, of a little nitric acid. The residue is taken up with hydrochloric acid, cooled, transferred to a graduated flask, and diluted to the mark. It is then shaken up, filtered through a dry filter, and a measured portion, containing about 0.05 gram of phosphoric acid, transferred to a small beaker. 10 c.c. of a citric acid solution of magnesia is added. Footnote: this is made by adding 27 grams of magnesium carbonate, note a little at a time, end note, to a solution of 270 grams of citric acid in 350 c.c. of warm water, and when dissolved, adding 400 c.c. of dilute ammonia and making up the bulk to 1 litre. 20 cc of the solution is sufficient for 0.1 gram of P2O5, although more will be required if much iron or alumina is present. End footnote. And then an excess of ammonia. If an immediate precipitate is formed, a fresh portion must be measured out and treated with 20 cc of the citrate of magnesia solution and with ammonia, as before. The beaker is put aside for from 2 to 12 hours. The precipitate is then filtered off and washed with weak ammonia. It contains the phosphorus as ammonium magnesium phosphate. Gravimetric determination. If the phosphate is not already in the form of ammonic magnesic phosphate, it is converted into this by the addition to its solution of an excess of ammonia and magnesia mixture. In order to get the precipitate pure, the magnesia mixture is run in gradually by drops from a burette with constant stirring. A white crystalline precipitate at once falls if much phosphorus is present, but if there is only a small quantity, it may be an hour or two before it shows itself. The solution is best allowed to rest for 12 or 15 hours, note overnight, end note, before filtering. The presence of tartaric acid should be avoided, and the appearance of the precipitate should be crystalline. The solution is decanted through a filter, and the precipitate washed with dilute ammonia using as little as may be necessary. The precipitate is dried, transferred to a weighed Berlin or platinum crucible. The filter paper is carefully burnt and its ash added to the precipitate, which is then ignited, at first gently over a Bunsen burner, and then more strongly over the blowpipe or in the muffle. The residue is a white mass of magnesium pyrophosphate containing 27.92% of phosphorus or 63.96% of phosphoric oxide. Volumetric method. Instead of separating and weighing this compound, the phosphoric oxide in it can be determined by titration. In many cases the ore may be dissolved and immediately titrated without previous separation. It is better, however, to carry the separation so far as to get phosphoric acid, an alkaline phosphate, or the magnesia precipitate. It may then be prepared for titration in the following way. The precipitate in the last case, without much washing, is dissolved in a little hydrochloric acid, and the solution, in any case, rendered fairly acid. Dilute ammonia is added till it is just alkaline, and then 5 cc of the sodic acetate and acetic acid mixture, note, as described under the arsenic assay, end note. This should yield a clear, distinctly acid solution. It is diluted to 100 or 150 cc, heated to boiling and titrated with the uranium acetate solution, using that of potassic ferrocyanide as indicator. The standard solution required is made by dissolving 35 grams of uranium acetate in water with the aid of 25 cc of acetic acid and diluting to 1 litre. An equivalent solution of phosphoric oxide is made by dissolving 25.21 grams of crystallized hydric disodic phosphate, note HNA2PO4.12H2O, end note, in water, and making up to 1 litre. 100 cc will contain 0.5 gram of phosphoric oxide, P2O5, or 0.2183 gram of phosphorus. In making this solution, transparent crystals only must be used. The uranium acetate solution is only approximately equivalent to this, so that its exact standard must be determined. Sodic acetate and acetic acid solution. It is the same as that described under arsenic. Footnote: for the details of the titration, the student is referred to the same place. End footnote. Use 5 cc for each assay. The following experiments show the effect of variation in the conditions of the titration. Effect of varying temperature. The solution should be titrated while boiling. This is especially necessary for the last few cc's in order to get a decided and fixed finishing point. Temperature 15 degrees centigrade. Uranium required 18.0 cc. Temperature 30 degrees centigrade. uranium required 19.2 cc, temperature 70 degrees centigrade. Uranium required 19.0 cc, temperature 100 degrees centigrade. Uranium required 18.9 cc. Effect of varying bulk. Bulk 50.0 cc, uranium required 18.8 cc. Bulk 100.0 cc, uranium required 18.9 cc. Bulk 200.0 cc, uranium required 19.0 cc. Bulk 300.0 cc, uranium required 19.3 cc. Variation in bulk affects the results, therefore a constant bulk should be adhered to. Effect of varying sodium acetate and acetic acid solution. Sodium acetate and acetic acid solution 0.0 cc, uranium required 18.9 cc. Sodium acetate and acetic acid solution 1.0 cc, uranium required 18.9 cc. Sodium acetate and acetic acid solution 5.0 cc, uranium required 19.0 cc. Sodium acetate and acetic acid solution 10.0 cc, uranium required 18.8 cc. Sodium acetate and acetic acid solution 20.0 cc, uranium required 17.5 cc. As in the titration with arsenates, an excess is dangerous to the assay. A definite quantity, 5 cc, should therefore be used. Effect of foreign salts. Besides the sodium acetate, etc., added, the only salts likely to be present are those of ammonia and magnesia. In 3 experiments, in one of which no foreign salts were introduced, while in the other 2, 5 grams of ammonic chloride and of magnesium sulfate respectively were added, there were required, with ammonic chloride, 18.8 cc of uranium solution, with magnesium sulfate, 19.0 cc of uranium solution, without foreign salts, 18.9 cc uranium solution. Effect of varying phosphate. Phosphate solution added 10.0 cc, uranium required 9.8 cc. Phosphate solution added 20.0 cc, uranium required 18.9 cc. Phosphate solution added 50.0 cc, uranium required 47.6 cc. Phosphate solution added 100.0 cc, uranium required 94.5 cc. The quantity of phosphoric oxide in the assay solution for the conditions of titration should not be much less than 0.05 gram. For smaller quantities, the uranium solution should be diluted to half its strength, and the assay solution concentrated by reducing its bulk to 50 cc and using 2.5 cc of the sodium acetate and acetic acid solution. Determination of phosphoric oxide in apatite. Weigh up 0.5 gram of the dried and powdered sample and dissolve it in 5 cc of hydrochloric acid. Evaporate to a paste, add 5 cc of the sodic acetate and acetic acid solution. Dilute to 100 cc with water, boil, and titrate with uranium acetate solution. In an example, 0.5 gram of apatite required 37.4 cc of uranium acetate solution. Note standard equal to 0.5291 gram of phosphoric oxide. End note. The sample therefore contained 0.1979 gram of P2O5, equal to 39.58%. Determination of phosphoric oxide in an iron ore. Take 10 grams, boil with 50 cc of hydrochloric acid, and evaporate to a paste. Take up with 10 cc of dilute hydrochloric acid and dilute with water to 400 cc. Pass sulphuretted hydrogen for nearly a quarter of an hour. Warm and filter. Boil off the excess of gas. Cool. Add ammonia till nearly neutral, and then a few drops of ferric chloride solution and 4 or 5 grams of sodium acetate with a drop or 2 of acetic acid. Boil and filter. Dissolve the precipitate in hot dilute hydrochloric acid and add citro-magnesia mixture and ammonia. Allow to stand overnight. Filter, ignite, and weigh. In an example, 10 grams of ore gave 28.5 milligrams of magnesic pyrophosphate, which is equivalent to 0.18% of phosphoric oxide. Determination of phosphorus in iron. Take from 2 to 10 grams, according to the amount of phosphorus present, and dissolve in aqua regia, keeping the nitric acid in excess. Evaporate to dryness and take up with hydrochloric acid. Boil, dilute, and filter. Add 10 cc of nitric acid. Nearly neutralize with ammonia. Render acid with 3 or 4 cc of nitric acid, and add 10 or 20 cc of ammonic molybdate solution. Heat for some time, allow to settle. Filter and wash the precipitate with a solution of ammonic nitrate. Dissolve the precipitate in dilute ammonia, nearly neutralize with dilute hydrochloric acid, and add first magnesia mixture and then ammonia. Allow to stand overnight. Filter, wash with dilute ammonia, dry, ignite, and weigh as magnesic pyrophosphate. Calculate to phosphorus. Practical exercises. 1. 10 grams of an iron yielded 12 milligrams of pyrophosphate of magnesia. What percentage of phosphorus did the metal contain? 2. 10 grams of an iron ore gave 12 milligrams of pyrophosphate. What percentage of phosphoric oxide did it contain? 3. What weight of apatite? 3Ca3 open brackets PO4 close brackets twice dot CaClF would require 50 cc of standard uranium solution. Note, 100 cc equal to 0.5 gram of P2O5. End note. 4. You have reason to believe that a precipitate which has been weighed as magnesic pyrophosphate contains some arsenate. How would you determine the amount of phosphate really present? 5. 20 cc of a solution of sodic phosphate containing 0.100 gram of P2O5 was found to require a solution containing 0.700 gram of hydrated uranium acetate in a titration. The precipitate contains 80.09% uranium oxide and 19.91% of phosphoric oxide. What percentage of uranium oxide was contained in the uranic acetate? Nitrogen and nitrates. Nitrogen occurs in nature in the free state and forms about 4/5 of the atmosphere. In combination as nitrate, it is found in niter, KNO3, and Chile saltpeter, NaNO3, minerals which have a commercial importance. The latter occurs in beds and is extensively worked for use as a manure and in the preparation of nitric acid. Nitrogen is mainly characterized by negative properties, although many of its compounds are very energetic bodies. It is a gas present everywhere, but so inactive that the assayer can always afford to ignore its presence, and except in testing furnace gases, etc., he is never called on to determine its quantity. The nitrates are an important class of salts and may be looked on as compounds of the bases with nitric pentoxide, N2O5. They are, with the exception of a few basic compounds, soluble in water, and are remarkable for the ease with which they give up their oxygen. The alkaline nitrates fuse readily and lose oxygen with effervescence, forming nitrites, while at a higher temperature they yield more oxygen and lose their nitrogen, either as a lower oxide or as nitrogen. The nitrates of the metals, on heating, leave the oxide of the metal. It is as yielders of oxygen that nitrates are so largely used in the manufacture of explosives. Gunpowder contains from 65 to 75% of potassium nitrate, niter. Nitrates are best detected and determined by their yielding nitric oxide when treated with sulphuric acid and a suitable reducing agent, such as ferrous sulfate, mercury, or copper. Nitric oxide is a colourless gas very slightly soluble in water. It combines at once with oxygen on mixing with the air to form brown nitrous fumes, and dissolves in a solution of ferrous sulphate, producing a characteristic blackish-brown colour. It is this colour which affords the best and most easily applied test for nitrates. The substance suspected to contain nitrates is dissolved in about 1 cc of water and treated with an equal volume of strong sulphuric acid. After cooling, a solution of ferrous sulphate is poured on its surface so as to form a layer resting on it. On standing, a brown or black ring is developed where the liquids join, if any nitrate or nitrite is present. Nitrites are distinguished from nitrates by effervescing and yielding brown fumes when treated with a little dilute sulphuric acid. The separation of nitrates is in many cases difficult. Generally, on treating the substance with water, the nitrate will be in the solution and is filtered off from any insoluble matter. In the exceptional cases, it is got into solution by treating with a boiling solution of sodium carbonate. The filtrate will contain it as an alkaline nitrate. Since, however, in their determination nitrates are never separated and weighed as such, the difficulty of separating them has little importance. Usually the determination can be made on the original aqueous solution, and it is never necessary to do more than remove any special substance which has a bad effect, and this is easily done by the usual reagents. Gravimetric determination. It follows from what has been said that there is no direct gravimetric determination. The percentage of nitrogen pentoxide, N2O5, in a comparatively pure nitrate is sometimes determined indirectly in the following way. Place in a platinum crucible 4 or 5 grams of powdered and cleaned quartz. Ignite, cool in a desiccator, and weigh with the cover. Mix 1 gram of the dried and powdered salt with the quartz in the crucible by stirring with a stout platinum wire. Cover the crucible and heat in a Bunsen burner flame at scarcely visible redness for half an hour. Cool and weigh. The loss in weight gives the amount of nitrogen pentoxide. Sulphates and chlorides in moderate quantity do not interfere. The following is an example of the process. Crucible and sand, 26.6485 grams. Nitre taken, 1.0000 grams. Total, 27.6485 grams. Weight after ignition, 27.1160 grams. Loss on ignition, 0.5325 grams. This is equal to 53.25% of nitrogen pentoxide. Volumetric determination. This is based on the oxidizing action of nitric acid or of nitrates in acid solutions on ferrous salts. The pentoxide, N2O5, of the nitrate is reduced to nitric oxide, NO, so that 336 parts of iron peroxidized represents 108 parts of nitric pentoxide as oxidizing agent. Footnote: N2O5 plus 6FeO yields 3Fe2O3 plus 2NO. End footnote. The quantity of iron peroxidized is determined by taking a known quantity of ferrous salt, oxidizing with a weighed sample of nitrate, and then determining the residual ferrous iron by titration with bichromate or permanganate of potassium solution. The difference between the ferrous iron taken and that found gives the amount oxidized by the nitrate. The speed with which nitric oxide takes up oxygen from the air and thus becomes capable of oxidizing more iron renders some precautions necessary. Ferrous chloride should therefore be used, since it is easier to expel nitric oxide by boiling from solutions of a chloride than it is from those of a sulphate. The process is as follows. Dissolve 2 grams of thin soft iron wire in 50 cc of hydrochloric acid in a flask provided with an arrangement for maintaining an atmosphere of carbon dioxide. When the iron has dissolved, allow the solution to cool and add 0.5 gram of the nitrate. Heat gently for a few minutes and then boil until the nitric oxide is expelled. An atmosphere of carbon dioxide must be kept up. Dilute with water and titrate the residual iron with standard solution of bichromate of potassium. The standard bichromate is made by dissolving 17.5 grams of the salt, K2Cr2O7, in water and diluting to 1 litre. 100 cc's equal 2 grams of iron. Deduct the weight of iron found from the 2 grams originally taken and multiply by 0.3214. This gives the weight of the pentoxide in the sample. In an example, 0.5 gram of nitre was taken and 59.4 cc's of the bichromate solution were required. The 59.4 cc's thus used are equivalent to 1.198 gram of iron. This leaves 0.822 gram as the quantity oxidized by the nitre, which, multiplied by 0.3214, gives 0.2642 gram for the nitrogen pentoxide, or 52.8%. Gasometric method. This is based upon the measurement of the nitric oxide evolved on shaking up a weighed quantity of the nitrate with sulphuric acid over mercury in a nitrometer. Each cc of nitric oxide obtained, when reduced to normal temperature and pressure, is equivalent to 0.627 mg of nitrogen, 1.343 mg of nitric oxide, 2.418 mg of nitric pentoxide, 2.820 mg of nitric acid, 3.805 mg of sodium nitrate, 4.523 mg of potassium nitrate. In working on substances not rich in nitrates, an ordinary nitrometer, note figure 69, end note, is used. But in the assay of sodium nitrate, nitroglycerin, etc., an instrument provided with a bulb having a capacity of 100 cc's is employed. Reader's note. Figure 69 shows a clamp holding 2 vertical glass tubes connected by a loop of rubber tubing, from which a short outlet tube is closed by a clip. The glass tubes are approximately a third full of mercury. The level is the same in each tube. The top of the right-hand tube is open. The top of the left-hand tube is closed by a stopcock with a cup leading into it from above. End reader's note. The plan of working is as follows. The measuring tube is filled with mercury until it reaches up into the tap, and the levelling tube is placed so that it contains an inch or two of mercury. If the nitrate is in solution, 2 or 3 cc's of the liquid. Note, dilute liquids are brought to this bulk by evaporation. End note, are measured into the cup. The levelling tube is lowered a little and the tap cautiously opened until all but the last drop of the liquid has run in. The cup is then rinsed with 2 or 3 cc's of sulphuric acid, which is run in the same way, and the operation is repeated with another lot of acid. The measuring tube is now taken from the clamp and shaken for 2 or 3 minutes until no more gas is given off. It is replaced and the mercury level in the 2 tubes adjusted. Then it is allowed to stand until the froth has subsided and the gas has cooled to the temperature of the room. The volume of the gas is then read off. In adjusting the level, account must be taken of the sulphuric acid in the measuring tube. This is allowed for by having the mercury higher in the other tube by, say, 1 mm for each 6.5 mm of sulphuric acid. Or it is counterpoised by an equal height of sulphuric acid in the levelling tube, in which case the 2 mercury levels are made to correspond. On opening the tap after reading off the volume, there should be no change in the level of the mercury. If it should rise or fall a little, a slight increase or decrease, say 0.1 cc, is made to the volume previously read off. In working with nitrate of soda, etc., in the bulb nitrometer, it is necessary to take a quantity of the substance which will yield more than 100 and less than 150 cc's of the gas. End of section 42.